Good morning. I'm going to start talking to you about the logistics. Thank you, first of all, for making out here so early in the morning. We're very excited to have a full day of colloquium fun. Our first speaker today is Jose Luis. And while the slides are getting set up for his presentation, I'm going to tell you a little bit about the way that we're going to run things today. So you might have noticed in the program that I've been sending out that we have panels at the end of every session. This is a little bit like the LPSC conference style where all the speakers in the session will speak one after another, no questions in between. And then at the end, all the speakers will come back up here and people can ask some questions. You can ask specific questions about their talk, so you can ask general questions. They're categorized so that their expertise sort of overlaps. It makes for a fun discussion-based question session. And yeah, I think it'll be a great time. So yeah, and then after every session, we'll have a break or lunch. Our two keynote speakers are on either side of lunch. We have Tony Chen and Penny Boston, who will be giving our keynotes. The other organizers today, if you have questions. So I'm Abby. We have Olivia down here who's helping coordinating all of the slides. Jaleese is up there running catering, and Chloe is all the way in the back running around doing logistics. So if you have any questions, feel free to ask any of us. Oh, here, set you up with this mic. Oh, so it doesn't have feedback. Okay. All right, without further ado, here is Jose Luis from Dr. Chris Carr's lab presenting on frontier orbital energy distributions in abiotic and biotic systems.
Thank you, Abby. Good morning, everyone. What an honor to be the first one. As Abby said, my name is Jose Luis Ramirez Colon. I'm a PhD candidate in the School of Earth and Atmospheric Sciences, working in Dr. Christopher Carr's Planetary Exploration Laboratory. And over the next 10 minutes, I'll introduce you to an approach that Chris, Grace, and I have been developing in order to distinguish between abiotic and biotic organic matter using frontier orbital energy distributions, where I get more into detail in a moment. So probably everyone in this room has previously heard that all life as we know it is carbon-based. We are composed of carbon molecules that drive all biological functions, from building structures to information storage to regulating metabolism to even making mundane look as adorable. Yet organic molecules have been detected beyond Earth and even beyond our solar system and can form via abiotic processes. Therefore, this raises the question of how we're going to search for carbon-based extraterrestrial life if we reside in an organic cosmos. So for the past few decades, astrobiologists have dedicated a lot of effort to define biosignatures as part of the framework to search for extraterrestrial life. And as part of today's presentation, we're going to focus on the patterns of an organic class of compounds known as amino acids. Life as we know it uses the same 20 amino acids to build proteins, which catalyze a metabolic reaction. And out of these 20 amino acids, 12 have already been detected in meteorites, and 5 of the remaining 8 have known confirmed abiotic routes, with the remaining 3 having tentative, not yet widely accepted abiotic routes. Therefore, the detection of any of these amino acids in an extraterrestrial sample wouldn't necessarily be the indicator of life. Also, other patterns of amino acids have been historically assessed in order to distinguish between biotic and abiotic systems. However, advances in analytical techniques are blurring these differences. For example, biotic samples have generally shown increased concentration of amino acids compared to abiotic systems. However, samples from the Murchison meteorites have shown increased abundances of amino acids compared to some environmental samples from certain regions of the Atacama Desert. Furthermore, life is known to exclusively select for L amino acids, yet Murchison meteorites in general have shown L enantiomeric excesses up to 20%. Finally, Okay, now it's not showing the, there we go. Okay. And life as we know it is also known to incorporate lighter isotopes within their structures, yet biological processes have also shown to enrich for carbon-13 and nitrogen-15, overlapping with meteoritic values. So given these challenges, over a year ago, we set out to improve the framework to distinguish between abiotic and biotic amino acid systems. And we follow 6 key criteria. We wanted to develop a method that was mechanistic based on physical quantifiable characteristics, also a method that was adaptable, able to be used across different data sets, sensitive and specific, minimizing false negative and false positive, also robust, achieving more than 90% accuracy in distinguishing between these 2 categories, and finally being able to be spaceflight compatible. So that's how we ended up landing on the HOMO gap, which is a quantum chemical property used to describe the energy difference between the highest occupied and lowest unoccupied molecular orbitals. And these molecular orbitals are essentially used to define the minimum energy required to excite a molecule. So therefore, it's a proxy of how reactive or how stable a molecule can be. And you might be wondering, how did we landed on this idea in the first place? So we were inspired by this paper, Granol et al. 2018, that showed that those amino acids that have not been detected in meteorites so far have relatively low HOMO gaps. Therefore, they are more reactive. And they have been suggested that these amino acids were the last ones to be incorporated into the genetic code in order to mitigate oxidative stress in cells that were emerging in an oxidizing world. So instead of simply just comparing the HOMO gap of meteoritic amino acids versus biotic amino acids, we thought that it would be more insightful to also include the abundances of these amino acids within their system. Therefore, we built a database of 187 amino acid profiles from environmental and abiotic samples. And then considering 54 amino acids, then we calculated the HOMO gap of these amino acids and then applied 3 different statistical metrics: the weighted mean, the weighted variance, and the Gini coefficient, to account for abundance weighted distributions. We finally use class separation methods in order to assess how well our approach distinguish between biotic and abiotic systems. And here are our results. So we can see in the right plot that the HOMO gap outperforms 9 other molecular descriptors that we explored in this study, including the molecular assembly index. In distinguishing between these 2 categories, we can also see that the HOMO gap ranks the highest among the 3 different statistical metrics that we consider. And in the plot in the left, we can show the distribution of weighted variance values using the HOMO gap as the input property. And we can see a clear separation between these 2 categories with minimal overlap with only 5 samples. And in the plot in the left down part of the slide, we can see when comparing to the molecular assembly index, we can just see a slight improvement of class separation with just this sample. So moving on, in order to assess the specificity and sensitivity of our approach, we plotted the receiver operating characteristic curve using the weighted variance values, and following this yellow line over here, that is the one regarding the HOMO gap, we can see that at a false positive rate of 0, which would equal to 100% specificity, we see more than 0.9 true positive rate, which will equal to more than 90% sensitivity. And we can also see an area under the curve of almost close to 1, which is that of a perfect classifier. So finally, we tested the robustness of our approach via machine learning classification using a medium neural network. And we can see that when comparing all the properties that we explore versus just the HOMO gap, we see very similar performance metrics, basically telling us that the HOMO gap has most of the discriminatory power in this case. Finally, our approach is almost flight ready. Essentially, any flight heritage instrument that can identify more than 3 amino acids with their structure can support it. But more importantly, in our research group, we're developing ELI, which is a TRL-L2 solid-state single molecule detector targeting amino acids. And we have previously shown using data from our collaborators with a solid-state nanogap device that the homologap of the amino acids tested has a really good relationship with the resulting conductance patterns from the instrument. Therefore, we think that ELI could be a really promising instrument targeting direct measurements of homologap in the future. With that, I conclude my presentation showcasing the next steps for the projects, which are depending on an ICAR proposal, so fingers crossed. These include extending the analysis to other classes of organic compounds, exploring the effect of pH, temperature, and solvent on the homologap, assessing other type of abiotic environments aside from the ones that we studied that were mostly meteorites, and finally measuring the homologap using flight heritage instrumentation. I'd like to acknowledge our funding sources and our collaborators. Thank you very much.
Thank you so much, Jose Luis. That was a great talk. Our next speaker is Vahab Rajai. He's from Dr. Lauren Williams' lab, and he's going to be talking to us about wet-dry cycling. Did anyone hear about that farmer who won the award for his cows? They were outstanding in his field. Yes. This is a long one. The other day I was reading this article about corvids, crows and ravens, and they found that some of them get hit by cars and trucks on certain parts of the road, but normally they post lookouts for each other so that they don't. And what they found as they were studying this is disproportionately the crows were getting hit by trucks instead of cars. And this was because they didn't have a word for truck. They could only say caw, caw. Without further ado,
Okay, is that better? Wonderful. Okay, I'm going to be sharing some work on chemical evolution of organic mixtures via wet-dry cycling. I'm part of the Williams lab here at Georgia Tech, and I will jump into the presentation. So I want to take us back to the Hadean Earth first, just to set the scene a little bit. So we are broadly interested in the origins of life, and the Hadean Earth formed about 4.6 billion years ago, and I want to cover a few kind of important pieces of context. So first I want to talk about land-water interfaces and the fact that there was water even present on the Hadean Earth, despite it being such a harsh, hot, and inhospitable climate. But there was liquid water, and models show that as early as 4.4 billion years ago, there would have been land-water interfaces. this will be important for our experimental model a little later. And I also want to mention that there would have been organic matter raining down on the surface of the Hadean Earth. This is a illustration that is illustrating what it might look like on Titan. The other thing I want to mention is that the Hadean Earth, as well as the current Earth, they spin. This is the diurnal cycle. This is what accounts for the day-night cycle. And this will tie back in later when I talk about our experimental platform, wet-dry cycling. You can think of it as being analogous to this diurnal cycle. Okay, so the Hadean Earth forms, and then somehow over the course of 4.6 billion years, we arrive at the current Earth. There's a lot of things that happen in here. One of those things is the origins of life. And what is the origins of life? Well, we know that somehow we went from a prebiotic primordial soup to something that resembles life, but there's still a lot of open questions even within that time frame. Now, I like this image. This is a mural from JPL, and they kind of have you starting off with organics on the left side and moving all the way up to a telescope where you have humans looking out into space again. But out of the context of this big picture, we arrive at something that's like life somewhere in the middle there. And the work that I'm going to present on today is really focused in over here, where we have these organic molecules. They are somehow turning into something like a biopolymer of life. I think they're showing DNA here, but it could be protein, polysaccharides, other things as well. So I touched on there being water present on the Hadean Earth. Water is, we can really think of this as the currency of biopolymer bond breaking and making. So biopolymers of life, ubiquitous in all of life. We have proteins up here at the top, nucleic acids, so think of DNA and RNA here in the middle, and then polysaccharides here, think of carbohydrates and things like that. Now, every single one of these is present in all of life, and every single one of these can form through the removal of a water molecule. That's the condensation reaction. And so as you lower water activity, you form polymers. And conversely, as you add water back in, you can hydrolyze those bonds and form monomers. So you get this relationship between the monomers and the oligomers, where by oscillating water activity, you can essentially drive polymerization. Now, because of this, water is dangerous. And so another name for water is dihydrogen monoxide. It sounds a bit more intimidating, but I show this to really just emphasize that water is a bit of a double-edged sword in that you need it for life. I think we all know it's essential for life, as we know it at least. But at the same time, if you were to leave any of these biopolymers in water for long enough, they would just degrade down into their monomers. So now I want to transition into talking about the organic inventory that we use in our experiments. So the primordial soup, if you want to think of it, that we use in our experiments is centered around these molecules here. The ones that I will focus on in the data that I show are here in this central circle, but these are all going to be fairly soluble organics. And we're using molecules that are capable of condensation and dehydration reaction. So think back to the water chemistry I was talking about. And all of these molecules in here, they have carboxylic acids, hydroxyl groups, amine groups, thiol groups. All of these are functional groups that allow them to participate in this type of chemistry that we are interested in. Now, this library, our system, isn't necessarily constrained by prebiotic plausibility. Some of these molecules are prebiotic. You can find them on meteorites. You can think back to the amino acids that Jose presented on. Some of those are found in meteorites or are available through other prebiotic pathways. And some of these are selected because they're representatives from the biopolymers of life. So this would be things like the decanoic acid, kind of representative of the membranes and things like that. Some of these are found both in prebiotic environments and in life, and some of them, like some of the sugars, are just present in life and may or may not be prebiotically possible. So we have our library of organic molecules. What do we do with them? So I mentioned wet-dry cycling. This is where I want you to think back to the diurnal cycle. We have a day-night cycle, and if at nighttime, things cool down and you get condensation on the surface. So if you ever woken up and noticed some water or dew on the surface you can think of that as that condensation. But then during the day, the sun comes out, things heat up, and we can do this in a tube by just having a system in a tube exposed to. We're working at fairly mild temperatures compared to some of the other work that's done in this realm, and 45 degrees Celsius, and we let it sit for a period of time. In our case, 48 hours. And then after that 48 hours, we rehydrate, and we just do this over and over again. The results I'm going to share with you today, we've done this for 15 cycles. And then we do analysis via HPLC, NMR, and mass spec, and the data that I'm going to show today is going to be focused on the HPLC. So we do this experiment. We cycle our system, those 9 components, 15 times at 45 degrees Celsius. And what happens? So this is what it looks like when we take HPLC spectra. We can see our starting materials here. I've taken just 3 select regions to show here to kind of illustrate some purposes. But at cycle 1, we already see some new products forming. And then as we progress through these cycles onto cycle 2, cycle 3, 4, and 5, we can start to track the changes in the in the behaviors of these peaks, and the changes in the concentration, the changes in the presence of them and the identities. So we go through cycle 10, and then we go through cycle 15. And what I want to emphasize here is that the system is not reaching equilibrium. So one of the things that was really interesting to us when we first looked at this data is that the difference between cycle 14 and 15, you can't really tell that visually here, but when we look at the data closely, the difference there is actually greater than between any of these other cycles, with the exception of the first cycle. So this is reassuring for us. It tells us that the system is continuing to change and we have not reached equilibrium. If it had reached equilibrium, we would think of this as being analogous to the system being dead. Now, a few interesting things that came out of our observations from this experiment are not only we got this continuous change and we want to push the system further to see how far we can go with it, but we saw a coordinated change in the peak trajectory. So what this means is that we kind of broke it up into 4 different categories of peak behavior. So group A is the starting materials. You can think of these things that are present at the start, but then are used up throughout the course of the experiment. We have things that we categorize as group B. You can think of these as increasing at first and then decreasing. I skip group C here because it's not a good example. And then group D is things that continue to increase over time. And so we call this population synchronicity. This is another way of visualizing this. You can see group A is the starting materials I mentioned. They go away. Group B increases and decreases. Group C, which I didn't show in the last slide, this is something that increases and then kind of plateaus out or stabilizes. And then group D is continuing to increase. Another thing that we observed is combinatorial compression and product subtraction. So working with a 9-component system, you get into a combinatorial space where you can have hundreds, if not thousands, of different possibilities of products forming. And so this is just a kind of a graphical representation of what it might look like if we were to take our 9-component system and form all the possibilities up to trimers. You can see that that already starts to get really overwhelming, and this is representative of a combinatorial explosion. Now, what we actually observe is something more like this, where we get only a select few, and this tells us that there's some kind of selection going on, and that there's a process that is compressing the system. So this was a particular interest to us. We're still studying this further, and we established that this is a temperature-dependent phenomenon, and this is another way of showing it instead of just a graphical representation with the data that we have. Showing this is on a log scale. We have our theoretical versus what we actually observed. And then product subtraction just means that the subsystems that we do experiments with of our 9-component system, they produce peaks that are not observed in the full system. So I want to wrap that up here and mention that this we submitted this paper back in 2022. So after 2 years and a couple months, it was finally published just a couple weeks ago. So there's a QR code to the paper itself, and then also for the preprint if anybody is unable to access that. And then so far it's doing well, so we're excited about that. So hopefully that continues. And then just due to time constraints, I wasn't able to get too much into our model chemical evolution, but the experimental part that I showed has been really focused in on here. And there is a preprint out of this as well if you're interested in learning more about how we're thinking about chemical evolution. And this is currently under review, so hopefully stay tuned for more. And with that, I will wrap up with acknowledging the funding sources and all the people who have worked with this and the whole Williams group. Thanks, everyone.
Thank you, Vahab. How about those graphics? I want that HPLC plot on a shirt. Our next speaker is Bree from Dr. Hudd's lab. I'm going to stretch it out to get the slides up. We have a little bit of breakfast left at the back of the room. Yes. Yes. So if anybody's still feeling a bit peckish, grab some now while you can. Bree is going to be speaking about some candidate proto-RNA in the realm of pre-evolution biopolymers.
Can everyone hear me or? Okay, cool.
Great. And without further ado, here's Bree.
Good morning, I'm Bree from the HUD Lab, and I'll be presenting on a proto-RNA, especially in the context of the chemical evolution of informational biopolymers on early Earth, hopefully. So to begin with, I'm going to introduce the RNA world hypothesis. And basically what it supposes is that in between DNA, which is a purely information storage molecule, and protein, which amongst many things is capable of doing reaction catalysis, you have RNA, which is capable of doing both. And based off of that observation, people have really pursued RNA as like the first biopolymer on early Earth because it's capable of doing everything. It bridges the gaps. And if you get RNA, you have the capability of Darwinian type evolution. But the problem with that is it inherently presupposes the prebiotic plausibility of ribonucleotides, and which has resulted in some issues. So real quick, what exactly makes up RNA and how do you break it down? So what we do is we break it down into 3 individual components. You have the ionizable linker, which in this case is phosphate, your trifunctional connector, which connects all the pieces, and that is ribose. And then you have the recognition unit, which are the nucleobases capable of storing information via Watson-Crick hydrogen bonding patterns. You have the pyrimidines, which are single ring, and you have the purines, which are double ring. And as I said, there's prebiotic issues with this. Nobody's really found a consistent, repeatable synthesis that is robust and also been able to polymerize it to a significant enough extent, especially if you're starting from monomeric units. And so what our lab does to circumvent those particular issues is we've proposed the concept of the chemical evolution, starting from a proto-RNA all the way to extant RNA, where over time, as the chemical landscape and the Earth conditions change, you could potentially swap out some of those individual components based off of chemical selection pressures and actually get you to the RNA at the end. So what our lab has been doing is we've swapped out that ribomonophosphate backbone out with a amino acid backbone. And this has precedence. It was first proposed by Dr. Estermoser and has been worked on since by Estermoser and then Dr. Krishnamurthy. And his initial proposal was using aspartic acid and glutamic acid as a dipeptide backbone, as a nucleooligodipeptide. And the reason it was attractive or has been attractive is that the sterics and the structure of that dipeptide is homologous in a way to the extant ribomonophosphate backbone. And so as such, our lab is focused on 3 specific amino acids for our backbone. So you can have the trifunctional connector be 2,4-diaminobutyric acid or aspartic acid, which both have just 2 carbon backbones. And then for the ionizable linker, we have aspartic acid or glutamic acid, which are both capable of holding a negative charge. And all of these amino acids are prebiotically plausible. So for swapping up the nucleobases, this is a candidate 4-letter prebiotic system. The only one we've worked on so far is that top one, which is with the uracil and adenine homologs. So the top is cyanuric acid and melamine, which are capable of doing a homologous hydrogen bonding pattern to uracil and adenine. At the bottom is completely hypothetical, but it's amylide and amyline, which would have a cytosine guanine type hydrogen bonding pattern. And an interesting thing to note is the homology also of the linkage to the backbone, so the location there. So for the pyrimidine analogs, you have it linked to the ring nitrogen. And then for the purine analogs, like with the actual purines, it's attached to that more exocyclic nitrogen point. So there's some structural homology there, which is attractive to us. One reason we really like, especially like cyanuric acid and melamine, which we have tested before, is they form these hexad structures. So there's 2 hydrogen bonding sides to each one. So you're able to form these 6 component rings of alternating nucleobases, and those end up stacking on top of each other in non-covalent supramolecular structures. And once you have that, which helps to increase local concentration, isolate our nucleobases or our protonucleotides, you're able to better polymerize those structures because they're more nearby each other, and it helps to orient the selection of the backbone linkages. So our current system, which will hopefully be published within the next year, is with melamine and cyanuric acid, like I mentioned. And this one, it has the diaminobutyric acid and glutamic acid as the backbone. And those form the hexad structures. Our assemblies, if we're starting from the monomers, are with just one has a backbone unit, and then the other one doesn't. So it's a free protonucleobase. And those stack on top of each other in supramolecular structures, as can be seen in our AFM atomic force microscopy images. So you get these nice fibers. And then when you add a condensing agent, the goal is to polymerize those 3 backbones that are going to be present on that structure. And so this is work by Dr. Karunakaran, the initial work where he polymerized the melamine protonucleotide using cyanuric acid as the protonucleobase free in solution, and he got up to 16 mers. But if you look closely here, we found that there was some heterogeneity, and when we repeated the experiments with the method on the HPLC for better peak separation, we found it was more heterogeneous than we thought, which is why the paper is taking so long. And so we found that with increased assembly, so going from a 1:0 to 1:3 ratio of our nucleotide with the protonucleotide with the protonucleobase, we found that the main thing that decreases is the epimerized product, which is a side product of EDC being a slow reaction. And then we've also seen some changes in the relative intensity of the gamma linkage, which is with the side chain. That's the middle peak, and then the alpha linkage, which is the far right peak, which is like the canonical polymer of amino acids. And some of that heterogeneity remains in like the 3-mer, 4-mer as you go on. And then we've polymerized also the cyanuric acid monomer with melamine as the free base. And we also see that linkage heterogeneity. So we want to look at, are there any benefits between the different types of linkages? So again, the alpha, canonical, gamma, side chain linkage, and epimer, unfortunate side product of EDC. And so when you assemble these and polymerize those, we see a difference in the behavior of how they're able to polymerize. So at the bottom, you have the alpha linkage, which generally gets us the greatest yield of polymers, although as you can tell, it's a little messier and has a bit more linkage heterogeneity. The gamma polymerizes beautifully cleanly. You just get nice solid single peaks, but its yields are a little bit lower. And then the epimer is able to polymerize, which we weren't expecting at all. And it does have some heterogeneity, and it doesn't polymerize quite as well. And so we wanted to look, are they forming fibers like our monomers are, and do they have different structures to them? And the answer is yes. The gamma makes nice clean fibers. Thank you. And then the epimer, however, does some weird spaghetti stuff. So that might explain why it doesn't polymerize as well. Unfortunately, we didn't see the alpha melamine tumor forming fibers, which is a bit concerning. However, if we make a 6-membered backbone, so every bearing partner has a backbone on it, with the melamine and cyanuric acid with the alpha linkage, we do get assemblies, which can be quite stable if you ask our postdoc Sejena. So the main reason we're specifically interested in the alpha-linked backbones is the way that it assembles based off of our modeling gets us beta sheet structures, which have very nice hydrogen bonding with the peptide backbone, which makes for very stable structures. So that's our ultimate goal. Generally, it seems to the best backbone for the 6 backbone structure has been alpha based off of our modeling. So we want that to work, hopefully. And since I have time, I've got some really preliminary results on my thesis subject, which is instead of using cyanuric acid, I'm actually using barbituric acid, which swaps out that nitrogen connecting point with a carbon. So it's now able to enolize if you use a carbonyl containing trifunctional connector, which in this case is the aspartic acid I mentioned earlier. And what that is able to do is it can enolize, and that hydrogen that can be passed between the two can hydrogen bond and potentially increase the stacking structure or surface area of our compound and potentially make more stable structures. And also it is now a labile linkage, so you can do base and component exchange. So it's more prebiotic because it has a reversible linkage. You can actually make it potentially in prebiotic conditions. And I found that it's pretty much what Esther Moser was proposing with that aspartic acid glutamic acid pattern. And so I have a base paired with melamine, and I was able to get polymerization, very, very tentative peak assignments because I haven't gotten to confirm it yet. It's that new, but it polymerizes and it looks like it has linkage heterogeneity like the rest of them. So in conclusion, we can form supermolecular assemblies which aid in non-enzymatic polymerization. The hexad assemblies with 3 backbones permit greater linkage variety. Oh, I was also timing 1 second. Linkage types impact the assembly and polymerization behavior, which could be a point of chemical selection, and the more prebiotic protonucleotide with an exchangeable base may actually be possible. My acknowledgements are funding from NASA, and then everyone in the HUD lab, especially all the people who helped make my molecules for me. And yeah, that's it.
Very much, Bree. That was a great talk. Our next speaker is going to be Tony Bernetti. He's a postdoc in the staff scientist, sorry, in the Ratcliffe lab. And while we pull up those slides, I do want to ask y'all one question. We've been talking a little bit about prebiotic soup. Do you think it would taste good? Big thumbs down. All right, Tony's going to be talking about a relationship between things that you don't think are related, evolution, machine learning, other optimized phenomena.
Oh, forgot about
On the mic. Good call. After Tony's talk, we'll have the panel that will end at 9:32, and then we'll have a quick six-ish minute break before the next talk starts. So if you have to go to the bathroom or anything, be prepared to do that after the panel.
Right, this thing on? Yes. All right. So thanks for the introduction. So I work at the Ratcliffe lab. Most of the time, I am doing long-term evolution experiments on yeast about multicellularity. This is a little different. This talk is rather speculative, and half the reason I'm giving this talk is I'd love people's thoughts on how to move some of these odd ideas forward. So let's get into it. So how do I make it go? There we go. So really big question. What is evolution anyway? This is not a small question. The question you can sort of restate it as, how does matter spontaneously organize into complex forms? Because it apparently did, and it apparently continues to do so. And under what circumstances is this kind of process possible? And just why does it work? And it turns out that's a more interesting question than you think. So adjust my microphone. I keep breathing on it. There we go. So I started thinking about this looking at the long-term evolution experiment from Richard Lenski. There's been a long-term experiment where E. coli have been adapting to a bad growth media for longer than I've been alive. And it turns out that the fitness of the bacteria in this experiment is really predictable. It follows a very specific power law. I'm not going to have a lot of equations in this talk, but suffice to say, with a little bit of adjusting of the coordinate system, you can verbally restate this equation as every time the number of generations in the experiment doubles, the fitness goes up by X%. And it turns out that kind of power law is really oddly common. A very, very similar power law governs laboratory evolution experiments training machine learning systems, simulations of non-equilibrium thermodynamics, and more. I think I found 8 systems so far where I can fit the power law together like this. Things as varied as the industrial learning curve, where things get cheaper when more are made, to establishing electric arcs through air. So, and you might say, okay, that's just a power law. Power laws are common, but I don't think it's just a power law. These power laws are very similar to each other in an important way. And to illustrate it, I'm going to show you that sentence about what the power law means with these 3 different systems. And that is, when the number of bacteria that have ever lived doubles, fitness goes up by X%. The bacteria that have ever lived is equivalent to the number of training cycles or the amount of energy transferred through the system. Fitness is related to loss and the amount of energy the system absorbs, and whether it goes up or down is just dependent on exactly how those things are defined. So these concepts are weirdly related to each other in a way that I think is more interesting than just, oh, it's another power law. And just to demonstrate this relationship in detail, I'm going to turn a machine learning curve into an evolution curve. So I managed to get a hold of some of the training curves from OpenAI language model creation from one of their papers, up to and including actually GPT-3. And so I got them into a spreadsheet. And so here's a graph of the loss of training some machine learning systems. Loss is basically a measure of how different your output is from what it should be. And this is machine learning systems that vary in size by a factor of 1,000 from each other. And they talk about it in terms of loss, which is the cross entropy of the bits, and they talk about it in terms of the total amount of computation implied. If you can turn computation into the equivalent of generations by dividing it by the size of the model, and you can turn loss into an equivalent of fitness with an operation that's a little more complicated than 1 over it, but not much more complicated, and you can turn it into basically evolution curves, the equivalent of generations and the equivalent of fitness. And I can fit the Lenski power law curve to these curves with a correlation coefficient of 0.996. It's kind of hilarious. And so why should these systems follow the same kind of power law? Yeah, power laws are common. They are all optimizing systems with some kinds of landscape, but I think there's something a little deeper going on, an actual mechanistic reason. And I'm going to talk about those same 3 systems real quick to tell you what I think that is. So let's talk about some non-equilibrium thermodynamic simulations that Jeremy England's done. Suffice to say, it's just a network of weights and springs. You're pumping energy into the network by shaking some of the weights, and energy is removed when the thing sort of starts shaking in a way that anticipates that motion. And it rapidly optimizes into a form that absorbs almost no energy. So think about those springs. If a spring doesn't receive any energy, it's not pushed so it doesn't change. If it receives energy, but it passes it along because it's part of a nice energy channel, it doesn't change. If it receives energy but doesn't pass it on, energy builds up until it changes. And that's sort of a mechanism of how this is optimizing. Now let's talk about machine learning with gradient descent. Don't have time to go into the mechanism of this, but if you have a parameter in a machine learning system that doesn't affect the output, it doesn't change because there's no gradient. If a parameter is already at an optimum, it doesn't change because there's no gradient. If there's a parameter that affects the output, but it's not optimal, it climbs the gradient. And I think these 3 cases are actually related. And then, if we talk about genetic evolution, those same 3 cases. If you have a genetic locus that doesn't affect reproduction, it doesn't change. Technically, it drifts, but whatever, slightly different dynamic. If you have a locus that's vital to reproduction, it doesn't change. It's under purifying selection. And if you have a locus that can mutate to increase fitness, it evolves under positive selection. And I think all these 3 things are related. And it turns out there's one way you can talk about all of these things. And that's talking about them in terms of evolution-like processes involving sort of a frustrated flow. Something is flowing through the system that rearranges the system when it reaches an obstruction. In non-equilibrium thermodynamics, you're maximizing a flow of energy from a source to a sink. In machine learning, you're maximizing a flow of mutual information from the input to the output. And in evolution, you're maximizing a flow of genetic information from the past to the future generations. And they have different reasons that they act like this, but they all have one. In non-equilibrium thermodynamics, flowing energy builds up at obstructions and jiggles them until they change. In machine learning, it's just a simple enough system that you can directly calculate how to increase mutual information. And in evolution, the act of reproduction, the act of information flow, jiggles all the loci via mutation, and those that increase the flow are retained, and those that decrease the flow are rejected. So, and this is a really general process, like even erosion can be talked about in this way. And something interesting here, I think this means that insights from machine learning can be applied in evolutionary biology and vice versa. And so I'm currently actually working to try to figure out, try to do some experiments on this in the lab with trying to reproduce catastrophic forgetting in an evolution context, and working with Mark Davenport to figure out what the equivalent of a diploid neural network would be. And so what's interesting too is I think this means machine learning is actually machine evolution. But so I'm trying to work to make this rigorous and mathematical. One method I'm looking at is Shannon information theory, talking about a noisy channel transmitting its own blueprint. Turns out percolation theory is relevant to this very appropriately, but I'm less familiar with it. And I'm looking at math of other related systems, and I welcome any ideas from people after the fact here. So I've got about a minute and a half. So I have some more slides, but I'm going to zip right through just because I wanted to show you one really interesting graph. I noticed something new when I was looking at these machine learning curves. And that's what happens right at the very beginning, right when it's first starting to train/evolve. If you zoom way the heck in, it doesn't look like the Lenski curve anymore. It's got this weird little accelerating returns hook. And it turns out that it's following the Lenski curve after the fact. That very beginning, it's actually a perfect parabola. I'm not quite sure why that yet, but I'm working on it. But it turns out I've seen this before. You see that kind of accelerating returns in AVITA simulations of computational evolution right at the beginning of a run, when their quote unquote genomes are mostly inert no-ops that do nothing. You even see it in erosion simulations. Here, this is a simulation of erosion, and that bottom left graph is the rate of sediment transport, which is basically equivalent to the rate of change of the system, sort of the derivative of one of those previous graphs. You can see it starts out accelerating and then it decelerates. And I decided to see how similar this was to other things. So I took those machine learning curves I had and I took their derivative, and I laughed when I saw this. It was kind of hilarious how similar they were. So I think that accelerating returns happens when you have the first channels digging through a previously inert material or previously inert system. And then once the channels exist, power law decelerating returns happen as they optimize more slowly. Do you ever see this in evolution? No one ever has. Maybe you would have seen that at the origin of life 4 billion years ago, inert matter first gaining the ability to be an information channel. So some speculative takeaways here. I think evolution-like processes occur when a flow is being pushed through media that has enough degrees of freedom. I think this says that disparate approaches on the origin of life are actually looking at very similar phenomena. You have metabolism is driving an energy flow through previously inert matter. Heredity is driving an information flow through previously inert matter. They're both important. And I think this suggests that the origin of life might be an accelerating returns process and could be rapid by comparison to some of the later processes. At least that's seems to be the case in these systems that show that accelerating returns that I've seen so far. So thanks to the whole Ratcliffe team for supporting me as I think about this while I do my evolution experiments. And that's it. Thank you.
Thank you very much, Tony. That was a really cool talk. Can I have the other 3 speakers from this session come hang out up here? The way that we'll do this is I'm going to try having y'all say the question without me running the mic to you, just in the interest of time. If the volume doesn't work and we can't hear you, then I'll run around with the microphone. Speakers, please repeat the question so that the folks online can hear. And yeah, does anyone have any questions for any of these speakers? Oh, hold on, we'll go with Alex in the back.
Okay, so Alex's question is whether or not we plan on using wet-dry cycling to oligomerize our structures. Our lab has done wet-dry cycling in the past with deoxypeptide oligomerization with our protonucleotides, more or less, and it wasn't as good because the assemblies don't really help when it's dry for the oligomerization. However, for like synthesis of the more prebiotic nucleotides, I'm hoping to use maybe wet dry cycling to get the barbiturate acid onto the aspartic acid. But for the oligomerization, we're leaning more towards sulfur chemistry for polymerization instead.
Other questions out there? Else I'll let Tony ask one. Go ahead.
So the question is, how have I looked at sort of dynamics of these things, and if inserting randomness into systems sort of is one of the reasons that this works? Is that an appropriate summarization, or? Okay. Dynamical systems. So I've mostly looked at data from other people so far. Right now I'm doing my first actual experiments where I'm basically trying to replicate some machine learning experiments in evolution. But there are people who have there's the simulations that I talked about with non-equilibrium thermodynamics are actually really interesting. They just throw up a random network of weights and springs, and they can throw up all kinds of different random networks. And it turns out they all sort of behave in the same sort of way, despite their little tiny details. More broadly, I think, like, this is something I can't state this rigorously right now, but I think that one of the things that I think what defines a system that can have this kind of behavior is that it needs to be able to sit there and hold structure when it's not being driven by something, but it needs to also be able to react to a flow when a flow occurs. So you need something that can be stable but is mutable enough to actually react. So that's what I'm thinking so far. So,
More questions from the audience? Tony, go ahead.
I have a question for you. You were talking about the measurement between the orbitals. I forget the exact name of it, but and how biotic was mostly was mostly the ones with larger gaps, and abiotic was mostly the smaller ones. Could that have anything to do with stability? Is this sort of a proxy for stability, and biotic systems are actively generating things, whereas abiotic systems they might have been sitting around for a while?
Yeah, sorry, exactly that. So the question is that if the distribution that we're seeing in terms of the homo gaps, where the biotic systems have a broader range of not only stable but also reactive homo gaps, where the abiotic only has stable, and the answer to that is exactly has to do with the stability in meteorite parent bodies, for example. Abiotic processes are thermodynamically constrained, so we have seen actually a good relationship with the amino acids that we see on meteorites are those that are able to survive, for example, like vacuum UV. And we have this hypothesis that in the other side of things with life as we know it, we have this hypothesis that life is able to control like when, how, and where reactions take place. Therefore, it's constantly providing a sort of like a stable environment in order to be able to produce these more reactive amino acids that we're not necessarily seeing in the abiotic samples.
Thank you. I have a question for Vahab. Does anyone out there have any more questions before I ask it? Okay, Vahab, can you talk a little bit about how the rate of hydration and dehydration might affect the chemical reactions that you're seeing? Is there any impact, or is it completely not important?
No, that's a great question. So this is really important to think about in the context of what persists in our system. So talk about chemical evolution and selective pressure. So if there are different rates of hydrolysis and the different types of bonds that form in our system. And so the things that hydrolyze slower will persist in the system longer. Things that hydrolyze quickly will be broken down faster. And so you get this dynamic between what can stick around longer. And then, of course, you have other factors that might come in later, like folding or assembly, that might protect certain groups over others. So rates of hydrolysis certainly factors into what sticks around and what doesn't.
Awesome, thank you. Any other questions for the speakers? Go ahead.
Yeah, so thus far we have only explored amino acids. Kind of like our next step is expanded to other relevant biomolecules, including nucleobases, sugars, even also like precursors to that, carboxylic acids. But yeah, thus far we have only explored amino acids. We do have done some sort of like we've explored other abiotic simulations of other type of environments other than meteorites and their parent bodies. So we have looked at maybe like Titan, Enceladus, even early Mars simulated formation of amino acids. And it's been really interesting because we have also now are trying to implement how we can use the HOMO-LOMO-GAP to potentially assess habitability of an environment or see how life might evolve with different reactivity in terms of like molecules. So I feel like there's a lot of, I guess, space for exploration that we can continue doing with this really interesting quantum chemical property.
Thank you. All right, it is now break time. I'd like to encourage everybody to eat some more breakfast, drink some more coffee. It won't be there at the next break, so take it while you can. The restrooms are somewhere around in this building and at that direction. And I would really love to see everyone back here a little bit before the start time. We're starting again at 9:38. Would the next speakers for the next session plan to sit up front so that you can get to the microphone quickly and make transition speed? Thanks, y'all. One more round of applause for the speakers.
Oh. Am I audible? Am I coming through speakers? Wonderful.
All right, our next speaker is Beck Palmer from Dr. Lightsey's lab and from the Space Systems Design Lab. So I'm really excited to hear their talk. Take it away.
Morning, everybody. Bright and early. So my research, not to bury the lead, is looking at debris selection for aluminum recycling that will hopefully take place on the moon. The key's not working. There we go. Are we just going to have a little search box there? Okay, hopefully we're good now. So what if we could recycle orbital debris on the moon? Obviously, orbital debris is a problem for various reasons that lots of people are trying to solve right now. One of the proposed solutions is deorbiting. However, we know that it is polluting our atmosphere. We don't know if that's bad or not, but it's probably bad. Also, deorbiting is just burning up useful material. We also have this upcoming economy, potentially, for in-space assembly and manufacturing, and a lot of Moon to Mars initiatives coming out of NASA. There's some problems that need to be solved there. You need materials. You can't make stuff without stuff. Delta V to get stuff to the moon for manufacturing is a lot more expensive, but not as expensive as getting it just from GEO, from Earth. Some people are talking about in situ resource utilization, but that's still unproven. So can we find a better way? That's what we have started to try to do with our research. We started out with a tool that can help us identify which debris might have the most valuable materials on them for recycling. So here's some questions that we use to help build our tool. How much recyclable stuff is up there, and can I touch it? So we have some criteria that our debris field that we're looking at has to be US origin. It has to be dead, so launched before the turn of the century. It has to be pretty big, and it has to be above LEO, because most of the LEO stuff is going to be too expensive to get up. So we're just looking at above low Earth orbit. And then we spent a lot of time looking for how much mass is on each of these pieces of debris, or how much mass do they have. Right now, we don't know specifically how much aluminum or how much steel. That's what our next step of research is. But we can make a general assumption about how much aluminum might be there. So the next question is, how expensive will it be to collect? We need to know the delta V cost to go and get it and take it up to, if you look here, that green orbit, that is our little collection orbit. Then we need to know how much that propellant will cost. We looked at a couple different architectures, just straight up launch fuel up there, it gets used up, single use. We looked at reusable architecture, and then we looked at maybe a far future where it's much, much cheaper. We also looked at the specs for a couple of different potential vehicles and built those into the model. So what is our objective? We want to maximize the amount of debris that is collected, and we constrained it by, if I'm driving my little recycling truck to go get debris, I have to deliver as much value to this green recycling orbit as possible in the amount of time that the lunar transfer takes to go to the moon and back to pick it up. So those are our constraints. And I get a lot of questions about, well, what assumptions are you making? What is this collection orbit? So I know this is a lot of text, but I just want to point out to you a couple of assumptions. We're assuming that this is in the future where we already have a lunar transfer that's going back and forth. We're not designing that. We're assuming that there's already active debris removal or recovery going on, and we can take those vehicles and use them for something else. Instead of deorbit, use them for collection. We are also assuming that the entire piece of debris gets taken to the moon and disassembled there. I would love for all of these to be mutable and changeable in the future, but we got to start small. Also, we're assuming a 38% aluminum by mass. This is a a general value that has been developed by others in the field. That's just what we're working with right now. We also have a pessimistic value for aluminum in our graveyard orbit. So instead of GEO, I've used GREO, which is graveyard Earth orbit. It's a little bit above GEO, 300 kilometers. We're assuming that it's worth $2,000 of launch cost. So a kilogram of aluminum on Earth is about 88 cents. But once you launch a kilogram into LEO, that costs about $2,000. So we're assuming by the time it gets way up into GEO, it's at least worth $2,000. All right. We have a couple, we ran our model a few times. We found a couple of nominal values, which is what I'm going to show you the results for next. Over 30 years, let's say we're doing these lunar transfer missions and collection in between for 30 years. For a couple different vehicles, this is a table, don't freak out. All I want you to look at is the thrust for the first two items. Whoops. The PPE, that's what NASA's using for their gateway, and the MEP, the Mission Extension Pod by Space Logistics. These two, the red line and the yellow line, are the most realistic ones we have to look at right now. The other three are in development. Over 30 years, it looks like you could consistently generate a profit by raising to GEO and selling. This is with a $600 per kilogram propellant cost. That's a reusable architecture, like I mentioned before. If we look at the far future, where it might be $30 per kilogram, where we're making propellant in space, perhaps, that potential profit margin goes up. Today, however, you're only going to be able to make profit off of the first 6 to 7 years with any of these vehicles. All right, so now that we've run the model, we have some projected numbers. Will this approach actually help reduce the orbital debris in a meaningful way? A number that you'll hear cited a lot is we need to remove at least 5 pieces of debris per year to prevent a Kessler syndrome type situation. So we looked at, under each of these pricing models for propellant refueling cost, how much debris would we remove over 30 years? On average, it's about 2 for our median price range, but this is just US debris, and the United States is not the sole contributor to debris in Earth orbit. So if we are removing 2 of our pieces per year, I think that's a significant contribution. Now, the second question, can a business case be made to bring me the debris to recycle instead of just throwing it away? And in sum, over 30 years, you can make over $60 million on average, even at the median refueling price. So that looks pretty good. So what I am hoping that if we can someday pay people a flat cost to deliver aluminum up to this recycling orbit, we can incentivize better stewardship of our Earth orbit, or our Earth environment and our orbit, and, you know, hopefully make manufacturing and move to Mars stuff a little bit easier. And I hope that you guys want to collaborate and have questions and suggestions for later. That is all.
Thank you, Beck. Our next speaker is Luca Schifoni. And give us a second just to pull up the slides and stuff. I'm excited to see recycling in space. I think that's promising for our future as a species. So Luca's going to be talking about dust shields for lunar dust mitigation, which is probably really important if we're actually going to make it to the moon again. All right, Luca is from the LGST lab, and as soon as this mic gets situated, we'll let them take it away.
Can you hear me? Yeah. So good morning, everyone. My name is Luca. I'm a PhD student in aerospace engineering. Today, I'll be presenting about the work that I've been doing for my master thesis, and it's about performance analysis and optimization of rigid and flexible EDS, that is the electrodynamic dust shield for lunar dust mitigation. Oh, here it is. Okay. So let me start with a brief introduction about the importance of the topic. The lunar soil is covered with a layer of regolith that is electrostatically charged due to photoelectric radiation and interaction with the solar wind. It is highly adhesive and abrasive, and is most importantly toxic, posing a health risk for the astronaut, and is considered one of the biggest challenges for the future of lunar exploration, because it can interact and can stick onto the astronaut spacesuits, with the rovers, with the solar panels, thermoradiators. So for this reason, the development of technologies to mitigate the effect of lunar dust is one of the biggest concerns and challenges for the scientific community. One of these technologies is the EDS, the electrodynamic dust shield, which exploits the generation of electric fields changing in time and space to interact with the charged lunar dust particles to swipe them off a surface thanks to electrostatic forces, which can overcome the gravity and the adhesion forces and swipe those particles from off surfaces. To realize an EDS, you need to realize an array of electrodes. Then you place the array of electrodes on a substrate, which can be both flexible or rigid. And then usually there is also a dielectric coating onto the electrodes to prevent dielectric breakdown and micro discharges. Here are 3 examples of EDS devices, the ones that I've been testing. Here you see black substrate, but it's very easy to make them transparent in such a way that can be used, for example, on solar panels. To show you how one of them works, I can show you one video. As soon as the EDS is activated, the dust that is on its surface starts to be removed by these electrostatic waves, electrodynamic waves. So the EDS that I've been testing are realized with a nanocomposite material for the electrodes, that is the chemically modified reduced graphene oxide, on a substrate made of high-density polyethylene. And the novelty is in the 2 coatings that I've been testing. That is, the first one is a coating made of polystyrene, and the second one is a functionalization of the electrodes. The second one is particularly interesting because this material has a low surface energy, and so it's used to reduce the adhesion forces with the dust particles. Moreover, there are flexible devices. The first type is made in the same way, so with chemically modified reduced graphene oxide on a HDPE substrate. And the second one is a flexible device made with a polymed substrate, copper electrodes, and then polymed again, so Kapton for the coating. I run like hundreds of tests on these devices in 2 different vacuum chambers to simulate the lunar environment. Both the chambers have inside a dust falling system that is a vibrating device that I use to have the dust falling onto this device while it's active, instead of covering with dust before the experiment. That is what actually we usually see in the literature. Moreover, there is a UV light source to reproduce the photoelectric charging of the dust grains. To collect data from these experiments, recorded videos, and then obtain numbers by using image analysis, so counting the number of white pixels which are directly related to the amount of dust. And as a metric for the experiments, I defined an accumulation factor. So how much of the dust that is falling on the EDS is actually sticking on it and remaining on it at the end of the experiment. One of the first investigation is about the effect of the applied voltage on this device and on the difference between different coatings. In the plot on the left, you see the accumulation of dust as a function of the applied potential, but this is for an uncoated device, which for voltages as high as 1000 volts start to have too many micro discharges and cannot be used. For this reason, it's necessary to apply the dielectric coating. And so on the plot on the right, you see the comparison between the linear regression lines for the experiment of coated and uncoated devices. In particular, it's interesting to see the performance of the red line, which is the TPFS coated device, which has a statistically significant different slope compared to the other two cases, and also a statistically significant different intercept, which means that has a better performance when we increase the applied potential, but at the same time has a good performance at its maximum allowable voltage without having micro discharges compared to the other coated device that is the green one. I ran similar experiments for the frequency. Here the data scatter was much more significant, so I realized a numerical model to compare my experimental results with the ones from the numerical simulation, which demonstrated the presence of an optimal frequency for different EDS devices, meaning that for very high frequency and for very low frequency, the EDS is not working properly because there is a problem with the timing, the characteristic time of the movement of the particles and that of the electrodynamic wave. This is something I want to keep working on because I want to refine both the numerical model and the experimental data. Here are two of the flexible devices, but the one made with chemically modified reduced graphene oxide. It was mostly a demonstration of the performance and effectiveness of these devices. What is really interesting about flexible devices is the results obtained with the other type, the one made with polyimide copper and polyimide, where given the much easier fabrication process, we could, as a team, test different geometries and, for example, electrode thickness and width. And for initial design, here you see the video where the ADS is actually getting clean, but not perfectly, while with a smaller electrode and a smaller thickness between the smaller distance between the electrodes, the clearance was much more significant and almost perfect. In conclusion, the last of the investigation was about the two factors that are reducing the performance of the EDS over time. The first one is the degradation of the device itself, because every time that there is a micro discharge between the electrodes are eroded by this micro discharge. And this doesn't cause the EDS to stop working, but dust can ingrain into that part of the electrode and start to accumulate, making the electrode not working anymore. At the same time, sometimes these micro discharges can extend to the entire substrate, as in the third picture on the right, where the substrate is completely melted. We applied the dielectric coating exactly for this purpose to reduce the amount of micro discharges, but the coating itself undergoes degradation. For example, the polystyrene coating started to lift from the surface, while the other coating, the TPFS, did not have any problem. Eventually, the analysis of the grain size distribution of the dust remaining on the EDS at the end of experiments, which is a measure of what particle size are more compatible with this technology for dust removal. I realized plots of this residual dust size distribution and compared to the original simulant distribution that I obtained in the experiment with the EDS off. As you can see, for an uncoated device, the blue plot, there is no big difference between the distribution of the dust remaining on the EDS and the distribution of the original simulant. While applying the coating, the TPFS coating, the distribution is significantly different. It's much easier to remove larger particles because the adhesion forces are smaller, and given the better performance, the lower surface energy, it's possible to overcome those addition forces thanks to the electrodynamic wave. And similarly, this happens with the UV charged particles, because the charge for larger grains is higher, and so the electrostatic force, as the Coulomb force, is stronger and can wipe off, can let us remove the dust. So in general, the smaller grain size is the hardest to remove for all the devices, and is what I'm gonna focus on from now on to go on with this research. So thank you, and look forward to hearing your questions at the end of the session. Thank you.
Thank you so much, Luca. I think one of my favorite parts about space science is how the knowledge will cascade down to everyday applications like, Velcro or whatever. I'm really looking forward to when Luca's technology gets to be available for auto manufacturers to keep the pollen off of my car. Our next speaker is Vic Paulson from the Aerospace Systems Design Laboratory, and they will be speaking about some, not really whales, but a beluga project for some Titan exploration.
Sorry, can you guys all hear me okay? Okay, sounds great. Let me get this thing somewhere. Hi, thank you guys for being here today. This project is what got me into astrobiology about a year ago, and so I'm just thrilled to be presenting it today to all of you. This project was an effort to create a non-terrestrial aircraft, and we took that very broad goal and specified it down to a Titan non-terrestrial aircraft, which has biological exploration and landform understanding geoscience capabilities, also known as beluga. Oh no, I'm having the same issue everyone seems to be having. There we go. Okay, so our research team was made up of me, 3 other PhD first-year grad students, as well as 3 various advisors. Going into kind of this effort, why we chose Titan in particular for this non-terrestrial aircraft was its scientific intrigue, which is the atmospheric richness, its unique liquids being the only other body in our solar system that has stable liquids on it. It's very interesting, diverse terrain, as well as its interesting meteorological cycle. It has this entire weather system that occurs on it, and these chemical reactions in its methane, which is really interesting because it means there's a lot of astrobiological and life potential on Titan because of all of this interesting intrigue. So when we look at Titan to Earth, there's a lot of differences when it comes in terms of like, how do we operate flight there? So the first one is that there's lower gravity on Titan, which means we actually need less energy on Titan to produce lift, which means we can glide for longer and have greater ranges on Titan than Earth. There's also higher atmospheric density on Titan, which means there's more lift efficiency and more stable flight, which means we can have lighter and smaller propulsion systems on Titan with improved energy efficiency, which overall means Titan, in some ways, is a lot easier to fly on than Earth, which is great if you're making a non-terrestrial aircraft. When we continue looking at these differences between Titan and Earth, we can see that Titan has this methane-based hydrological cycle, and Earth has, as we know, our water-based hydrological cycle. And so that's kind of the real thing this aircraft wants to study and look at, which is, just a proposed idea at this point. But also Titan has this really low solar intensity. Because of that atmospheric density and that weather I was talking about earlier, it has a lot of clouds and a lot of haze, which means you cannot power this non-terrestrial aircraft using solar panels, which means our team had to look into using an alternative, and it obviously can't be refueled, so we looked into using an RTG and designing an RTG for this use case, as well as it has a lot of really low surface temperatures, so it means it needs really durable materials to resist this extreme cold temperatures. So overall, why are we making a non-terrestrial aircraft? I know a lot of you guys know about Titan and you know about Dragonfly and Cassini. Why are these missions not sufficient? Cassini had pretty much an entire global coverage of Titan's surface. However, its resolution was about only 1 kilometer, whereas the Dragonfly proposed mission has this really high 1 centimeter squared resolution. However, it has a really minimal coverage. And if you guys know about the Dragonfly mission, it's pretty much staying just located on Titan's dunes. However, I'm really interested in those liquid water bodies and this not water cycle, liquid methane cycle. And so I want to have something that fills this research gap and can glide over those large water bodies. And so this is why non-terrestrial aircraft in particular. And like I said, I wanted to look at these large water bodies. So we're looking at Kraken Mare, which is Titan's largest methane lake. It has a surface area of about 400 kilometers square, or about as large as the Black Sea. It's at Titan's North Pole, and its composition is methane and ethane. Overall, we would have a 6-month-long mission duration, and because of Titan's seasons and having favorable winds, we would launch in 2040 to land in 2048 and have winds help us glide across that lake. Continuing on, our various scientific objectives of this would be to look at the shore composition and topography and those various wind and surface currents and tides using imagery. And then we would also want to use infrared imagery to look at the geothermal activities under the aircraft and that hydrologic cycle. So continuing on, after we look at our scientific intrigue, we of course need to communicate that back to Earth. So that's going to be having to use the current deep space network to have that communication. And we're going to need to have 100 hours of visibility between Earth and our aircraft in order to use that network to communicate. So continuing on, now that we know our mission, our scientific intrigue, how did this actually get designed? There was a lot of very interesting modeling and simulations and engineering, where here is just a brief overview. And from this overview, from all of these codes and simulations, we were able to get a sized aircraft design. This aircraft ended up having, like I said earlier, that RTG power system, a mounted V-tail, and 3 propeller blades, as well as a cruise speed of 10 meters per second. It's going slow, it's just gliding over this aircraft to conserve energy. Again, you can't refuel it. It has a wingspan of about 4 meters, so it's not very long. It doesn't have any unfolding mechanisms in those wingspans to not have a ton of complexity and also be able to fit inside an aeroshell. Now, inside of this, we also determined the various instrumentation, and we were able to use a payload distribution algorithm looking at the various size and volume and center of masses of all of these instruments and distribute them in that blended wing body shape to make sure that we had all of our instrumentation and payloads that we needed. And as you can see, the majority of this aircraft is taken up by its RTG. So continuing on into our design, like I said, it has only a 4-meter long wingspan, which means it can fit in something like the Mars Science Laboratory heat shield and be launched on a very similar rocket, which is nice. So overall, this mission and aircraft was designed and sized and is currently the most complexly sized with our payload algorithm and this blended wing body and our sizing and our wind considerations and constraints to meet the challenges of Titan's unique and extreme environment. And hopefully this project can set a foundation for aerial exploration and looking at potential other oceanic worlds, as well as kind of the big takeaways is that our largest constraints were that very small aeroshell, meaning we could only have that 4-meter wingspan. So it kind of limited a lot of our design options, as well as our biggest impact was that RTG, which posed a large constraints and was most of the entire size and weight of our aircraft. So thank you for listening about kind of this innovative mission and technology that we're trying to design. And I'll hear your questions later.
Thank you, Vic. Looks like a whale of a project. I'm definitely excited to see where it goes. All right, for sharks, I'm done now. This is the kind of project that makes me really thrilled to have such an interdisciplinary group at ExplOrigins and part of the GT Azure Biology community. Like I said, it's really cool to have engineers talking about the ways that they will help facilitate the science that needs to go into Azure Biology projects. Up next, we have Sarah Kingsley. They're going to be talking about the thing that you don't want, microorganisms in the ISS water. Thanks, Sarah.
Hey. All right, so I'm going to be talking today about some work I did at the Johnson Space Center this summer, doing VOC analysis on microorganisms that have been found in ISS water. So VOCs are any volatile organic compounds. These are organic molecules that are gas phase at room temperature. Microorganisms are known to emit VOCs through metabolic activity, and there's a lot of evidence to suggest that these VOCs can be used in detecting and identifying these microorganisms. A pro of this method is that VOCs are pretty easy to measure because they're accessible in the headspace above a culture. So they use a lot less sample prep than other methods for detecting microbes. Cons of this method, microorganisms emit a very wide variety of VOCs at low abundances. So to compensate for this, we're looking at instruments that can detect a wide range of molecules and have higher sensitivity. Microorganisms also emit VOCs, and these VOCs are dependent on environmental conditions. So if you look at the same organism in two different media, you're likely to detect different VOCs. So for this study, we looked at microbes under environmental conditions that they're likely to experience on the ISS. Okay, so why do we care? Well, try as we might to keep our spacecrafts very clean, microbes will go wherever the humans go. And as we look at some of NASA's Moon to Mars efforts, we're going to see a lot of vehicles that are going to experience periods of dormancy. So sometimes they'll have a crew, sometimes they won't. Now, currently, all of our microbial monitoring methods do require humans to carry them out. But we still would need to know about the microbial population when there's no crew there to make sure it's a safe environment for crew to return to. So in this study, we were looking at microbes in spacecraft wastewater. And to do this, we used a simulant called ersatz, and this is just like a solution that NASA made up that's like, this is basically spacecraft wastewater. So here we looked at the growth patterns. We were aiming to determine if the microorganisms were detectable through VOC analysis in this water. And then also to identify volatile markers for the microorganisms if possible. Okay, so to do this, we set up our system using this instrument here. This is a portable GCMS, and it took measurements of the headspace, which is shown right up here, this air above a culture of microorganisms. So it would collect all of these volatiles, concentrate them, and then release them to the GCMS. The GC part is going to separate out our volatiles, and then the mass spec is going to analyze them and give us some information that will help us identify them. The organisms we were looking at in this study, we had Ralstonia piquetii, Burkholderia contaminans, and Klebsiella erosionus. So R. piquetii and B contaminans, these are organisms that are pretty commonly found in ISS water, but that's okay because they're pretty safe for humans. Klebsiella erosionus, though, is actually not very commonly found. I don't think it's been found since like 2005. But that's good because it's a coliform bacteria, which means it's an indicator of water that would make you sick. So we included it to see if we could detect coliforms as well. All right, so we started out with a little petri dish of bacteria, took a colony from that and transferred it to a falcon tube, let that grow overnight. In the morning, we rinsed and diluted the cells. We took one of the dilutions to inoculate our flasks and the others to plate. And all of this is just to make sure that we're putting the same amount of microbes in every flask we measure. We put our flasks on the shaker for 24 hours, and then we analyze the headspace with GCMS. So one thing to note, we actually grew these in 2 different media. The first media we use is called R3A. This is like a minimal media, so it has like some salts, some nutrients, some things the bacteria need, but everything is kind of like limited. The other media was our ersatz. That is even more like minimal than the R3A. So the R3A experience was kind of to give us an idea, like a baseline of what we might expect to see in the ersatz, so we knew what we were looking for in that data. All right, so here we have all of the volatiles that we detected in the R3A data for B contaminants, Arpachettii, and K. aerogenes. So main takeaways here is that each organism did emit detectable VOCs, and they emitted different sets. So while we are seeing some VOCs in common, like this guy here, dimethyl disulfide, we are seeing overall unique sets. So they are detectable and they are differentiatable in R3A. Now, going into the ersatz experiments, we weren't really sure how long it would take them to grow to a population that we could detect. So we started out preparing 5 blanks, so that's just ersatz in a flask, and then 5 ersatz inoculated with B contaminants. We measured 1 of each of those a day for 5 days. And then on day 7, we measured 2 blanks, 2 B contaminants, 2 Arpachettii, and 2 K. aerogenes. All right, and here's what we found. So the last 2 columns here, the last 2 columns are showing the B contaminants and the Arpachettii and ersatz. You may notice the K. aerogenes is not there, and that is because they actually did not survive in the ersatz. We repeated this several times to make sure, but yeah, they couldn't handle it. Probably why we haven't detected them since 2005, but you know, kind of boring for this experiment. All right, but we do have B contaminants in Arpachettii, and what we were seeing is kind of what we expected. Because there are less nutrients available in the ersatz, these guys are way less active than they are in the R3A, so they are producing less volatiles. We are still detecting a few volatiles. So in B contaminants, we found the volatile isoprene and dimethyl disulfide. And dimethyl disulfide was also present in Arpachettii. For all of these volatiles, they were present at lower abundances than the R3A cultures. I think it might be frozen. Sorry, I lost the cursor. Okay, cool. All right. Okay, so when we look at the, so we grew B contaminants over several days, so we can look at how these peaks have evolved over time. And what we found was that we started to see the isoprene peak showing up on day 2, persisting through day 7, and dimethyl disulfide showing up on day 4 and persisting through day 7. Now this isoprene aligns very well with the B contaminants growth. So here we're seeing the growth of the population over the 7 days. Now all of our growth occurs between days 1 and day 2, which matches up very nicely for when we first see isoprene. Dimethyl disulfide detected a little later. This could correspond with a change in the environment as maybe nutrients are depleted, or it could have just taken a few days for this compound to concentrate to a level that we could detect. Something that was interesting was that we actually expected Arpachettii to follow this same growth pattern. That ended up not being the case. So this phase right here, where we're not seeing any growth, this is called the lag phase. What we found was that Arpachettii actually stayed in the lag phase until day 4, and then its growth occurred between days 4 and day 7. So if I had had time, it would have been great to track abundance of peaks over time, potentially something we would do in the future. Kind of wrap things up, we were able to analyze Arpachettii, B contaminants, K. aerogenes in R3A and in ersatz. And we were able to detect VOCs in both media for all 3, except for K. aerogenes, which did not survive in the ersatz. So based on these results, this does suggest that there are VOCs that could be used as markers for microbial growth in spacecraft wastewater. Now, the current efforts on this project are aimed at analyzing the organism's genomes to better understand the pathways through which they produce these VOCs, which could give us some insight into how reliably we may expect to detect them. And to close, I'd just like to thank the team I worked with at JSC, Aaron Knott, Dr. Hong Nguyen, Dr. William Wallace, and Dr. Sarah Wallace, as well as the JSC Environmental chemistry and toxicology lab and the JSE microbiology lab. Thank you.
Thank you, Sarah. That was a cool talk. Our next speaker is someone from my very own lab, the Cicerone lab. This is Jesse Larson. He is going to be talking about our Raman instrument technology, but specifically the one that he's been working on for his thesis. His title used to be cooler. It said, Green Men, no, Green Cars, because they're using a green laser.
Hello? Everyone hear me? Other way.
The other way.
That better?
I don't know. Can y'all hear him?
Ready? Can you hear me?
All right, take it away, Jesse.
Hello? That sounds good. Ready? Can you hear me? Okay, great. Hello. So today I'm going to be talking to you about using ultrafast coherent Raman to identify biosignatures on planetary analogs. Sorry. I'll skip the summary for the sake of time. So the abundance of certain elements in the sedimentary environment of planetary analogs are often indicative of their potential habitability. These elements include carbon, oxygen, hydrogen, nitrogen, sulfur, and phosphorus. And when these elements combine to form more complex systems like minerals and organic macromolecules, then we're really cooking with gas when it comes to potential habitability indicators. Mars has shown great promise as a planetary analog that could support life due to the presence of these materials. How do we know that? We sent a rover up there, the Perseverance rover to be exact. And among other tools, this rover contains the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, or SHERLOC spectrometer. And the corny slide titles pretty much write themselves from there. SHERLOC utilizes a deep UV laser for Raman and fluorescence spectroscopy. And Raman is going to be the core of what I'm talking about today, so I'm going to get to the nitty-gritty of it here a little bit before I go on. So when a molecule is excited with a laser, the main peak that we see is from Rayleigh scattering, which is the molecules going up with the energy of the photon that absorbs and then emitting with that same energy. However, two additional processes, the Raman processes, which include anti-Stokes and Stokes processes, also take place, where a electron can be excited from an excited excited vibrational state and then emit to the ground vibrational state, or be excited from the ground state and then emit back down to an excited vibrational state. And so we get these peaks on either side of our main Rayleigh scattering peak. And the difference in frequency of these two peaks can tell us about the vibrational energies of our molecule. And these transitions are very good for identifying bond energies and therefore potential minerals, biosignatures, what have you, signs of life. So like I said, SHERLOC utilizes a deep UV resonant Raman and fluorescence setup. So that means that its excitation peak is in the deep UV at about 240 nanometers. Fluorescence occurs where you have a absorption to a excited electronic state and excited vibrational states, which then decays down non-radiatively to just the ground vibrational state of the excited electronic state, and then emits radiatively from the excited electronic state to the ground electronic state. And so you can see here that SHERLOC has taken some very clear and resolute pictures of, or spectra of both Raman and fluorescence peaks. One more thing about the Raman is that it's resonant. In a lot of cases, resonance occurs when you have the main excitation peak of a molecule occurring at the exact frequency of the laser, which increases the intensity of the transitions by a lot. And so this is a very effective method. However, there are some potential drawbacks. We want to look at the Stokes side, which is the lower energy side of the Raman peaks, because it's being excited from the ground state, ground vibrational state. And so those states are much more populated than for anti-Stokes, which get excited from the excited vibrational states. And so our intensity for Stokes is much higher. However, because it's redshifted or lower in energy, that means it can often be interfered with by the fluorescence signal, which is much greater in intensity and is also redshifted due to the loss of energy coming from the non-radiative emission. So that is an issue. In addition, some materials don't have resonance at 248, and so we're missing out on some intensity that can be picked up were we to use a different excitation signal. So this is where green CARS comes in. Green CARS stands for Green Coherent Anti-Stokes Raman Spectroscopy. And this is a Raman microscope that utilizes the anti-Stokes side for characterization. There are three beam functions here, the pump, Stokes, and probe. The pump and the Stokes or the pump and the probe are often the same beam. The most common setup is that the pump and the probe are the same, and so we're going to go with that for the rest of the talk. The probe beam is always at 532 nanometers, hence the green CARS moniker. So there are 4 steps to this process. The first step is simulate absorption from the ground state with a pump beam to a virtual state, which is then immediately simulated to emit at an excited vibrational state in the ground state. Following that, another simulated absorption occurs at the same pump wavelength, and then that emits down to the ground state in an anti-Stokes process. So this probably seems a lot more complicated than just spontaneous Raman. Why would we want to do it? What is the benefit to this? I'm going to try and allay that with a quick quantum mechanics interlude. Because coherence is the cool thing about green CARS, and it's a quantum mechanical phenomenon. And what happens with coherence is that the 2 beams, the pump and the probe coming in simultaneously, causes the beams to line up and become in phase with one another. And so this leads to all the molecules that are being excited to vibrate at the same frequency. And so they're all vibrating in unison in sync. So we have a very strong signal. This is stronger than any non-resonant spontaneous effect because it's directed and all of them are doing it at the same time. Abby has a good analogy, I think, of a stadium. Instead of clapping randomly, everyone in the stadium clapping together at once. I like that analogy. I wanted to come up with one of my own. So I'd like you to imagine you're in Atlanta traffic and you are about to miss your exit. And so you merge across a bunch of lanes of traffic. So then imagine like how much louder in volume and intensity the sound of all the people you cut off honking at you would be if they all honked at once versus if they all, spontaneously honked at different times. So that's kind of what we're doing here with the coherence effect. Some additional advantages besides the increased intensity from the coherence are the fact that we're on the anti-Stokes side, and so we don't have fluorescent interference in our signal. Additionally, if we have biosignatures or minerals that excite at the 532 nanometer wavelength, then we can get resonance with those, which we could not access with the Sherlock setup from before. And finally, we can tune the Stokes beam precisely to get a certain vibrational energy that we may be particularly looking for with a broadband beam or just through tuning the frequency of the Stokes beam. There are a few challenges to this, however. There's not a lot of room on the rover for this to take place. The Sherlock spectrometer is less than a cubic foot, and the current Cicerone setup we have is the size of a small car. So there's some issues with that. Also, this coherent process is extremely precise. The beam alignment needs to be lined up on the scale of micrometers, and this is hard to do just with a huge setup like I talked about earlier, let alone on a very tiny little laser that's also being bumped around in space. So that could also pose challenges to this working. There are some future explorations that could even be explored further to take this very conceptual idea even to a more conceptual place. And that would be generating the second harmonic of 532, which is half the wavelength of the 532 laser, which would be in the range of the minerals and biosignatures that are currently being excited through the deep UV Sherlock setup. They could also be excited as well, and we could have resonance effects and coherence effects for that too, perhaps with a deep UV CARS laser. I'd like to thank Dr. Cicerone, my PI, my mentor, Kelly Nunez, Abby, for asking me to do this talk. It's been really fun. And also the rest of the Cicerone lab and everyone here who came to listen. Thank you.
Thank you, Jesse. Don't go anywhere. It is now time for the panel. All right, same way that we did it last time, but I'll restate the rules in case anybody didn't hear. These are the speakers from the session. You're welcome to ask them questions, any of them, any question about their talk, or a general broad overview question that you think multiple of them could have an answer for. Please, speakers, restate the question into the microphone for the online audience. And if you yell loud enough, I won't have to run up and down the stairs with a microphone. Does anyone want to kick it off? Okay, go first.
Sure. So the question was, how do we assign each VOC to each organism, right? Great question. We grew them individually. So they were all by themselves. We knew that the VOCs were related to the organisms.
I have a follow-up to that one real quick. When you grow them in a coal culture, do you expect that the VOCs would be the same as if you summed all of the individual culture VOCs, or do you think that they might impact each other's expression?
Yeah, that's a great question. We would probably expect that they would have some like interactions that may affect VOCs. We did have some like accidentally growing them together contamination issues, where we saw some like differences than just like what you would get if you added the cultures or the VOC spectra together. So it's not really something that we've like explored deeply, but probably expect to see like overall changes instead of just like a mix of what you would see individually. Yeah.
Awesome, thank you. All right, Tony, go ahead.
Yeah, so this is one of the things we were looking at is temperature and all of that insulation and the type of composite materials we're going to have to use to keep it lightweight and structurally sound and all of that. And that is something that I ended up deleting the future work slide because of time, but it was one of the 3 things on the future work because all of us are aerospace engineers and not material scientists or nuclear engineers or like necessarily thermal experts.
Yeah, Alex.
Sure. So the question is, what method did we use to identify the VOCs with the GCMS? Yeah, we used a couple standards. So we ran standards for the isoprene and the dimethyl disulfide because that's what we're seeing in the ersatz. We also had a library that we used to match up the identities of the other compounds.
Other questions? Oh, yeah, go ahead.
I didn't catch the first part. Can you say it again? Sorry. So the question is, did I look at the cost of getting things out of different orbital regimes? So we didn't look at LEO because obviously there's other missions going on there and some of that's already due to be recycled for propellant. We looked at above GEO or above LEO, and those generally are pretty stable. They're going to stay like all of the old rocket bodies, upper stages, they're going to stay there for a really long time, and they're causing a lot of problems. So when we did our cost calculation for how much delta V is it going to take to go get that piece, we split it out piecewise. So we would raise our altitude, we would then circularize and finally do a plane change maneuver. So those three delta V put together ultimately was the cost. Does that answer your question?
Sure. To test the instrument's effective ability to take these measurements. Right now we have this set up currently at Georgia Tech, and what we use is samples that we know the spectra of already, and so we essentially just run samples like carbamazepine, for example, has a very well-defined Raman spectra, and so we can use a sample of that, like a crystal, carbamazepine crystal. And we can look first to see if we're seeing spontaneous peaks. And if we do see those, then we can check for coherent Raman peaks by seeing if we get a greater intensity, like when adding the Stokes beam in. Because you're gonna get spontaneous peaks with just your probe beam, right? Because spontaneous happens just naturally. But if you see a greater intensity after adding the Stokes, that means that you're seeing this coherent effect. And so that's how you know that there's something going on. And so that's how we would test to see if it actually works or not. Yeah. Well, I will say this is a very conceptual idea. And so I haven't actually done anything in terms of, trying to, locate through rock these biosignatures or anything like that. Hypothetically, you could get a depth of signal that could penetrate through into sediment and try and find these signatures buried under rock. It would have to depend on what kind of objective you're using, like how deep your laser can penetrate into these materials. And so basically, not really sure right now if that's going to be a possibility. But I'm sorry, could you repeat that last question? Yeah, that's a really good point. And that's where this idea of how great can we get this intensity really is important, because if we have a really small amount, we're not going to get a lot of signal from that. And so this coherence effect is actually really important because, and resonance effects as well, which is what Sherlock actually utilizes. That's also very important because, like you said, we have these detection limits that potentially could get in the way of us actually learning anything about what's in there.
Yeah, Chris.
Or sorry, can you repeat the last part of the question? Yeah, I have to say that there are a lot of applications, not only for lunar dust, even on Earth and on Mars, for example. What your question makes me think about is that we have currently this kind of design of the electrodes because we just want to swipe dust from a surface. But by changing that design, what we could actually do with this type of technology is to move the dust, the Martian dust or lunar dust or whatever, from a point to another, which could be related to, yeah, to your question, to move dust or whatever is collected without contact, which is, yeah, very, very good. Thank you. So the potentials are very high, but you don't actually have a current there. So the power that you need is very small. What you really need to power is your high voltage amplifier, and there is where you have the most of the power. But we are not talking about very high numbers. I would say in the range of 10 watts, for example, for sustained activation. So it's not very high numbers. It's very feasible. Thank you.
I have a question before I let you go, Francis. Luca, the design that you showed on the slides had the sort of the thingy thing in a curved shape, which mimics like the outside of a ship or something. But what about if it's a sort of a concave corner shape? Is the dust rejected in a normal direction, or would it reject even if it might intersect with another plane of the surface of the system that you're trying to dedust?
So I've never tested the flexible devices in a concave configuration, but in general, I think that it's going to be much harder to remove the dust. You're probably going to prefer, have you seen that there are two types of electrodes geometries? One is like rectangular and the other one is circular. Probably with the circular one where you have a radial distribution of the dust, you can get better dust removal in sort of concave position. So I don't really know how much your performance is going to be lower, but it's definitely going to be lower, yeah.
Okay, other questions from the audience? Okay, Francis?
Yeah, so it's definitely smaller than like a standard benchtop GCMS. It was made for like military operations, so they could carry it around like on the back of like a Jeep or a truck or something. Yeah, so if I like really tried, I could pick it up and carry it, but it wouldn't be like comfortable, I think. Yeah. Yeah, you probably wouldn't want to carry it anywhere unless you had like I don't know, like a wagon or something. Yeah, I have a grant that provides funds for me to go like to a NASA center every year. And so this year I was at JC. Yeah. It's called NSTGRO. You submit it in November, so check it out.
Thank you. Any last questions? Yeah, go ahead.
Yeah, and I figured I would get a bunch of questions on this. This was like, I was going through deleting stuff, and I had like 4 slides of animations on this, and I was like, I don't think there's time for this. We're getting rid of it. But essentially, it uses that aeroshell technology where essentially the bottom of that aeroshell drops off. So it opens up, the aircraft falls out the bottom, and the top of that aeroshell deploys a parachute. So the bottom falls off, it stays in. It drops, the entire top comes off, and then it just falls thousands of feet while its engines start up. So deploys at a too high altitude, drops a lot while its engines start up, and then it never lands or takes off. It just keeps a consistent glide after that drop and once its engines are up.
Sky, not sky gray.
Thanks for that, Chris. All right, that's about the end of our panel. We have just a few minutes before our first keynote speaker, Dr. Tony G. Chen. If y'all want to take a break, I think that the food is all gone now, but there are still restrooms, and I recommend you take a break, run around real fast. The next talk will be over the course of an hour, and then we will have lunch where you can ask Tony questions at the end of his talk, and then we'll have lunch where you can engage with all the speakers as much as you want. All right. Oh, one more round of applause for this session of speakers. Hey there, hi there, ho there, space folks. We're going to get started with Tony's keynote speech, talk, as soon as the slides get up. All right, this is Dr. Tony G. Chen, currently at Harvard University and coming to Georgia Tech in the fall to work in the mechanical engineering department as an assistant professor? Assistant professor. So please welcome Tony with a round of applause, and then we'll let him take it away.
Hi, can you guys hear me fine? Perfect. So hello, everyone. My name is Tony Chen, and thanks, Abby, for the introduction. And I did my PhD. This is a lot of my PhD work. I've done my PhD at Stanford, and will be starting here as assistant professor in July. I'm happy to be home. Feel extremely honored for this because I grew up in Atlanta. I came here undergrad. So being able to come back here has always been the dream. And secondly, I'm really honored today because our second keynote speaker, Dr. Penny Boston. This day, I'm going to talk about ReachBot, which is one of the robot that we designed during my PhD. And this idea came up in early 2020. And after we came up with this idea of exploring potentially lava tubes, we start talking with people at NASA, and every person that we talked with told us, have you gone talk with Penny? So actually, Penny is one of the first person we reached out to and met on Zoom talking about what potentially ReachBot could look like and what kind of science mission that we can serve. Because speaking from an engineering perspective, with anything of these space robotics, the goal of engineering is always to serve science. What kind of science questions are we actually trying to answer, and how do we build a robot to answer potentially that question to get you samples or get to places that you couldn't go before? So this is what my talk's about today. So before I start talking about ReachBot, I just have one quick slide talking about a little bit like a preamble about what my lab is going to be about. And I want to talk that really quickly to show you how our design approach and how that sort of permeates through this entire project. And yeah, so the question I want, my lab will be focused on this topic called mechanical intelligence. And the first question, of course, is what is mechanical intelligence? In order to answer this question, I'll give a juxtaposed definition. So I swear this is the only wordy slides I have today. So the first, so what is artificial intelligence? This is a big thing right now in all different kind of STEM field. We define artificial intelligence, a broad definition as it's development of a computer systems or robots that are able to perform these functions, perception, controls, autonomy tasks that usually require human intelligence. Then opposing this, what is mechanical intelligence? We define mechanical intelligence as we want to develop new robot platforms and mechanisms that make these challenges for perception, controls, and autonomy easier or more robust to control for natural, unstructured, and often unpredictable environment by the virtue of their physical design. And they're not really just opposed dyads, because mechanical intelligence and all the artificial intelligence research that we've been doing right now works really synergistically well with each other. I'll give an example here. This is not a new concept. I'll give you an example here from thousands of years old. When you have multiple horses or mule that you're trying to plow a field, how do you make sure that each animal is actually pulling the plow sort of evenly? You do not want one animal to do bulk of the work. So it's through this old mechanism called Whipple tree mechanism. You can probably pretty easily tell by the lever definition, just by the degrees of freedom in the system, it just naturally almost guarantees that each animal pulls the load, shares the load fairly evenly. And sure, this is an old example. Not that many fields are tilted right now or carriages pulled by horses, but this exact same principle actually is exactly in your windshield wiper in your cars. And this mechanism you can see right there, that's what distributes the forces evenly across your windshield wiper when you go across. And the fundamental principle stands that load sharing is important for achieving maximum efficiency by distributing this force evenly. So this is just a really quick example, and then I'll go into ReachBot. And so here is a rendered picture, of course, rendered picture of ReachBot. And we'll talk about the challenges that it faces, why we haven't built this in the past 3 years. You can probably guess a lot of the answers, but we'll talk about the challenges later. But I just want to introduce the concept of ReachBot. So I always have this slide in the beginning because this is normally I'm at engineering conferences and I have to spend 5 minutes of my conversation convincing people why do we want to go to caves in the first place. But luckily to this crowd of people, we don't need to do that anymore. So it makes sense that these planetary caves and cliff-like features are of really high interest because they provide really stable conditions due to the insulating and shielding properties. And this shielded environment can also provide potential sites for human habitats. So I can skip over the slides, nice. And a little bit previous work. So what's in the field right now for what currently that's being developed for rock climbing robot? So what you see on the left side of your screen right now is sort of state of the art from JPL. This is actually from JPL called Lemur. And it's this big rigid link robot that can scale. They try to put in the field and they try to scale the cliffs with it. And on the right is a similar architecture. This is done from a group in China, so a similar architecture. But what you see here is what we call in robotics called rigid link robots. And another good example of a rigid link robots is like human, like me or you. I don't know how many of you here go rock climbing. So when we go rock climbing on a rock climbing wall, we're a rigid link robot. By definition, we can only ever reach as far as our body length away. So that provides a really interesting challenge because when you go on these rock climbing wall, I always wish my arm is a little bit longer so I can reach the next hold. And that's with the pre-described route. And what if you go to this natural environment? What if there's no longer a good handhold for the robot to proceed? Then what happens? So that brings to the comparative advantage. So the problem I describe here is these small rigid link robots are limited to small reachable workspace. In order to increase the reach, we just had to mechanically make the robot larger and larger and make the arms larger and larger. And it really scales very poorly with mass and complexity. What if you have a robot that no longer get confined by the length of your robot? Your arm can go multiple length, your body length away. Then you can really try to reach a large workspace. Here it says repurpose extendable booms. I'll show you exactly what that means on the engineering side. And the whole point is that we want to introduce you the ReachBot paradigm. Is a small mobile robot that uses long reach to navigate difficult terrain and interact with the environment. That last part is actually really important because sure, you build you can tell me I build a robot that can go to places, but if it cannot exert forces, it cannot do the science missions, and this is not a good robot for a mission like this. And ReachBot's large reachable workspace ensures more accessible anchor points in this. So I'll talk a little bit about this later when we did field testing. The picture you see over there is a lava tube in the Mojave Desert. And lava tubes on Mars are probably even way larger than this because of the gravity, because of lava formation. And even this, it's really hard for a normal robot or even normal human to climb around. So this is with my collaborator, Stephanie Newdick, and she focuses on the control aspect of ReachBot. So the joke we always likes to tell us that I sort of built her robot and she controls my robot. But she made this awesome GIF about a conceptual mission, cartoonish GIF, but it really showcases the strength of potentially a ReachBot architecture could provide with you. Normally, descending on a lava tube or a skylight of a lava tube is actually cliff-like features, actually extremely difficult situation. You have a rover driving on there, you act like an anchor. Now you have these long reachable arms that you can reach across the cavern or reach across the other side of the cliff. Now that you can actually impose the stability into your system by providing the external constraints. And then you can reach out, you can drill into the surfaces because you can brace yourself against the environment and go in. And I think at the end here, the robot takes a selfie, but. So this is not new. And a lot of my research actually focuses, we get a lot of inspiration. So my teaching here is a lot of bio-inspiration, is that we look at nature and actually see what's available right now. Through millions of years of evolution, nature has solved some of the most challenging problems. Some of the creatures not only survive, but thrive in some of the most challenging environment that robots didn't even dare to go to today. So we can learn so much from bio-inspiration. So, as mammals, as animals, it's sort of similar to a orangutan, and the term here is called brachiating. It's a fancy term, just basically you're doing monkey bars. And that's the biology term for it's called brachiating. But you can sort of see the similarity here, how the body itself, although their arm doesn't extend that far, they're still constrained by rigid link robots. But they can always actually brace itself against the environment that can actually exert a large amount of force. Then you may ask me here, then what's this different than human? Well, we face, in biology, all the different creatures face different constraints from the environment. And because of the scaling law, I know in biology talk a lot about this, the scaling law, because mass scales with L to the third, it just right now, and then based on the limited material that we have through evolution, we just simply cannot support arms that long. But what if you remove gravity? Here is a Japanese spider crab that lives in the ocean. Once you have buoyancy to help you, these things actually grow really, really large and has extremely long limbs once you get rid of the effect of gravity. So 100% that we can see some of the inspiration here, and we're using a lot of the principles that sort of giving you as a motivation of a reachbar architecture. We did not come up with reachbar just from nothing. And there's actually some, even on Earth, there's a lot of biological examples of this happening. So now I'm going to sort of peel back the curtain a little bit, talk a little bit more the technical details of reachbot. And I got rid of a lot of the boring math slides, but I'm more than happy to answer any questions. So my plan is to go for about 40, 45 minutes, and then I'll have lunch too. If there's any questions about more technical details, I'm more than happy to provide, but I just want to peel back the curtain a little bit, tell you what it goes into designing a novel robotic system like this for a really challenging environment, and how can we go forward from just building more, from my perspective, just build cooler robots that can do things that robots can't do before and answer some of the questions for us. So I've been talking about this extendable booms. So what is it? So this enabling technology, here, I'll play the video. I'll play a couple times. This is currently used as a space boom. This is usually mounted, you can see a camera there. This is what they use right now in space for extending a camera out there to take pictures and things like that. The easy way to think about this is it's literally a 3D tape measure. Everyone played with tape measure before. It coils up, it coils flat, but once you extend it, you have a structure. And I'm sure a lot of you, like me, have played with the game where you try to extend the tape measure as long as you can or as high as you can before it buckles. It buckles because it sort of have a flat geometry to it once you expand it. What this thing did was, what if you have a full circle when you expand? So it still collapses completely flat, but as it extends, it comes to a completely tube or with a slot in there. This gives you a lot more rigidity in the system. And this is basically the fundamental technology that allows, what if we use this camera boom right now as a limb for reachbot? And the question I usually get here is like, how far can these things go? And the typical answer, as you may expect, is it depends. It depends on a lot of the parameters that, the thickness of these boom, but also the gravity which we operate in. If we're talking about Martian gravity, we have done some trace studies. If we're talking about Martian gravity, these booms support, of course, it really depends on how heavy your gripper is at the end, because you need to be able to grasp onto the environment. But based on the current architecture on Mars, we can actually extend these things to about 20 to 30 meters without it buckling. Now that you're suddenly talking about reachbot, maybe with a meter by meter by meter cube, but that potentially can reach out to, with two arms opposing to each other, reach out to 30 to 50 meters across. And then that's way more, that's probably more than enough to reach some of the most difficult terrains and span the diameter of a typical lava tube on Mars. And so this is the arm of reachbar. Then what about the hand? How do we grasp onto rough surfaces? This is another bio inspiration slide. And the picture here on the top left is a zoomed in picture of some insects. This is actually a cockroach. And unfortunately for us, the reason why cockroaches are so darn good at climbing everything is because they have these hard hair on their forearm. And what they do is when they climb, when you zoom in, when they climb seemingly smooth surface, like even this drywall right here, if you zoom all the way in, it's actually have a lot of tiny asperities. What this hard hair does, what we call spine, is actually hooks onto these tiny asperities on seemingly smooth surfaces. Then it provides you direction, it's still friction. It still provides you friction in the normal direction a little bit because of the slope of the contact point. And that what gives you, by definition, adhesion meaning normal away from the surface. Based on this principle, we built these microspines. And what you see here is actually exactly what you think it is. They're sewing needles. We buy really sharp sewing needles, and then we sort of use the same thing. I'll go into the gripper a little bit more later, but it's about having this bunch of these needles in this cassette, and then we drag it across the surface. And because it's conformity, because it got springs on the back of these needles, it can conform to surfaces. And we can sort of load it in a way, and then if we have a force closure on the object, then we can get normal force of the system. So this is what's powering, essentially allowing reachbar to be able to climb rough surfaces. Glass wouldn't work because you need a certain, asperity on the level of about 10 to 20 micron for this technology to work. And I have one slide later about what if the surface is extremely smooth, because I know that for lava flows. So I have to say, I've learned so I had no formal training in geology or biology. And everything that I've taught here, this is why I love this community and also love doing robots like this, is because I get to learn so much. And all these things I have learned from a professor, Mathieu Laporte, over he's actual geologist at Stanford. And once I have a question, it's like, what even are there different types of lava flow? What kind of things that we should be doing? I just go to his office, schedule 30-minute meeting with him. It's like drinking from a fire hose and trying to remember as much information as I can. But what happens with lava flow is actually, I know there are two types of lava flow, and oh yeah, there we go. Yeah, thank you. And then what if we encounter smooth obsidian-like glass structures? We'll talk about that later. So my teaching has always been, if we can prove a physical concept work with rubber bands, hot melt glue, and popsicle sticks, for sure we can make it work with CNC machine parts. So I'm really believing in this low fidelity prototyping of proving the fundamental first principle work before proceeding. So this was during COVID, and and then we received a small pot of money from this program called NIAC from NASA Innovative Advanced Concepts, phase 1. And it's a small pot of money, and they're like, okay, this idea is cool, but you need to prove that it works before we start giving you more money. We're like, okay, with the limited funding, what can we do to prove that, to showcase NASA that this concept may actually work? Well, let's build a 2D prototype. I'll play the video, I'll talk through the video. What you see here is basically a platform rolling on 4 ball bearings, ball transfer units. So it's like a 2D microgravity thing. And like I alluded to earlier, we just straight up use tape measure. We put their forearms planar. We just took apart 4 tape measure, put a motor in there, and now each of the arm can go in and out. And each of the shoulder joint has a motor. You can actually do these 2D sweeping motion. And we can start performing some of the most basic functionalities, showcasing some of the basic functionality of the reachbar. Here is a reachbar going stay stationary, extending the gripper, the arm to the end, grips onto the lava rock, and pull itself forward. And it was an interesting time during COVID, try to buy these lava rocks, try to figure out where I can go buy these lava rocks. But And I had to admit, I sort of cheated here. They weren't Martian-like. I spray painted them to look a little bit more Martian-like, but but now you can do some really interesting things. You can have this so this robot is free floating on flat ground. You can anchor itself to the environment. And now you can actually move this really large rock around. You can actually brace yourself against the environment, and you can start manipulating this really heavy object. And then there's one more full sequence video here. So this, again, this was done during COVID. We're trying to do COVID is the worst for anyone who has to run hardware experiments. So you just have to figure out what you can do. Here, you can actually showcase the most basic functionality of once you brace yourself against the environment, what you can do is you can actually also keep tension within the body, and you can do a translating motion. And this is, of course, the most simple one of two. But imagine ReachBot having 6, 7 arms in there. Then you can actually move your body, not only the position of your body, but the orientation of your body around. And we deem this to be extremely important because once you start carrying sense payload or even drills, not only is it's not just enough to get your body to exactly where it is, but you also have to be able to orient the orientation of your body. So here's the full system demonstration of going overhead camera. You have this ReachBot. It identifies the next anchor point, and then it reaches the arm to grasp onto it, and it releases the other anchoring points and pulls itself towards the next gate, what we call gate. Pretty simple. It's easy. This whole thing costs probably less than $500, and the most costly thing is my time, which is $0. Yeah, in this during COVID, but this is one of the first times we said to ourselves, well, this concept might actually work. Before this, there was not a robot that's sort of like this and can do things that it can. And it's all about proving from really low cost, first principle, low fidelity prototyping, does this concept work? And we're able to convince ourselves, most importantly, and also NASA to continue onto this project during a phase 2. And then, but this is a picture of a lava tube. It's 3D, unfortunately, so we had to move from 2D to a 3D prototype. Things get a lot more complicated in modeling, simulation, and actual hardware once you move to 3D. Who knew? So I'll go through some of this is a lot of what my research is about and what I'm really passionate about. But I'll go through on the high level about how do we consider some of these challenges. So the first question is always, when you are designing a gripper, a 3D gripper to be able to grasp onto these rocks, you start with modeling. You start with very simple dynamics and kinematics modeling. If you write out there's no fancy math here. I know it's a lot of variables, but it boils down to just doing a static FBD, a free body diagram on this rock. Once we have a gripper of these dimensions, we're trying to grasp onto a rock. We don't want the gripper to slip. What we can do is that we can form this grasp matrix. It's a 9x9 grasp matrix, and then we can say, what kind of pull force? You can see F pull right there, sort of on the top right. What kind of pull force can we expect on the object? So I have an object right here. It's anchored to the ground. I'm trying to pull on it. So this is essentially the F pull. How hard can we pull on the rock? Basically, that would determine how strong the holds are and how can we design ReachBot. And what we can do is we can put grasp matrix on one side and put pull force angle on the other side. We can solve for these contact forces and the kinematic constraints in the system. And you're like, okay, that's great. Then how does that actually help you designing things? Then based on all the math behind this, what we can do is whenever you design a gripper for a natural environment, unlike in a lab, you cannot control the environment. There's so many variables, such an open-ended question. In terms of mechanical design, that's sort of the hardest problem to solve is when you are faced with overwhelming choices. What kind of rock from all different kind of aspects? Like, what's the rock geometry? We define an angle of alpha here, but coefficient friction, the radius. But what kind of rock and what sort of the geometry you're trying to grasp onto? How about the gripper design parameters? This is some of the things we list. How much internal force are you applying to the gripper? as we probably know from intuition, the harder you grip something, which meaning that you're increasing the internal force, the more secure your grasp actually is. And then what's the maximum force? What's the number of spines, these microspines you're going to put on there? And how about the stiffness? How can you design the compliant mechanisms to this? But what we can do is now with the fundamental model, we can put all these in and we can run Monte Carlo simulation. And it forms this thing, what we call a limit surface. This is a really cool concept. I won't get to too much math here, but I really want to share this. So this is a limit surface is essentially a space in force space, X, Y, Z. It plots, whenever you have a grasp, it plots exactly how much force you can apply to before it fails. And how do you do that? Is you draw your force vector, like F pull here, from the origin. If the vector of force F pull exceeds this limit surface, that means the grasp is going to fail. As long as F pull, the applied force stays within this limit surface, you're going to be okay. And this is really useful concept for Stephanie's work, which I won't get into today, is that how do we use these to predict trajectory planning? And because it's a really risky thing when you have a heavy robot trying to climb, you really want to make sure that the robot does not fall onto the ground. And the other really cool thing about trajectory planning from this is that if you have a vector that exceeds this limit surface, the surface normal of where it pierces through this limit surface is actually the instantaneous velocity of your robot. So you can not only predict how hard you can grasp onto a surface, but you can also grasp if the grasp fails in this way, which way is the robot actually going to slide. So what you can do is you have all these different, from the previous slides, you have all these different vectors. I can vary them now really quickly. Say what happens if I increase the F internal force? What if I design the gripper to be to grasp a little bit harder? How does it affect this limit surface? What if we increase the number of spines? Let's say instead of each finger has 20 spines, what if I have 50 spines? How does it affect the overall limit surface? And this gives us a really quick tool to iterate on different designs of the gripper, saying, okay, but more importantly, for future missions, if reach bound needs to go onto a different environment, the same principle, the same modeling still appears. Now, maybe you don't have to hold 30 newtons anymore, you need to hold 70 newtons. Then we can use the same fundamental principle to predict, okay, in order to achieve that different parameter in a different mission scenario, we need a gripper to be able to do this, to have these different parameters. So this is a really useful tool for us to solve a super under-constrained engineering challenge. So here's the gripper right here. I'll go through each different component really quick. We'll get to the fun part of the field testing. Load sharing, same slide. This is really important because you're going to have, you see the gripper right here, at each end of the gripper, you actually have about 40 microspines each of these cassettes. There's 6 cassettes total. So there's 240 microspines there. These are sewing needles. They bend if they experience probably more than 10 to 12 newtons of shear force. So you really need to be able to distribute the load evenly across them to be able to engage as many of them as they can. So the most important aspect here is load sharing. And here's the cassettes you see, these are microspine tiles we call here. You have a sharp needle and you have a spring there. And without these load sharing, whichever spine finds the first asperity, it's going to take majority of the load and it's going to fail. And the failure is going to cascade and you're going to have a grasp failure. So this is for the microspines. Here's the exact same wiffle tree I showed earlier. It's like now you have 3 fingers. How do you actually balance the force among the three different fingers? This is how you do it with a 2,000-year-old mechanism. Is that you have 3 fingers, you just have 2 bars, simply 2 bars. By where you vary the L in this case, you just ensure, yeah, these 3 almost within like 10 to 20% margin, these 3 fingers, no matter what you do, will experience the same amount of force when you pull on the rock. Purely passive. And you want to have a non-back drivable actuation motor unit. The important thing here is like if you need to grasp the rock really hard, my hand will get tired if I keep holding a grip onto a rock for like more than 30 seconds. And anything to do with space robots, the most challenging thing is always the power source. So if I designed this gripper to be actually non-back drivable, meaning that once you apply enough force to grasp onto the rock, you can just cut the power off. and you'll stay there permanently until you drive it backwards. So this is designed for sort of space mission of energy saving. It's driven by tendon. This whole gripper is powered by one single motor. And just like our human hand, we don't have a bunch of motors in our hand. We have tendons, and of course, we have muscles, but this case, we have a single motor, but you can have a bunch of tendons in your gripper to actually control the opening and closing of your entire gripper. But one thing I didn't really quite touch on earlier is that when you have a long boom like this, like ReachBot, it really affects the mass you mount at the end of the gripper really affects how far you can extend these, which is a fundamental principle of how long you can reach for ReachBot. So you really want to minimize the amount of weight that you have at the end of each of these boom. So instead of having 20 different motors there, let's just put one motor. So it's about this under actuation, about saving weight on how much. This whole entire gripper, I think, weighs about 140 grams. All 3D printed too, which I know for if in the future actual mission happens, it's gonna not be 3D printed, but we were able to do this with all 3D printed parts for about $150 each. Actually, the most expensive part are the sewing needles. So now we have a gripper that can actually grasp onto these rocks. Now I want to talk about other aspects of ReachBots. How do we know where to grasp? So this goes into how do we identify convex surfaces? Because when you have what do I mean by that? If you have a flat surface like this, unless you have some really sticky finger, you're not going to be able to grasp onto the surface. Any convex surface, anything can be modeled with how convex it is, right? The more convex the surface is, the easier it is for the hand to grasp. And then we derive this angle, this thing called local surface angle, alpha, basically telling you how round is your object. And then you based on again, going back to the modeling of the gripper, we can say, well, this work is done by Julia. I have a picture of her on the next slide. It's basically, through the modeling, we realize that there, of course, is sort of trivial, if you think about it, is that there's a big improvement on the pull forces and reliability with increase in local surface angle. So then what Julia did was Julia took that and let's combine it with LiDAR scanning. Then once we take the LiDAR scanning of inside the cave, we can sort of start fitting these hemispheres onto the surface and identify this alpha local angle. And then we can go through some of the perception algorithms that Julia has designed to say, okay, this is a potentially good grasping spot. But if you remember earlier from the Monte Carlo simulation we did, alpha is actually an input to the system. So what we can also go the other way is that, in order to get to that next step, this is the best available grasp location that we can have in the cave. Then what's the alpha? Feed the alpha into the algorithm saying, okay, then we predict with some conservatively that maybe we can only pull about 20 newtons of force instead of 60 newton force. Then that gets fed into the trajectory optimization algorithm that Stephanie had been working on, that worked on, say, okay, then in order to do that, we need to minimize the swinging weight, we need to minimize this, minimize that to get a ReachBot from point A to point B. And surface conformation comes in different length scale. I talked about the large bulk scale, but it can go as little as how do we conform these microspine to micron level scale? To how does a finger go on a surface? How does a whole hand go on the surface? And so it goes all kind of different scales. And so this is what we call a reachability analysis. Through a bunch of field work, we realized that roughly you can classify these natural features into two different types of features. One's a ledge. It's sort of like a stair. And right here, you have a 90-degree drop-off. And the other one, what we call spherical, is you can sort of estimate it as a hemisphere. And one important thing here is that when we design a gripper, we sometimes, as mechanical engineers, I'm speaking on behalf of engineers, we like to build things. And then we're like, oh, we did it this way, but we don't know why we designed this way. It just happened to work. That doesn't make really good research. We need to prove that we're make conscious decisions through our design process. So what we did here is like, how many degrees of freedom? We asked ourselves a question, how many degrees of freedom are needed to reliably conform to these surfaces? So what we did was we came up with a thought experiment. is that you have just treat this as an individual finger. For case 1, it's essentially your finger can only go up and down. And for case 2, what if you add a revolute joint in the middle, and then you add all these different added degrees of freedom to it? What we did, I'll skip to the results, but what you did was with every single added degrees of freedom in the final gripper, we were actually able to reach more surfaces within a given feature. You can sort of see this is a result of it. With each added degrees of freedom, we can actually we break down a LiDAR scan into different phases, and then we can actually reach a lot more. And this served as the justification for our design. So I talked plenty, and then let's show some videos. So here's the gripper in action. It goes really slow because we're only using one tiny, for those of you who run Harvard experiment, a Pololu motor. This motor costs like $5. A tiny Pololu motor, extremely geared up so that it make it non-back drivable. So it is really slow. Luckily for a lot of the space robots, NASA don't particularly care about speed, which we got away with on this one. But so you can see just with one single actuation, we're able to conform this gripper onto a highly irregular surface right there. So once we got close to field testing, well, in order for us to write this paper, we should take partial reach bar. We didn't have enough money to build a full reach bar. We're like, what if we build one gripper, one arm, and mount it onto a tripod? Can we bring it into a sort of analogous environment on Earth to show here, in a real environment, this thing actually works? So again, I booked a 30-minute meeting with Matthew Laporte and went to his office saying, hey, Matthew, where do you think I could go? You know, I was sort of hoping the answer is Hawaii, but I got sent to the Mojave Desert instead. So this is the middle of a Mojave Desert. It's not on the national park side, which makes the testing a lot easier. We don't have to get any permits for it. And it just lava fields. And unfortunately, because of that, there's quite a hike involved. And when you bring a whole robot into the field with all the testing equipment, it becomes a very hard track around. And so this is a cave that we ended up deciding to test on. There's a lot of challenges coming with field robotics. I'm sure a lot of you do field work, so I don't really have to say this. But to me, we've never been really in a cave like this before. I went there like, ooh, this is tough. And not only because it's hard to get to, but also if you don't have a skylight in a cave, it's extremely dark. How can you set up a environment? How can you set up a robot testing ground if everything's dark? So this is actually one of the reasons we picked this one, is because it had a natural skylight, so that we don't have to set up too much lighting. So what we did here is you see ReachBot on a gripper, a single boom mounted on a tripod. I'll let it play. So you identify that target on the ground. It sort of goes up, extend, because it's unfortunately it's under Earth gravity, so we can't reach that far. And these booms, these space booms, are actually extremely expensive. What we used here is a low-cost version of it. It's actually, there's a company that uses similar technology to make it for a boat hook. And because it stores really compactly in your boat, but you can actually extend it pretty far, about 8 feet long, and you can actually hook things in water. So this is what we actually used. It's way overkill. The diameter here is way overkill for what we're using it for, but it was cheap. So you're able to extend, identify the grasping site, go there, and close the gripper. And we're actually able to pull quite a bit of mass on there. It's the last bit of the video. So we're able, during this field testing, we're actually able to show that the gripper actually grasps onto a variety of different surfaces. And we arrange this on the left side. There's hemispheres features from really large hemisphere to very small hemisphere. And on the right side is the ledges from very sharp ledge to very bulky ledge. But the gripper we do not have any sensing in the gripper. All we have is one single $5 motor. And all we're telling it to do is let ReachBot to reach the target and just turn the motor on until it stalls. And that's all it is. But it's able to conform to all these different surface geometries. And of course, at the end, we had to do testing, saying how well is this whole thing working. So we, unfortunately for these microspines, whenever a glass fails, you are essentially grinding these really sharp needles on really rough surfaces and really dose them really hard, really fast, meaning that failure is actually really tough on the system. So destructive testing is, we always say destructive testing to the end, because I'm the one who is sitting in front of the desk, gluing each of the needle in there. Each of this gripper probably takes me about 50 hours to assemble, 50 to 60 hours to assemble. So we did a field testing. We're like, okay, let's bring one lava rock from the field test back to our lab, and then we can just destroy one of these grippers. And you can actually see here on the right-hand side, what you see is our Monte Carlo simulation prediction about how hard we can actually pull on this rock based on the rock geometry. And we have because it's a Monte Carlo simulation, you have mean, you have standard deviation, 1 and 2, and then you have the actual pull data. The thing here is that you can probably tell our model is a little bit conservative. This sort of goes back to the beginning that we want this whole thing to be a little bit conservative, because the consequence of a failure, meaning you have a big robot climbing in a lava tube on Mars, the last thing you want is fall on the ground. So you want your model to be built in a little bit conservative. So this is for the field testing. So reach bar work is still ongoing, although I have left Stanford, but I have 2 really great first-year students. My last year there, I was trying to train them, and they are continuing on with the reach bar work. And the challenge to them during my last year there, I gave them a challenge saying, okay, this reach bar thing is great, but it's huge, and you need to take like 8 different arms. What's the simplest form? If we forego some of the stability of the system, what's the simplest reach bar you can build? Maybe 4. So what they did was they built a 4-armed reach bar. And this is an older video from 3 months ago or something. You can sort of starting to get the idea. A simplified gripper too, but you can start getting how potential reach bars could be in the future. So this ends the last part of reach bar. Take the question at the end, but I have a couple more slides I want to show, because Abby asked me, well, what about your other projects? What about how you went from, I don't usually like talking about, myself, this is all my work, but since there's a lot of students sitting here, like because I'm from Atlanta and I did my undergrad here in the mechanical engineering, it's sort of my journey, how did I get into space robotics? Because I sort of want to talk a little bit about that. So I was a Georgia Tech undergrad here. I went to high school here in Atlanta area as well. For so long, working for NASA or working with anything NASA related has been seems out of reach, right? It seems like this is impossible. Only the smartest people get to work with NASA. And this is something that's way out of the reach. I'm just an undergrad here taking classes. And then my sophomore year, I took I don't know how many of you know the program, the campus Georgia Tech have in France, I think called Georgia Tech Europe now, Georgia Tech Lorraine back then. So I went there, and there was a lot of travel time. Whenever you have travel time, you read books, you go watch movies, and this was back in 2014, and a really big movie came out. We really wanted to watch it. And I have a sort of personal policy. If I'm going to watch a movie adapted by the book, I want to read the book first before I watch the movie. So on the flight to Paris, I read a book called The Martian. And I was so inspired by it. I was like, this sounds so much fun. I filled out my application to go to an internship at NASA Marshall at the Charles de Gaulle Airport. Never knew that I was going to get a call back. And then 3 months later, I got a call back, and I spent summer, I guess 2016, I spent summer of 2016 at NASA Marshall Space and Flight Center in Huntsville, Alabama, in part of the Robotics Academy. And then after that whole entire process, okay, building rockets are cool, but I want to work on robots. What's one place that I get to go work on robots? JPL. So I submitted my application online, and I got a call back saying, do you want to graduate in December and spend the last 9 months, spend the 9 months between undergrad and grad school to come work for JPL? I was like, sure, why not? So I worked on a mission called Asteroid Redirect Mission. So I was working with the Extreme Environment Robotics Group 340. Life turns out funny. My old boss over there turned out to be from the exact same lab that I did my PhD in, so he became a lab alumni, but he's the one who pointed me in this direction. I worked in this mission called Asteroid Redirect Mission. What if we have a robot that we can go capture a large mass in space in situ, and then of course either using as for a gravity tractor for asteroid redirect, or just push it or latch onto a big asteroid and push it away. And guess what technology was used to latch onto these asteroids? Microspines. So it was the exact same fundamental technology right there. So after this, I went to Stanford, and I alluded to in the beginning of the talks that these microspines actually only work well on smooth surfaces. But ReachBot as a platform is sort of gripper agnostic. It's about the architecture of the whole thing. We can swap different type of grippers on there. And another technology that I got a chance to learn and use is called gecko adhesive. And geckos are really interesting because they can actually climb extremely smooth surfaces. And they can climb that they have tiny hair on their feet. It's called setae. And they're tiny hair, and they can get so close to the surface on the order of 10 nanometer. And van der Waals force kicks in and gives you the adhesion between the gecko and the surface. And of course, we can't really build on the precision of a gecko hair right now. But what we can do is we can learn from the fundamental principle of how they climb using van der Waals force. And we build this gecko adhesive. What you see right there is a zoom in picture of it. It's at tiny wedges. Normally, when you touch the surface without any normal force, you have extremely little contact area. But as soon as you apply a shear force, the contact area drastically increases. Because van der Waals force is directly in scale with the contact area, then that's what we call controllable adhesion. So based on the same, so this is actually the loading cycle you can see here. Top is the surface and bottom is the adhesive itself. It just made out of silicon PDMS. And then that's what gives you the adhesion. Based on the same principle, we built this gripper. You can see what's it picking up is a really heavy piece of glass, about 1 kilo. And then you can just control it. Whenever you want it on, it comes on. Whenever you want it off, it goes off. And the application here, the reason why I'm talking about this, the application here is that we were aiming for this for potential space debris capture. Because a lot of the space debris use satellites, solar panels are really smooth surfaces, and use rockets are really smooth surfaces. And the gecko adhesive actually gives you extremely, because it doesn't, unlike suction, it doesn't rely on pressure differential, it doesn't rely on anything else. Van der Waals force still works in free space. And it gives you a really reliable, gentle way of capturing space debris. Sure, there's other methods of it, like casting a net, or I know the space agency, the European Space Agency did a test last year where they used a titanium-tipped harpoon and just pierce through debris and then trying to rail it. But you're in risk of creating more debris. But this is a good way of both cleaning up the debris, but also potentially for in-orbit servicing. If you have old satellite, this is a really reliable way. Just go up there and attach a jetpack. If it run out of fuel or anything, just attach a jetpack with another propulsion unit onto an old satellite and just prolong the life mission of this. So but this same technology can also be used on other smooth surfaces. This is what I'm talking about. So this was my first project. It was really cool. And what's even more cool, I thought I've never had the chance to do it, is we actually built this thing. I'll actually send it to the International Space Station. And on the ISS, we had they have this robot called Astrobee. It's a cubic foot robot. And normally it has a simple gripper that it grabs onto the handrail of inside the International Space Station to stay out of the way for the astronauts. But the handrail was really limited inside the ISS. So they asked us, hey, as a tech demo, are you willing to build a gecko adhesive gripper to replace the gripper we have on Astrobee, so that now it can actually stick onto any smooth surfaces inside of the International Space Station? And that's what we did. We sent it up there. It took a long time. It was during COVID again, unfortunately, and it took a long time, but we're able to put it onto Astrobee. And now the Astrobee with the gecko adhesive gripper is able to attach onto these really smooth, I think this is polished aluminum cabinet door. Oh, and the astronaut helped us, happened to be from Stanford alumni. So she was very excited that we did not send that t-shirt up there, but she already had it. So she was very excited about that. But we can actually see now that you can have arbitrary object actually just stick to seemingly smooth surfaces without any wrap angle. just smooth surface like this with get cohesive. And the last quick video I show is I also do other types of grasping work. This was one of the first things that we did. The first time that we used a drone to catch another drone in mid-flight. In nature, eagles can do it, birds of prey can do it. Why couldn't we do it with drones? So we built grippers that actually catches, we built grippers that, a very simple gripper, 27 grams, no, purely passive. We're actually able to build drones, try to snatch other drones out of mid-air. You can see the propeller there didn't make it. Pretty destructive testing. So yeah, I think, so last slide here. So what's my future lab focus here at Georgia Tech is how do we actually apply this mechanical intelligence into all different kind of areas. We want to build mechanisms that are highly synergistic with modern controls, perception, and machine learning algorithms. And we want to build new robot mobility and manipulation methods to enable robots to do things, to go to places that it hasn't been able to do before, go before, and do things that it haven't been able to do before from a mechanical perspective. And of course, from the bio side, I do some bio-inspired and biomimetic parts. And I do a lot of, the application area, of course, is grasping, manipulation, and also field robotics. I'll say thank you. And then, yeah, I have 6 more minutes, but I'll thank you very much. Yeah, anyways, we'll
Thank you so much. That was incredible to listen to. I will run around with the microphone just to make sure that the questions are heard online. So put your hand up in the air and I'll run to you if you have a question.
Thanks. Hi, great talk. So I had a question about the grippers you used for Astrobee on the ISS. Did you do any testing or did it matter what surface, the material that it was gripping onto?
Yeah, so yeah, that's a really great question. I didn't have too much time going into that, of course. So van der Waals force, the fundamental grasping, what's providing the adhesion is van der Waals force, and van der Waals force falls drastically. I think it's R to the 4th or something with distance between the gripper itself and the surface. And then once you get the gap between the material and the grasping target gets above like 10 to 15 nanometers, it gets drastically, you basically get 0 force out of it. But that doesn't mean that you can only grasp onto things that's like nanometer scale smooth. That's not the case because of all these fundamental principles that we talked about earlier, is like compliance. We can actually design these wedges. The reason why they're wedge shaped, because they only have to locally grasp onto smooth areas. So the bulk area can also be somewhat rough. So get cohesive, of course, the smoother the material, the grasping target is, the better adhesion you get. But we are able to grasp. But nice thing about space is, or free space, is that there's no gravity. So you actually really don't need that much force, adhesion force, to actually stay attached to an object. You only have to worry about the inertia of the object you're grasping onto. But we have done the testing on even powder treated aluminum, and you can still grasp onto that because that's usually what they use on the outside of the rocket body. And then we done the wood, certain type of treated wood on Earth, of course, works well. But the target thing we were talking about, like solar panel, glass, and all kinds of different aluminum, polished aluminum, powder treated aluminum, we can all get quite significant adhesion out of it.
Awesome. I hear this.
I saw you kind of had this bio-inspired design and you were showing the Japanese crab and you were showing the orangutans, and then you are using these telescopic arms, which you hardly ever see in nature for climbing or grasping.
Yep.
Why did you make that initial assumption of let's pursue these telescopic arms instead of like a expandable jointing mechanism?
That's a great question. Thank you. So that's actually absolutely right that there's almost no telescopic biomechanics exists out there. And this is my teaching from my PI. And whenever you ask him this question, the answer he always tells you, the hardest thing in bioinspiration is know when to depart from nature. You learn from nature and know when to depart from nature, because nature have its own limitations that we can surpass with engineering. The hardest material in nature that through all these evolutions pales in comparison against the material hardness of like carbon fiber that we have access to. Another really good example in nature that doesn't exist in nature is actually rotary joints. We have like everything here, like most of the robots are powered by motors. Motors spin. And that rotary joint doesn't exist in nature because through evolution, you can't get blood vessels to the blood inside. You cannot have a rotary joints. But that's some of the fundamental technology that we're using for robotics. So the hardest thing for bio-inspiration, you don't want to turn, if you just follow biology to the T, you end up with biomimetics. You end up with a robot that behave exactly the same as that. There's use for that for biological study. I've done projects like that. But for bio-inspiration, we want to take inspiration from nature on how do they deal with it. Another example there you can see is water striders. They have, or daddy long legs, they have really long arm, and you can actually see that they traverse some crevices by actually expanding its long legs around and to brace itself. So we notice, in nature, these are how these animals deal with these really challenging environments. That's the principle how they do it. They have really long arm, really almost absurdly long compared to their body, the body length itself. And that's how they deal with those challenging environments. And we bring that principle into engineering. By engineering, we can think, now we can have these carbon fiber tubes. We can have these telescopic arms, and we can even amplify this, what we learned from the bio-inspiration even more. So that's sort of how we arrived at the telescopic version of ReachBot.
But why telescopic over something that has a bunch of joints and expanding?
So the reason why is when you have a bunch of joints, each additional joint either needs to be controlled or is movable. It gives you more. Potential point of failure, and also, which means that the mass scales actually pretty poorly, because then you have to figure out how to fold itself together. But for these telescopic things, because it's so mass efficient to store them, and also you don't need the added degree of freedom. Like for a long arm like this, ReachBot is built on the belief that each arm is just purely straight. You can only have a shoulder joint go around, and a telescopic arm is good enough for that. Yeah.
Hey, so speaking of those telescopic tape measure arms, given how things were moving around, I was trying to figure out, and maybe I missed this, is it all about like differential pulling, or can you use these things to push, or is that something that, I don't know, where it's like unspooling, it's like too floppy or something?
Oh, no, that's a great question. I didn't really touch on that. So basically these booms, you can sort of treat them as a cable. You can pull on them as hard as you can. Can you push on them? Yeah, sure. You can push on a little bit, but the degree which you can push on is very limited. You're talking about 1 to 2 newtons before they buckle, because pushing on the thing, that's actually exactly inducing one of the buckling configurations of these long beams. Yeah. I don't know where the mic is. Yeah.
I'm curious what the logistical process will be for determining which surfaces might be like viable for the ReachBot to be able to grab onto without the surface itself crumbling, for example.
Yeah, so that's actually one of the first questions we asked our resident astrogeologist at Stanford. Is like, what if the surface fails? That's actually really good observation, because for microspines to fail, there's 3 different failure modes. One, you're applying too much force, it's sliding on the surface. The second failure mode is the needles bend and the needles themselves fail. And the third type is when the surface actually fail. And the answer that we got from Matthew was that for these lava tubes on Mars, it's unlikely that the surface is going to be crumbly. And so that's what we went with. But that actually brings up a really good question, because for the other project I showed, the asteroid redirect mission, for asteroids, it's actually the exact other side of the problem. It's probably very crumbly. Then what we can do there is that from the mechanical perspective, we can vary the size of these spines. And you saw these sewing needles, they have a tip radius of 10 micron. But what you can do is you can actually increase the size of these spines to give you more contact area to dig deeper if your surface that you were expecting to encounter is actually a little bit more crumbly. So for the asteroid redirect mission, we actually had a gripper with those what called megalodon hooks. Like the hook itself is about the size of my hand, and you can just build a cassette of these microspine with that. And instead of almost grasping onto asperities, you're plowing into the asperity. But there's definitely different engineering strategies you can do if you know sort of what type of surface that you're dealing with, which brings up back to my first point, which is the most important thing is engineering. We are driven by science, that we need to design robots to serve science. And also we are constrained by all of you guys' input on I don't know what kind of environment that we need to be, but this is a part of this, what makes this job so much fun is talking with you guys to learn as much as I can to understand these unique challenges of these different applications that we can put a robot into, and then how do we solve that from the engineering perspective.
Thank you so much for the really fun talk. I learned a lot. So actually related to the last question, I'm curious, well, if the surface doesn't fail, but in general, there's a failure around the robot.
Yep.
And with such long arms, there's potential for it to break so how strong do you have to make the arms? And also, if one arm were to break off, like how do you account for that?
Yeah, that's great. That's a great question. So this really goes into details of Stephanie's research, which I'll try to speak on her behalf. Essentially, this goes back to planning, right? These grasps, with these microspines, because it's depending on the surface, it's depending on so many things, they are inherently stochastic. That's why even from the Monte Carlo simulation there, we can only predict the mean and the standard deviation. And as anyone who had to deal with data, things fall outside of your standard deviation all the time, meaning what if your grasp fails because it just fell outside of your standard deviation of your prediction? Then that gets fed into, because it's stochastic, because we compute a mean and standard deviation, what we can also do is once we know a grasp, a stance, we can calculate the probability of failure. And the trajectory planning of ReachBot can actually take that into consideration. Say, if we want to reach to that particular spot, because of the grasp failure, we have maybe 95% confidence in grasp, but meaning that we have 5% chance of failure, meaning that we actually had to use the other arms to brace ourselves in case of the failure. So the trajectory planning for ReachBot is not just about how to get from point A to point B. It's about every single step of the way. What's the contingency plan? What if anything fails based on the stochasticity of the whole entire system, that you always have a backup option? And that's sort of why ReachBot you saw there, the conceptual picture you saw in the beginning has 8 different arms. And the reason why it's actually not intuitive, a little bit intuitive. So when you have an object in free space, there's 6 degrees of freedom. To constrain it, if each of these arms can only pull, to constrain it, well, the obvious answer is that you need 6 arms for 6 degrees of freedom to constrain yourself. But that's assuming each arm can push and pull. But if you can, but each arm can only pull, that means you have to add 1 more arm to the system to actually fully guarantee the stability of ReachBot. So that goes 7. So why there's 8? Well, you need a free arm to do things. You need a free arm to either do drilling, you need another free arm to actually move to the next location. You always want 7 arm engaged with the surface. So that what gives you the redundancy in the safety, saying, oh, well, if we have a failure, what happens? And I'll go to the second point really quick. The other point of failure, what you mentioned, is what if the arm itself, you have a really long arm, got there, you fail the grasp and you start swinging. So actually, we looked in the literature here, a lot of literature actually in crane operations. When a crane, I'll use this as an example. When you have a crane going forward, moving left and right, this whole thing is really unstable. But there's actually tricks you can do on the motor side. What I'm going to do here is I'm going to move forward. As soon as they start swinging, I'm going to pull back and forth on my hand. You can actually see the difference here. So the same thing can actually be used to control the ReachBot, is that when you detect this dynamic failure, there's things you can do on the actuator side to actually dampen out, to counteract the momentum, to hopefully it doesn't. But if the arm hits the ground, so I mean, there's nothing you can do about that. and you just had to sort of plan for that.
We have time for one more question, and then we'll go to lunch.
Yeah,
And
I'll be here, so.
yeah, there's plenty of time during lunch to talk to Dr. Chen.
First of all, really great talk, really informative. So I had a question about if the ReachBot would be, or like if you're planning to develop it so that you could add more instruments besides just a camera.
Yep.
And if you were, then like, would you keep trying to maximize the efficiency of the ReachBot itself, or would you have to compromise something?
Yep.
Regarding the ReachBot's functionality, or like what would you prioritize if you're trying to add more instruments to it?
So actually, that's a great question, but the answer will come from you guys. So if we have a robot system like this that we can send to the cave, what are the most useful instruments or different modality that we can carry? So we just showed the camera up there, but what we can actually do is like the sort of 2D planar prototype, what we can do is we can brace ReachBot against its environment. We can have a drill on the body. And because we have full control of the position and the orientation of the body itself, we can actually drill into different layers of the rocks as you descend down a cliff and potentially deposit sensors in there to check different things. But this is an active ongoing thing. Is that, yeah, we have this potential architecture that we can use. What kind of things do we want to carry on there? What kind of paper? So a big paper, like a small paper that came out of this was about the trace studies. How much payload can we carry? Potentially, we have 20, 30 kilos of payload. Then what are the most likely payload that we can carry to provide enough science to justify potentially for a mission like this?
Thank you so much again. Let's give Tony another round of applause. All right, now for the moment you have been waiting for, lunch. So they're boxed lunches. We ordered enough for everybody who registered. And if you didn't register, you might be in luck. There might be a couple extras. So if you registered, please go find one of the fellows who will have a list of people who registered, and we can get you a boxed lunch. There are vegetarian options. If you're not vegetarian or not gluten-free, please try to avoid taking those ones, just because there's less of them. Lunch will be until about 12:45. Try to get back in here before Dr. Boston's talk starts at 12:50. Yeah, I think that's about it. Oh, yeah. You can eat in here or outdoors or in the hallway, wherever you feel comfortable.
Where's the fancy? Oh, okay. Oh, no.
I can also, if you
Find the
want
little
to-
thing.
If you want me to be up here, I can advance that for you.
Well, okay, don't leave me.
Okay, yeah.
And what? Can this work?
Yeah.
Oh, yeah,
So as long
okay.
as
Okay.
it wasn't working earlier. Okay. If you put it next to, it'll like disconnect from the PowerPoint. So
Yeah.
as long as you stay on the PowerPoint.
Okay. All right, go for it.
Hello again, everybody. Thank you so much for coming back from lunch. It's always appreciated. So y'all heard Dr. Tony Chen give a talk earlier, and I don't know about y'all, but that was really inspirational to hear about such a cool project that overcomes so many like problems that we have when we're exploring complex systems. And it was also really cool to hear about the trajectory of someone who isn't that far from where we are in his career. So thank you again, Dr. Chen. Next up, we're going to be listening to Dr. Penny Boston. Penny is one of my role models in the field of science. I first met her a couple years ago at a Space Caves conference. And ever since I heard that talk, I've just been like, I want to be Penny. I want to grow up to be Penny. So
Let me tell you the hard parts of life, and you won't want to be me.
I am so thrilled and so grateful that you have been able to come out here and give this talk to us. So without further ado, I will let you take the floor.
Okay, thanks, Abby. It's great to be here. I haven't been to Georgia Tech since before the pandemic. I see you guys are all alive. Is it? Oh. La 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 la. What do you think? Okay, better? Okay. I just don't want to, make it clink around on my chest. Yeah, okay. So the subsurface of Earth is a big deal. And people largely don't know that. And I know Abby's a caver, but most people aren't. And so we are very, very, very enmeshed in the science of the surface. And biologists, not the least of us, because obviously that's the way it developed. And it's what we saw. But in the last 30 years, it's become far clearer that the total biodiversity, the total number of pieces of information in the microbial community in the subsurface of Earth down to, I don't know, 5, maybe 10 kilometers, far exceeds the total biodiversity of Earth if you count it that way. Even in terms of numerosity of individual organisms, it's not just caves, it's the entire rock fracture habitat, both on the continents, on islands, and in the seafloor. So, if we weren't poisoned by the fact that we are thinking about this as surface creatures ourselves, if we were alien astrobiologists, for example, we might go, oh, there's a lot of life there, and most of it is in the subsurface. And even though it's microbial, there are, in some cases, small animal forms. So it's not entirely microbial. Some of the, the notable ones are the amazing weird worms that people have turned up in the South African gold mine studies, 4 or 5 kilometers deep, that they're able to access because of the mining. We don't have the capability in the research community to go that deep. You have to be driven by, the acquisition of some kind of monetary driver. So with that background, back in the late 80s, the Department of Energy, that has had a track record of making some mistakes in terms of pollutants that have been a byproduct of its activities, became worried about contaminating the subsurface water supplies for humans. And so that was really the initial driver for beginning to delve into the subsurface to look at whether or not we could use microorganisms derived from surface environments to actually gobble up nasty compounds. So it was really a very initial practical
practical motivation that drove that. What happened, of course, was when the DOE funded that and people began to do drilling and trying to develop the methods, of studying the subsurface after doping with surface microorganisms. They were taking samples of what they had doped, trying to figure out if, these organisms were actually doing the job of destroying and dispersing the pollutants. They began to discover that, oh, there are indigenous life forms down here. And that was a huge revelation. I mean, when I was a student, even when I was a graduate student, the idea about soils was, oh, you go down about 1 meter and there's no more microbes. Okay, that may be true in an agricultural field, when you get to the subsoil, although it actually isn't true, but they're just, they're below detection for the relatively crude methods at the time. But we began to understand that there was more and more and more and more and more life in the subsurface of Earth. And so I was a student and then a postdoc and then a young scientist early on in my career, and stimulated by that thinking and being someone who'd worked on the issue of life on Mars since I was an undergraduate, as a matter of fact, when it wasn't fashionable. Not sure it's still fashionable, but anyway, it was extremely not fashionable at the time in terms of funding. And so it was kind of a side project. But we put together, thinking about, gee, if Earth has all these subsurface microbial riches that we're just beginning to discover, maybe that's the last best place you would look for life on Mars. Because by then, the Viking missions had already gone in the late 1970s. We already began to really fundamentally understand how tough an environment the surface of Mars was. And so in 1992, we published the first paper suggesting that the deep subsurface of Mars would be the best place to look for life. Well, I was not a caver at the time, other than, going in with my parents at 8 years old and going, ooh, it's cool, into a show cave, right? But there was a National Geographic television program on Lechuguilla Cave, which is in New Mexico. And one of the USGS scientists said that they had done some, scanning electron microscopy work, and they had seen what they thought were microorganisms that looked like they belonged there on some of these cave decorations. So I called them up and I said, because I was at NASA at the time as a postdoc, and I called them up and I said, you don't know us, but we're from NASA and we want to go into your cave. And of course, this was like idiotic because we had no idea that Lechuguilla Cave was one of the hardest caves in the world to do. It's one of the largest caves in North America and getting bigger all the time slowly. And, I'd never done vertical work. I had no idea. I'm like, how hard can this be? And so we threw together an expedition, the first NASA expedition in 1994. And we trained for about 3 hours on the rock climbing area outside of Boulder, Colorado, where I was then located. Because I had done my PhD work at Boulder and at the National Center for Atmospheric Research. And off we went for 8 days in the cave. And we had the crap beaten out of us, I gotta say. I mean, I had, a blob of goo fall in my eye from the ceiling, and I chipped a bone in my ankle, and I was, covered like with pizza-sized bruises. And the whole time I was in there, we just kept thinking, oh, we just have to live long enough to get out of here. And it was because we were completely unprepared. But in the meantime, the other part of my brain that wasn't suffering was actually taking in the gestalt of the environment. And when I got out, in about 4 hours, my eye cleared up and I thought, that's biology. That's not chemistry, that's biology. And I began to remember what I had seen, and that I had seen an environment that was completely different from anything I had experienced. And I was already working in extreme file biology in surface systems. And so I thought, well, I just have to do this and I can learn to do this safely. So that's where that connection came. And I just offer that as a preamble, as to why you would want to do that. Oh, bad. Want to do it here? How's that? Is that better?
Better.
Okay. Yeah, I have a pretty soft voice, so I can't really scream. So let's dive into this. Let's see. How long do I have? It's 1 o'clock now. Okay. I will. Okay. Hello. There. So, poor public understanding of caves doesn't even begin to dig in. Some of these are classics, One of the caving community's biggest jokes is this ongoing series of the Bat Child in caves. They've done this kind of article for the last, I don't know, 30 years. And a lot of us have clippings from that. So, but it's not just the public that doesn't understand caves. Caves have had limited penetration into the scientific community, especially in this country. This is not the case in Europe, where speleology writ large is actually a much more mainstream type of scientific endeavor. So there's a lot of reasons why we in general care about caves. Obviously, a lot of folks just love exploring. They don't have scientific aspirations for it. There's obviously the geology and mineralogy. You get to see, the below the outcrop look, right? So even figuring out geomorphology, because there are windows on the subsurface. The cave biology and microbiology, of course, is what originally attracted me to caves, because it was a methodology of getting into the subsurface that didn't require expensive drilling. That was really the motivation. And all of these other areas, but of course, we come down to astrobiology and making that connection that I just told you about with regards to Mars. We've also done some work, particularly in the early to mid 2000s, in terms of Mars habitats constructed within caves as the free architecture that you have available for you. So that's the laundry list. But what actually is a cave? Well, it depends on who you are. If you're a human, it's really what can we get into, right? It's a hole in the ground that we can actually access. If you're a smaller animal, then you need a much smaller hole. And so the world of caves is much larger if you're the smaller organism you are. And if you're a microorganism, essentially the pore spaces between a lot of granular rocky materials essentially function as caves, because you can hide out in them, right? So it doesn't have to be very deep. You see this all the time in stone outcrops where endoliths grow, so-called endoliths. The total real estate of caves on Earth is really vast. And you would not know that if you were just, a casual observer. But there are probably more than that, 300,000 known caves. And that means known and named and mapped. And there are, many times that have no openings, or very cryptic openings that have not been ever reported. So if you look at the entire cave real estate underground, it's quite spectacular, and it's globally distributed. And it is distributed down to probably a few kilometers. The deepest caves known are a few kilometers, and that's very deep. At some point, of course, even very small cavities are no longer viable because of the overlying lithostatic pressure. So for any given planetary body, there's going to be a lower depth at which you can maintain habitable space. For Earth, it's probably on the 5 to 6, maybe 10, depending on what the nature of the overlying rock mass is. So there's a lot of stuff to look at. So when we first started, writing about extraterrestrial caves, they had never been actually identified. So it was considered a science fiction topic. It's like, well, and most people, do know that a lot of caves on Earth are carbonate. Most of the show caves you go to are carbonate caves, right? And because carbonates, which have since subsequently been detected on Mars, not in large masses, but certainly in small amounts, there was a lot of resistance to the idea. But I didn't let reality deter me, and it was a side project. So, we kept writing about it and exploring the fact that, well, it was pretty clear that there were features on the moon that resembled very closely morphologically the features within which lava tube caves occur on Earth. Oh, thanks. And so, I didn't invent this idea. Ron Greeley, who grew up in the Pacific Northwest as a kid climbing around in lava tubes and having a good time as a caver, became a well-known planetary scientist. And he is third on the author list of that paper, but he was the primary driving force. He was just the junior member and didn't get first authorship, which he probably should have. So, the dawning of understanding that the surface morphology on the moon resembled very closely a lot of similar volcanic terrains on Earth has a long history. We now know, and I give whole talks on this, and I will just do it in one slide here, extraterrestrial caves on many different bodies, and there are many different kinds. And I'm not going to grind through this, but certainly the moon, the actual presence was not really confirmed until I don't know, 2009, I think it was, with a Japanese mission, even though we all suspected. And then in 2007, Glenn Cushing produced a paper about Mars pits with the high-rise images that we were getting out of the high-rise camera. And so all of those began to, make the circumstantial case. If you look at some of the images of Io, you can see lava tube-like structures that are partially collapsed. Those would qualify as, some variety of lava tube cave, even though the lavas on Io are extremely exotic and high in sulfur, probably rather different physical properties. Even some of the massive craters on Mercury have significant holes in them, which look like they have leads. So the subsurface terrain is something that, is not surprising that it occurs in retrospect. Just to wow you with the size, this is, one of the many pit crater types of cave entrances on Mars. You can see the size is enormous. When I give this talk in Europe, I put in a European football field, which is not too much different in size. But, these things are massive. I can't wait to go. But we don't have the technology right at the moment, but, Tony's working on it. I have great faith. And one of the other questions that we have had for a long time that has a little bit of work on it, and that is, what is the potential for ice? And potentially other volatiles, but certainly ice. There's a lot of buzz about that because we're going back to the moon. There's the Horvath et al. Just a couple of years ago did a thermal environment analysis of lunar pits and caves, trying to see whether ices that we know are in the permanently shadowed regions on the moon might also be trapped in caves as a resource. In 2010, there was a great study by Kai Williams looking at a modeling study trying to figure out the same thing for Mars. So we're beginning to see people think analytically about some of these questions. I put this in for you, Abby, because it's Lanzarote. We wrote in 2020, we wrote sort of a state of the art of planetary cave exploration paper. And we've come a long way since the early days when we were just sort of primitively imagining how to find such structures on other planets and what use we might make of them. So a lot of the reasoning in all of astrobiology is one big plausibility argument, right? We have this, that, and the other microbial process here. How can that be applied then to a radically different environment? Same thing with looking at the geology of caves, a field known as speleogenesis. And there are many different kinds. And if you roam around Earth, you can find caves in so many different kinds of rock materials, even including halite. You can see in the lower left corner, these are some of the rock salt caves in the Atacama Desert. And they're very alarming because if you happen to be on rope and the sun is rising or the sun is setting, they're very thermally responsive, and they begin to crack like popcorn. And if you're a caver, the last thing you want to hear is cracking rock, you know. So they're kind of a trip to go into. But yeah, marble, even granite. In granite and orthogranite and related materials, you have a very different kind of cave production. It's not dissolution, and it's not a byproduct of lava flows. It is essentially unlifting and eroding of granite masses that have been buried under huge amounts of overburden. So they're under a huge amount of pressure. And as that overburden erodes away and they get exposed, they begin to undergo elastic decompression. This is one of the most exotic mechanisms ever. And so then they start spalling and they start coming apart like an onion. And on the inside as well. And so you can find all these magnificent caves like in Spain and Portugal that are produced by that. So there are many, many ways of making holes in caves. So what we know about extraterrestrial caves is we certainly now know that there are volcanic caves on a number of bodies. I just showed a picture of that. But if you speculate from first principles, knowing about the properties of rocky materials of all different kinds, including water ice, and then contemplate how to apply that to the radically different physical parameters and chemical parameters of other bodies, you can begin to think of cave forming mechanisms that might occur that we don't have an example of here. And we have developed several papers describing those. I won't go into them deeply. So it's a gemisch of stuff, and there's so many different kinds of caves on Earth, and trying to make sense of this 20 years ago or so came up with a way to really focus on the dominant physics and chemical processes that would be involved. I'm not going to go through the details here, but if you look on the left-hand side, you can see solutional, erosional, tectonic, subvosional, phase transition, and constructional. Right? These are all fundamental ways that you can make holes in some kind of rocky material on some body. And then subsequent to that, we try to match those up with the right-hand column and suggest what kinds of bodies actually might have examples. So trying to work from what we know about the planetary end of things and what we know about speleogenesis and put those together. I will not belabor that any further. So cave environments, it's dark, you know that. And so obviously direct photosynthesis is not something that is going to be a major part of the food chain. Now, in Earth caves, of course, there is a tremendous amount of organic material coming in to some of them. If they have rivers, if they have a lot of groundwater coming in, then that material is brought in. But if you work in desert caves like I do, there's very, very limited amount of organic material coming in because overall it's a very low primary productivity environment. Even in deserts, you get very high humidity because it's the closest thing, a closed environment, is the closest thing to whatever water table you have, even if it's very deep. And water vapor can, come up through the cracks. And so caves, by and large, even those with openings, have very high humidity compared to the changing conditions on the surface. One of the things that benefits you if you're an organism is that one of the benign aspects of caves is that the temperatures are relatively constant. So if you are a creature on the surface, you got to deal with day and night and seasons and all that. If you're hiding in a cave, that's at least one thing that you can not worry about. There are plenty of other things to worry about, like where are you going to get your energy? So typically, a lot of the caves that we're particularly interested in, because they're in desert environments or alpine environments or whatever, they have very low organic nutrients, but they're mineral rich, right? Because they're made out of rock. And depending on the kind of rock, there's more or less buried organic material and a lot of minerals. And so that has pushed a lot of the work that's been done in the direction of chemolithotrophs. There are all different kinds of microorganisms in caves in every different nutritional slot you can imagine. But there's a heavy reliance on chemolithotrophy, particularly the oxidation of iron compounds, manganese compounds, sulfur compounds, a few other weird things. We think some are actually getting some energy out of heavy metal transformations, which amazes me still. So just to highlight the radically different nature of the surface versus the subsurface, this is one of my favorite examples, and this has been pointed out by John and Susie Pint. They live in Mexico. John is British, Susie is Mexican, and they have caved all over the world for many decades. And they've done a lot of work in the Rub al Khali, the empty quarter in the deserts in Saudi Arabia and nearby countries. And if you go into one of these caves, even though the surface looks like what you're seeing here, a highly dynamic, wind-blown, dunal surface desert, you find these diveable pools with unique biology, all the way from the microbes all the way to higher organisms. And this is true even when they have big openings. So if you look at the bottom of the screen there, you see this giant opening. You would think that it would dry out, but it doesn't. So, they are really semi-closed environments even when they have openings. One of the things that I think has been revolutionary in the last 20 years is work done by Bob Hazen at Carnegie in DC. And he and colleagues wrote a major paper looking at biominerals as biosignatures. And this was the first time that it was really pointed out that not only we had this dawning recognition that microorganisms were interacting with minerals and, and transforming them, but that it was a big deal on a planetary scale. And they have continued to work on this idea, but they point out that 12 primitive minerals in the early solar system, that's the basic stuff you got. That's what you see in asteroidal bodies and so forth. We actually now have closer to 4,800, I should update the slide, of known minerals on Earth today. And through their very detailed analysis, they identified 1,500 due to the presence of abundant water and tectonic mixing, right? So those major drivers. But that still leaves a lot of minerals. And Bob and his team attributed those to the chemical and thermodynamic and even physical effects of living organisms on the planet. And that's not just microbial, it's also higher organisms. So that together with knowing that there are all these different types of microbes in the subsurface, you see that it's not surprising that a lot of minerals that are known are only known from caves. And I attribute that to life, as does Bob. So this is my entire career's punchline here on the slide for your convenience. The environments that we've worked in are very varied in terms of temperature and geochemistry and basic lithology and all that stuff. But they have these things in common. So their ecosystem relationships are very similar. Metal oxidation, as I was just mentioning, is really ubiquitous. Even in caves that don't look like they would facilitate that. So, you know, you think a carbonate cave, well, that's carbonate, but there are always more chemically reduced metal materials in the carbonates. So organisms can mine the carbonate for the oxidizable, chemically reduced metal compounds that are there. Biofilms and biomats are everywhere. Some of them look like goo that you associate with a biofilm. Some of them just look like minerals. And it takes a lot of work to uncover the fact that they really are microbial products, intimately microbial products, not just passively attracting minerals to their surface. That happens as well. The illustration that you see here, this is a tiny speleothem, meaning a secondary cave decoration, just carbonate, calcite. The scale of this is maybe 10 centimeters. And you see that the abiotic precipitation of calcite crystals in the drop of water on the bottom. And then you see all the black stuff. And the black stuff is oxidized Mn4 compounds, so highly oxidized manganese compounds. And this is being facilitated by manganese oxidizers that are getting at least part, and in some cases all of their energy from those manganese transformations. The amazing thing about it is the minuscule concentration that is in the waters in this cave. If you just do a standard bulk, water analysis, you cannot find the manganese. You have to concentrate it and concentrate it and concentrate it and concentrate it because there's almost nothing in there. And yet the microorganisms are able to find it, transform it, get the energy out of it, and then precipitate out these minerals. Bernacite in this particular case. Bugs don't live alone. They're very friendly. I think everybody is now pretty much on board with the fact that microorganisms behave one way when they're isolated in a lab that really is only tangentially, in some cases, related to how they behave in nature, because they're in an ensemble. They're in an orchestra of their friends and relatives and unrelated species, but related insofar as they have exchanges of materials and quorum sensing going on. One of my young colleagues in Hawaii is now working on that. What is the role of quorum sensing in microbial communities and caves? Microbial pioneer species play the same kind of role that large pioneer species play on the surface of Earth, and that is they move into a new environment, they alter it, and then there's an ecological succession of other organisms. The same is true in the microbial realm in the cave environment. So there are many pioneer species that actually dissolve their way in to carbonate, for example. And even on lava surfaces. And that liberates materials, and then other people gobble those up. And then, of course, there are a bunch of heterotrophs being bums and hanging around, living off all that, right? So, I mean, it's the entire range of who you would expect. But this ability to invade bedrock is hugely important because it's a major erosional driver in the subsurface. The bugs aren't just there hanging out. Right, they're doing stuff, they're eating stuff, they're pooping stuff, they're transforming things, and they're dissolving rock, right? So the erosion rate of the surface would be much less without them. In the subsurface, there's not a lot of energy to go around. And so they have intrinsically slow growth rates. And if you try in the laboratory to make them grow faster, you just kill them. You know, and by slow, I don't mean, oh, I can do this in a four-month, you know, student project. I'm talking decades, right? So I have organisms that took years to show up and do anything. I have some experiments that have been running for decades. And so that makes them really hard to work with in terms of actually growing. Obviously, now we have so many other different techniques to poke around in their genetic material and their proteomics and all of that. But if you want to actually raise them and give them a happy home, they're really hard customers to do that. Very small cell sizes. So you are too young, perhaps, to most of you to remember this, but back in the you know, late 80s into the 90s, there was this raging debate about how small a cell could be. A lot of what was said was just stuff and nonsense. It was like, oh, well, here's this giant list of things that I know cells do. So therefore, all cells must have to do that. So therefore, they must have this minimum size. I mean, it was kind of a foolish argument. We've kind of gotten over that. But what you see in the caves is they're obligatorily small. Some of them are very, very small, and yet they're functioning as free-living organisms, or at least as free-living as you can be within the milieu of the community you're living in. So maybe not everybody has to have every kind of possible procedure. Maybe they're really almost a type of multicellular life. So a microbial community is a precursor, really, in my mind, to actual multicellularity, because different organisms are providing different services. There's an unusual preponderance of weird shape. I mean, you know, this long-term joke of like, what shape are bacteria? Well, you've got rods, and you've got cocci, and you've got maybe a few squirrels, spirals. Okay, in the subsurface, you've got everything. You've got knobs and bobs, and we have some that we call Smurfs because they look like they have little Smurf hats, and some that we call the Death Stars, and the tiny guys, and some spikes and knobs and stuff. I don't know why. I throw this out there because maybe some of you will want to know why. I have a couple of ideas. One is, well, maybe they're trying to manipulate the physics of the environment. More surface area, and I don't know. And there's no downside because there's so much less in terms of predation, right? You don't have macroscopic grazing organisms slurping you up, right? So you can afford to be Baroque, in your presentation. So I don't know, but it's something that we have seen in caves all over the world. Other people have seen too. I've already mentioned the large biodiversity and the fact that almost nobody that we yank out of a cave is known to science because there's so many. We used to think, oh, we should name some of these. And then when it became hundreds and thousands, it was like, well, no, really, there's no point in it, especially if we can't grow them. One of the good things for astrobiology about this kind of environment is that you get mineral reprecipitation, whatever the basic lithology of the cave is. Microbes are mobilizing that, and then both passively and actively, they're precipitating that on themselves. So in the same way that a coral reef essentially has new ones building on top, right, and the old ones are underneath, you get in situ self-fossilization. So that is a biosignature. If there are biosignatures in caves on Mars, I would imagine that they would be that, whether or not they contain any organic material. So even though we're all in love with chemistry and genomics and all that, I would make the case that chemistry alone is not going to prove the presence of living organisms on another planet. It's going to also be some component of structure and behavior. And structure in the microbial realm is a physical manifestation of behavior, right? in this case of transforming materials and pooping them out as another mineral, that's behavior, and that's what you're seeing. So earth caves as astrobiology models, that was kind of the point of this. The fact that earth caves are semi-closed systems means that you can study them in a way that you can't study surface environments. Because what goes on in the cave stays in the cave for the most part. I mean, there's obviously some coming and going of materials and energy, but it is a much more constrained system than if you're just studying desert plants on the surface. You know, it's a lot easier to think about the micrometeorology, for example, that's going on in a cave, and look at the other variables. You can find a cave somewhere on Earth that probably fits your list of properties. They're filled with all different kinds of gases. There are different degrees of wetness in the system, different temperatures, which are largely controlled by what you might expect, which is, you know, the average ground temperature within which the cave is housed. So this is why they've been, for us, very useful planetary analogs. So the extreme conditions here may be average on other planetary bodies, right? In terms of, you know, they're extraordinary here on modern Earth, but not necessarily on Enceladus, for example. So what's the kind of life we might imagine for an extraterrestrial cave? I do a lot of my thinking by just drawing and, you know, imagining a chemolithotrophic type of organism that actually was maybe as much mineral as it is biological. This is something we only rarely see here, but we see circumstances in which we think that's what we're seeing. Very hard to study. But let me just, I haven't put a lot of data into this. If you want that, you can read papers, but just to give you, you know, a visual impression of these organisms working in nature. You can see on the lower left, these are fluorescent stains in, you know, rock cores that we've taken out. You can see these incredibly tiny cell heads. And I hope you can see there are very thin filamentous processes coming out of there. Many organisms that are really low in nitrogen have that response. They put out very long processes. So they're trying to seek nutrients. And they're doing that in the bedrock. And these are the guys that are softening it up. For a lot of the guys on the right-hand side, like the Pedomicrobium genus and a lot of its relatives, we find a lot of those in caves working on the manganese. And they work on different types of manganese minerals and oxidize them to other minerals. And they do that in relatively rapid sequence compared to what the standard model is, abiotic model is for how minerals go from one phase to another. A few more pretty pictures. You can bring some of these guys into the lab. I'm pretty good at growing things that don't want to grow because I have a lot of patience and I speak to them sweetly and so forth. But these are some of the examples you can see on the left. These are all reproducing mineral crystals that we have seen in nature where the organisms came from, actually reproducing it in culture. And to me, that's the gold standard for the kind of work I do. I love my colleagues who do all the genomic end of things because that enriches, but my goal personally is to grow them. I view myself as a micro zookeeper, you know, because I want to grow them because I want to see if they can make the same minerals in real time that I think they're making in the cave. And that's really the only way to close that logical gap. Let's see, it's the lower right, okay. Trouble with left and right. So the little tiny spectra on the right shows the appearance after 3 months and 8 months in a culture from amorphous manganese and the transformation of that amorphous manganese into a sequence of increasingly crystalline manganese minerals. If you kill them, if you flood the plate with something awful, that does not continue. So not only do they transform the oxidation state of the manganese, their presence actually catalyzes the production of the mineralogical crystal forms. So that was something we weren't expecting. We were thinking, oh, they transform the basic chemistry and then their job is done. But apparently they're inherently important in the crystallization of these minerals. Mineralogists don't like that because it kind of messes up the classic scheme. So just to dazzle you with a little bit of eye candy, these are examples from a lot of the caves that we worked in. One of the lovely things about this microbial mineral interaction is from the point of view of looking for biosignatures, either on Earth or elsewhere, even though they're individually itty bitty guys, they make these very large, really clear mineral deposits. Some of these are gooey, some of these are stiff, some of these are fluffy, some of these are slimy, like the snotites in the upper left image. I draw your attention to the lower left image of that dark thing. That's actually a manganese microbe stalagmite on a miner's jacket. And this is in the Sudan mine in Minnesota. And we know exactly when this started because they closed the mine in March of 1962. And the miners said, to hell with this. And they threw all their gear down and left. And so everything that has grown as a microbial mineral deposit since then, we have a starting date. This is rare. So that, beautiful black core, it's actively still forming. You can easily recover the microbes from it. If you look at a cross section through it, you can see it's a lacy lattice of mineral with the microorganisms, growing in it. I could go on and on, but I won't because we're running out of time. The beautiful blue copper speleothems that we found, big patches in Italy, Sardinia, Hawaii, just recently actually found some in New Mexico, which surprised me because it's pretty dry. More acute forms. So I was talking about the weird shapes, those beautiful little stars in the center. If you actually slice and dice those and stain them, you can see that there's a whole pile of DNA on the center. So the center of each star is like a critter, and it's facilitating the growth of these crystals. So it's very magical. And then there's some that I don't understand at all, like the one on the very bottom. We call these the bird's nests. And they literally look like this, and they occur in a type of material called moon milk. And moon milk is this weird, gooey, white stuff that's a breakdown product of carbonate. It was named Mondmilch in German because somehow they had a theory about moonlight coming in and making this or something. I don't know. But anyway, it's the bugs. It's not the moon. And we find these little bird's nest things with a few cells on the inside. Who knows what that is? They're not fungi. You might say, gee, they must be fungi because they're complicated, but they're not. They're actually bacteria. Very often you can see dazzling arrays in lava tubes, so you can't see the sparkle, but trust me, everything that you're looking at here is silver, sparkly gold, sparkly orange, sparkly pink. And this is because these are dominated by actinobacteria. And actinobacteria have a complex life cycle, and part of the time they're hydrophobic. So the fluid in the cave condenses on them. And so that's why you go in and you see this glittering array. It's like being in fairyland. Biopatterning. This is one of the areas where we thought originally when we started to find biopatterns like this, like hieroglyphic patterns in caves, we thought that it must be because we were in a sulfuric acid dominated cave. So it's Cueva de Villaluz in Mexico. But then we began to see them other places and began to realize that it was not a chemical phenomenon of some sort, that it is essentially the interaction of microorganisms' intrinsic growth geometries fluid flow in the environment, precipitation of minerals, and trapping of particles. And when you put all that together, which we have done in several different models, mathematical models based on cellular automata, we can reproduce these patterns. So this is an ecological strategy that allows them to slow fluid flow and the flow of nutrients through the system so they can grab it. So that's the ecological consequence of physical and chemical processes that are going on. I love these things. And this is my entry in the agnostic biosignature sweepstakes. We'll see. If I could live another few hundred years, I might be able to test that, but I'll have to leave it to you guys. Let's see, I've got another, 10 minutes, right? Okay. So why are they there? When I first was going into caves, I was expecting an extremely depauperate biodiversity. My thinking was, naively at the time, oh gee, it's tough and it's miserable in there, so only a handful of guys are going to be able to tolerate it. And we found just the opposite. We found just the opposite. And after being surprised by that and thinking about it over a number of years, my suggestion is that really the surface of Earth behaves differently than the subsurface in one significant way, and that is that the subsurface actually is chopped up by physical barriers. So you probably have heard the old idea that, oh, everything is everywhere and the environment selects. That might be true for the surface because we have wind and water and patterns, animals walking around and dropping bugs and stuff. But in the subsurface, that's not true. You have impervious rock layers and you have fluid aquifers that may or may not be connected to anything else. So you've got evolutionary islands in the subsurface in a way that you do not have on the surface. And so that at least makes me satisfied for the moment as an explanation for why the biodiversity is very high. One of my other crazy ideas that I'm absolutely sure I'm right about is that the subterranean microbial biosphere has persisted for a very, very long period of time from very early on in Earth's history. And I suspect and I won't show it here, but when we look at patterns of relatedness of organisms that we have isolated from caves, where their closest relatives might be in another cave, on another continent, or might be in a sulfur system in the deep ocean, that actually there's a microbial load that gets dragged around with the supercontinental cycle of Earth. Their bugs are in there, they get dragged around, some proportion of them survive geological destruction, and then bam, they pop up again, and then re-evolve. Okay, I don't know how to prove that other than by living a really long time and seeing other people do a lot of the work, but I'm absolutely sure that this is true. And I actually think that, the more we know about the ability of microorganisms to endure ridiculously difficult conditions that you would think would kill them, even in synergy, that some of them are probably tough enough to survive burial and diagenesis, right? Not all, but enough so that when later you get another geological condition happening, we get uplift and erosion, there they are, and they can reemerge and re-evolve. So I think that the crust of Earth, including the oceans, are a geogenetic bank, a time dimensioned geogenetic bank. I want to just finish up here. I have a zillion slides. I thought I'll go as far as I can get and just show you this, because this is something we've been working on for 15 years, and it's very difficult because we can no longer get access to these mines. These mines became very famous because we did 2 different National Geographic expeditions into them, and they were made into TV specials and stuff, and they're visually spectacular. It's an amazing place. You see that we're wearing orange suits, and it looks like we're trying to keep warm, but we're actually packed in ice, and we're trying to keep cool, because this is a geothermal setting, very, very hot, 140 degrees Fahrenheit. So everybody is there with ice pack breathing gear and so forth. The reason I went in, besides it's cool and they invited me, was because old friend Paolo Forte from the University of Bologna in Italy is one of the world's great cave mineralogists. And he sent me some electromicrographs saying, I think there's bugs in these crystals. What do you think? And I'm like, yes, I think you're right. And I will go and we'll look. And sure enough, there are. So some of the geological work that's been done on these shows that the crystals are about 500,000 years old. That's not terribly old as systems go, but this is a very dynamic system. There is a big ore body there, which is why there are mines there, because it's commodity metals like zinc, lead, et cetera, a little bit of silver. So these have been delved into for mining, and that's when they discovered these gigantic crystals. They drained the chambers in which these crystals occur, because they're dewatering the mine so that they can actually do the mining. And that allowed, some of us to get in and actually study these things. We were able to drill down with sterile equipment, which is really difficult, based on the age of the crystal, and then normalizing that to how far we could drill down in. We figured that the fluid inclusions that we were able to sample are on the 10 to 50,000 year old time scale. And we recovered quite a bit of DNA and sequenced that. I won't show those results because it's complicated and you guys know what that stuff looks like anyway, for the most part. But at least 40 strains, and there were 40 weird strains. And I have isolated 60 live cultures. Now I've lost some of them over the years because keeping organisms in culture is really difficult. But I still have some, if anybody's interested. Subtle and Chan and Wingate from UBC were there. Curtis Subtle and his team, and they found a huge virome. So that says to me that these are indigenous organisms with that presence of those viral components. And so it's been there undoubtedly since the magma body in which the ores are contained actually began to rise up. So this is what you can do on Earth. This is the only data I'm going to show. This is from different sites within that cave. And you can see I've just given qualitative names to these things. You can see that a lot of them are related to thermally tolerant organisms in many different places, from New Zealand to Hawaii, Kamchatka, et cetera. Chemical weirdness of one sort or another, iron oxidation, pyrite degradation, something like that. There's a whole suite of those in there. Some that are related to soils from other places in the world. And then a few in yellow that are, from caves way far away. So Altamira Cave is in Spain, Frisassi is in Italy, the Nullarbor Plains Caves, very famous in Australia, and these are the closest relatives. So this is part of my possible evidence that these guys are related deeply in geological time and get dragged around the planet over time. So let me end there and take any questions with any remaining time. Thank you.
Thank you so much. That was awesome. Because I miscommunicated, we can ask questions during the break time, but if you have to get up and go, it won't be rude. So, yeah. With that, who has some questions? Oh my gosh.
Hi, super cool talk. Loved all the photos. I was just curious about what sort of generation times you're seeing in these caves, and then also how long it takes things to grow in the lab.
Way longer than anybody has, Well, I can bring some things up quickly. And I think it's, where are they in the food chain? So you know, the heterotrophs do better. I can bring them up. I mean, they're still slow compared to stuff you scrape off your teeth, right? So, but you know, weeks to the chemolithotrophs can be years. And I've had to, you know, develop methods of growing them. You know, you can't just do this on an ordinary Petri plate because it dries up, you know, and dies, right? So, you know, I've tried them in liquid culture. I've tried them in liquid culture, you know, on rock surfaces and just about every way of husbanding them. So it takes a long time. Even the heterotrophs are a little tricky. You can't just, you know, slap a bunch of nutrient broth in there and hope, because you'll just kill them. They can't stand the oxidative stress of that much nutrient. Yeah, so pretty slow guys. That's why they're special. Exospecial.
Thank you so much for this talk. I had a question about the chemolithotropic.
Can't hear you, darling.
Oh, I'm sorry. I had a question about the chemolithotropic organisms. So I'm curious of how specific they are to a certain mineral, or can you like grow them on a different mineral and they adapt?
Yeah, it's all over the map. So there are some generalists. Pedomicrobium manganicum, which we didn't discover, that was, you know, pretty widely known. That guy is a food slut. I don't know what to tell you. I mean, it'll eat anything. It will oxidize a wide variety of metals. Some of them, I have to do weird things like I have to grow Klebsiella in a medium and then filter stuff out, and I don't know what I'm filtering out, and put a little of that in before I can get them to grow. Okay, so there are growth factors that you know, are probably necessary. So some of them are really fussy. Sometimes I've tried to use you know, powdered chemical iron compounds and failed, but when I put a rusty nail in there at the bottom of the culture and let it diffuse, you know, through the solid medium or even through stratified liquid medium, they grow. So, you know, there's the weeds always, and they'll grow on a lot of things and can handle lots of different metals. And then there's the ones that are really fussy. So there's something for everybody.
I was just curious if you see like cross-contamination of microbes between caves is a risk, and for those of us that go into caves for field work or exploration or recreation.
Yeah, I mean,
doing
we are very careful, but cavers are not careful. So caves that are accessed by human cavers, you know, on a regular basis, there's probably lots of toing and froing. Caves that are accessed by bat colonies, there's a lot of transport mechanisms there. But, you know, if you're in the depths of Lechuguilla or something like that, no. We did in the, I don't know, probably about 2002 through 6, we did studies of human-associated organisms in Lechuguilla for you know, the cave management of the national park. And the contamination was amazingly minimal, and I think it was a testament to the fact that of the management, they have bivouac areas. The cave is too big to just go in and come out, right? So you're in for days, and there's a whole set of protocols to try to minimize your impact. Nevertheless, you are shedding. You know, you're urinating, you're pooping, and all of that has to come out with you. So even if you're being incredibly careful, you're still, you know, shedding effluvia. And so what it showed was that localized high impact areas was protecting the overall cave, which is important for planetary protection as applied to Mars, for example. Yeah.
Hello, amazing talk. My question is, since there are some very weird, extreme types of morphologies found in these cave systems, have you found or encountered any that were very influential in your decisions making into in your cultivation methods? And what were they, and what were the weirdest ones?
Yeah, I didn't get to one of the slides where I was going to show. Guess we've got a moment here.
While Penny pulls that up, just a reminder, we don't have a break before the next session. We're doing questions and break at the same time. So
these
just a reminder.
guys, these are one of my big mysteries. If I weren't running out of time, I would have told you about them. Now I'll tell you about them. We call them microchoyas. So those of you who are familiar with choya cacti and what it looks like when it rots away, it has this beautiful mesh stocking like, skeleton. We find these in the subsurface all over the place. Germany, Australia, Russia, Japan, everywhere, Mexico, Chile. They're only in the subsurface and we don't know who they are. They're not fungi. And if you just do, a blast at all the DNA environmentally, you don't know who's who. Are they the remnants of a filamentous type of something? I don't know, because when you do EDS on them and look at the elemental composition, they simply are coated with whatever they're growing near. So if it's in a copper environment, like some of those the blue goo I showed you, you get a copper and carbon, but we don't know who they are. And I've tried filtering them out, but it's hard to find them. There is a cave in Germany that I've got on my sites. And as soon as I get my knee replacement and heal from that, I want to go there and try to see if I can get some live ones. A lot of the ones that we find are not live. They're stiff and they're fossilized. But there are live ones in these muds in this one particular cave in Germany. So I'll let you know.
Other questions right now? I have one if nobody else does, but I'll prioritize the audience. Okay. I was wondering, as you're looking at these leftover biominerals, potential biosignatures on other planets, they seem to have lots of weird shapes, but they're weird from what is an abiotic process, because we know what abiotic processes on Earth kind of look like, and then we know that these are not that. So what about when you're looking at another system that has really distinct abiotic processes from what we see on Earth? How do you think we're going to be able to differentiate between the abiotic and biotic processes in biominerals there?
It's going to be challenging. I think what helps us is the more you see on Earth, the more you realize what you don't know, and the more you allow your perception to range more freely. If you only study one thing, you go, oh, everything is nail, right? And when you look at many, many different kinds of environments, many, many different kinds of organisms, many, many different kinds of deposits, I think you get a feel for it. And I think that's probably trainable for, machine learning systems with high fidelity, optical perception systems and so forth. So certainly AI is creeping into everything, including stupid stuff, but we're trying to use it in astrobiology. In fact, we have a big initiative in NASA now to actually, try to use this because we're just humans with like binary brains and it takes a while for a field scientist or a lab scientist to be trained and get a feel for what they're doing, which is part of the joy of it all. But we can't go to every destination, as humans. So we need help from our little computer buddies. Yeah. Thanks, guys.
Right, one more round of applause for Dr. Boston. All right, and if that clock is correct, we do have about 2 minutes before our next talk. So take a breather, relax, make a loud noise or something if you're antsy from being quiet for an hour.
Go out in the hall and scream. Okay, cool. That's funny. Oh, I've got to get this off me. Let's see, where's that? There it is.
Alrighty, I'm gonna bring you all back. The last session of the day is on planetary analogs. We'll have a group of folks talking about lots of different planetary analog vibes. And to start it off is Christina Buffo from the Orlando lab in the School of Chemistry and Biochemistry. And they're going to be talking about mice and dust.
All right, yeah, so thank you everybody, and thank you to the fellows for organizing this. So today I'm going to be talking about some laboratory experiments that I've been doing of water, ice, and mineral dust mixtures, looking at those with two important infrared bands. And this is work that I've been doing here at Georgia Tech with primarily the Orlando lab, and then also a lot of other people as I realize I have to care about rocks. So whenever we're talking about ice, which is something that I personally am very interested in, we're never really talking about pure anything. As we've heard from some of the talks earlier today, including the talk we just had, minerals are messy and you're going to have a lot of things involved. I'm not looking at anything related to life. I'm just even looking at mineral and water interactions, but you're still going to get quite a lot of interactions. And this can range in terms of composition. So lunar water, even in permanently shadowed regions, can be more than 90% mineral with only trace amounts of water, and that's in the highest concentrations of water on the moon. On the complete opposite end of things, plume-type cryovolcanism, like we'd see on Enceladus, has mostly water particles with a little bit of mineral. But the Cassini mission flew through and looked at some of those particles, and there were some minerals in there. So these very different environments can have different formation mechanisms, and that means also different morphologies. So then when we're trying to imitate these particular properties in the lab, you can really range in terms of how much interaction you get between components. So the diagram over on the right shows two of many possible interactions. On the far right, you see not much interaction between water and minerals. They're mostly separate. And then on the bottom, it's much more intermittently mixed. So I'm going to be talking about mixtures that have a lot of interaction. So the ices that I make, I'm forming through liquid aerosol injection. So I make a mixture, I put rock dust in a solution and pour water in and swirl it around a bit. And then I put that into a syringe and inject it into a vacuum chamber. So the whole diagram is over on the right. I won't go through all the aspects because they're very frustrating and boring. But the important part here is that I'm injecting the solution into the vacuum chamber. It drops quite a lot in terms of pressure, and it also drops in temperature. When the solution hits the frozen sample holder, the sample holder is sitting at about 91 Kelvin, and our best estimate for cooling rates is about 1 × 10⁷ Kelvin per second. So very fast flash freezing. And this sort of very rapid flash freezing will probably only happen in some environments in space. In particular, post-impact freezing on the moon, so large things like comets, or potentially also micrometeorites hitting ice that's already present on the moon and causing it to rapidly heat and then freeze again. This may also happen in plume-type cryovolcanism, but I am less sure of that, and I think all of us in general are slightly less sure of what the temperature constraints are on that. So in terms of detectability, I'm using 2 infrared absorbance measurements, and I'm looking at the 6 micron HOH bend. So that's like if my head is the oxygen and my hands are the hydrogens, it's this motion. The best part of being a chemist is you get to do the fun little dances. So that sort of motion is specific to water because you have to have the 2 hydrogens moving separately. But the 6 micron band isn't absorbing quite as much infrared light as at the 3 micron band, which is just the OH stretch. So again, if my head is the oxygen and my hand's the hydrogen, that's this sort of motion. And you can get that with other things that have hydroxyl groups, like some organic molecules and also like hydrated minerals. So I'm looking at those 2. As for the minerals that we picked represent a range of compositions. So I'm using 2 commercial simulants, lunar hyaline simulant and lunar Mare simulant, and then some single minerals that were picked because they're components of those lunar mixtures. So I have anarthosite, iron-rich ensitite, iron silicate, and olivine. If you're not a rock person, and I am also not a rock person, the important thing to know about these is that it's a lot of silicates with a bunch of other things around them in various structures. And the relative importance of that is an open question. So, and then in terms of preparing the solutions, those are all, again, made by mass to compare with estimates based on mass for the moon and such. So I have 5 and 10 weight% mineral, the rest water for everything, and then higher loadings of 25 and 50 weight% for the 2 lunar simulants. So let's talk about small mineral weight%. And I'm going to go a lot more in depth into this graph, but just starting from an overview, the wavelength and wave number, so energy axis is going to be on the x-axis, and then normalized absorbance on the y-axis. All the spectra I'm showing here have the 3 micron band set to 1. So everything is relative to that size. To break this down, so first, this is what it looks like if we just have water injected. No minerals, nothing at all. We end up with this sort of broad feature at 3 microns and a very amorphous structure, so amorphous solid water. If we form crystalline ice at higher temperatures through a more constrained methodology, we get something that's at lower energies, so closer to 3.1 microns, and also a different shape. And then with these 2 just water examples for comparison, then we can start looking at the minerals. So this is a solution of 5 weight% LHS1D. And if you're noticing it's kind of hard to tell where that is, that's because it looks very, very similar to the mineral-free water injected at the same temperature. Interestingly, though, anorthosite, which is one of the other single minerals, looks different. And LHS1D is mostly anorthosite by weight, and I'll talk more about that in a bit. So it was really interesting that the band is a little bit wider, especially at the higher energy range, closer to 2.8 microns. So to try to understand what is going on in here and why they might look different, we looked at breaking this down into 2 different parts. So we have water molecules absorbing at lower energies, closer to 3.1 micron, and that's the tetrahedral waters labeled in purple. And in the diagram over on the right, you can see those molecules are very nice, very regular. They're all bonded in this nice crystal structure, very specific distances, specific bonding environments. That's usually very energetically stable. In contrast, the undercoordinated water molecules in green are absorbing at higher energies because they're kind of messier. In the diagram on the right, they're kind of pointed all over the place, and the bonds and the distance between them aren't quite as regular. So we can also look at the 6 micron band, that's the HOH stretch, and with very constrained geometry and the very regular crystal structure, you don't get a lot of that bending motion. So you can see at the bottom that tetrahedral, it's not a very large structure because they're just not bending. In contrast, the uncoordinated water molecules are farther up at the top. They absorb a lot more because they're able to bend. And then the 2 mineral containing solutions are somewhere in between. You get some motion, but not quite as much as just water. So then when we put these 2 features together, we can say that there's more bonding environments present when you have a mineral than when you just have water. So the anorthosite band in red over on the left is slightly wider in range, and it also has a larger HOH bend over on the right. In contrast, LHS1D looks very similar to just water at 91 Kelvin and in the 3 micron band, but it's absorbing less bending motion in the 6 micron band. So we don't really know why, and this is starting to get into why anorthosite versus LHS1D. As mixed, it's mostly anorthosite, but there's a bunch of other components, and it's one of those compositions. When we were looking at this, originally we were hoping it was just differences in iron content because iron has been shown to increase or decrease amount of crystallization. But based on XRF and XRD results, it's probably not that. And when I looked at that, I was like, oh man, I gotta know things about rocks now. So I had to talk to a lot of rocks people who know things about rocks because I don't. And the best ideas we could come up with, it might be crystallinity, some sort of lattice matching using the rock as a template. Could also relate to surface hydrophobicity or acidity. These are things that people tend to think about in much more catalytic sort of environments. So I don't have time to talk too much about large mineral weight percents, but the short version of this is adding more minerals can sometimes make things look more crystalline, which is weird, and I don't really understand that yet. So in conclusion, adding some amount and composition of trace minerals will really strongly influence the ice structure, mostly in terms of the shape of the OH stretch and the size of the HOH bend. And these large mineral weight percent solutions can look pretty crystalline. So I did all this work with the Orlando lab, funded here by the Clever program. And if you're interested in talking more about ice, I'd be happy to take your questions later. Thank you.
Thank you so much, Christina. All of these talks have been really cool. I feel like I'm being cheap when I say that was such a cool talk, but they're all really cool. This one was particularly cool. You might even say ice cold. All right, up next we have Tatiana Gibson from the EAS department talking about using rover type instruments at a planetary analog in California.
All right, hi, I'm Tatiana, and this is my first time getting to present about this fieldwork that I got to do last year with Sharissa Thompson, who you'll get to hear about in a few talks as well. This is the result of me wanting to go to a field site and test out what alluvial fan deposits look like when we use rover type instruments, and I'll define these terms for you in a second. If I can get the click thing to happen. There we go. All right, so I just use this term alluvial fan, and I'm tying it to Mars and using an alluvial fan as a Mars analog site. So what an alluvial fan is ultimately a feature that we observe on Earth and Mars, and these are features that are the results of water flows on the surface. So everything that we talk about on Mars often has some sort of tie to water because we're interested in water and its influence on habitability in the past. So I wanted to come and visit an alluvial fan site on Earth to compare some of these things. So on the left, what you're seeing is an image of an alluvial fan. It's a little bit faint because this is a black and white image from satellite imagery. I believe that's the CTX camera, but this is the Peace Vallis fan, which is in Gale Crater, and that's where the Curiosity rover has been for well over a decade at this point. And this is a feature that looks like it was deposited by water in the past. So of course, we send a rover to Gale Crater to look at Mount Sharp, which is the center of Gale Crater, and there's also this alluvial fan here to study, and the rover has been roving along by the base of that, especially at the early beginning of its mission. And one of the beautiful first images that it took is the one that you see in the middle there, which is a fluvial conglomerate, or a rock that was deposited by water. And it looks a lot like rocks that we see that have been influenced by water on the surface, and particularly river flows. So we see an image of some gravels in the Atacama Desert on Earth in an alluvial fan setting, and we can see that there's some real parallels between the two because we see these rounded gravels. And that's really the key observation here, is that they're round and they're the size of what you might expect to see transported by water. So roundness is really my focus here. Here's a really pretty picture of some just classic round gravels. This is from the Colorado River on the Colorado-Arizona border. Really, really round gravels, like the roundest I've ever seen. And it's really a primary characteristic that we can use to say, oh, that looks like something that's been transported and rounded by a river. But an important thing to keep in mind here is that even though we use roundness as this parameter to think about past fluvial transport, roundness is influenced by more than just something being transported by a river. It can also be affected by the type of rock that's being transported in the first place. So that graph that you see on the right is the rounding rates over distances for all different sorts of rock types. So you can see that all those lines start and end at different places, and these represent the influence of rock type on how round a pebble can get when it's been transported by a river. And that influences what we might be able to interpret from just looking at a gravel, whether it's on Earth or on Mars. So I've got really interested in answering this question of understanding the influences of composition, which is to say the type of rock that we're looking at, that a pebble is made out of, and transport distance, so how far it's been transported by a river, and how those two factors influence how round a fluvial gravel can get. And a fluvial gravel is just anything transported by a river. And I wanted to measure it with rover type instruments. So on the left, we have a schematic of Curiosity, and I'm highlighting two different instruments on it. ChemCam LIBS. LIBS is laser-induced breakdown spectroscopy, and it's one of the tools that's on the rover that can tell us about the chemical makeup of rocks. So we have a laser, zaps a rock, tells us some information about the elements that are inside of whatever it zaps from up to several meters away. When I say rover type instruments, it's these two things that you see on the right. The Rivera Hernandez lab has a handheld LIBS, so that's what you see there. It's just an instrument that you can put up next to a rock and get an immediate readout of the elements that are inside of it that rocks are typically made out of. And then a DSLR camera replicates some of the cameras that are available on rovers to get images of what's on the surface as well. So my chosen field site to look at some of these influences is the Milner Creek Fan in California. It's sourced from the White Mountains, which are near Bishop. So if there's any climbers in the room that have ever been climbing out there, that's what you might know it from. But the Milner Creek Fan was specifically what I chose as an alluvial fan analog site because it has this bedrock catchment, or the mountains that the river is sourced from, that has 3 major rock types that it's composed of. They have long names: mafic metavolcanic, felsic metavolcanic, metasedimentary. But what you need to know is that I specifically wanted to compare the mafic and the felsic metavolcanic end members, which are to say they reflect the relative abundance of certain elements like silicon. So the felsic rocks will have more silicon, which is typically representative of harder minerals, and the mafic rocks will have a little bit less. So I want to look at some of those influences of those lithologies. And then the metasedimentary gravels ended up being a bonus, just a third rock type to compare to. We went out to this fan. We actually got to see some active water transport on it. There were some seasonal flows from snowmelt on it, which was really cool. So that's me taking some measurements of the snowmelt, just the water on the fan surface. And ultimately, what I wanted to do at this field site was to collect both field and digital measurements to basically compare the experience of what the data you could get from being a person walking around on this alluvial fan versus getting images and other remote data sets that would be more analogous to what a rover can do, and compare the two and see how much information we can get and how comparable they are and what it can tell us about how round gravels get in these alluvial fan settings. So 2 important things here for the parameters I was interested in: composition. For my field measurement, I took the LIBS out to zap these rocks, get some immediate output about the elements that they're made out of. And then for the digital measurement of the same, I'm just taking a bunch of pictures of these rocks and just classifying them by what my eye can tell, using color and texture and other indicators and images. And then to get roundness, I'm using 2 different parameters. For the field measurements, you can literally just pick up a rock and compare it to this visual comparison chart and classify it from anywhere between very angular to well-rounded. It's a quick qualitative way to go about things. And then there's also a quantitative metric to do it, which is just a ratio of 2 radii of curvature for the same pebble, and you can do that in an image, which would be the more rover analogous way of doing it. So I visited 4 sites on this fan, and I assessed 100 gravels at each of the sites. So that's 400 total gravels in this. I shot each gravel 3 times with the LIBS. That was 1,200 LIBS shots. That's me laying on the ground afterwards because it was hot, and I was lifting a lot of, not quite boulders, but a little bit smaller. It really takes it out of you. Love field work. So here's the first result from this work, and it was that the direct comparison of what I would classify as a certain rock type from an image and what the LIBS output is. So that's just the breakdown of the elements that are inside the rock. So on the right, or excuse me, on the left, what you're seeing is the 3 main rock types that I could classify by eye. On the top, you see that really orange-looking rock that ended up being the felsic end member. The orange is due to a lot of weathering. I guess there's a lot of feldspars in it that somehow weather to this orange color. The mafic rocks are darker, but they have that same kind of blocky shape. And then the metasedimentary gravels were kind of this greenish bluish color. And when I took all of those and classified each pebble that I assigned a number to, and then looked at the spectra and plotted the elements on this plot of silicon on the x-axis and sodium and potassium on the y-axis, we're getting ultimately these different groupings, which is to say that there's good correspondence between what I see with my eye and what the LIBS can tell me with the rover type instrument. A second result is that these different abundances of gravels are changing as you move down the fan. So the top of the fan is where you see that 0 kilometer mark. You see the relative proportions of each of the rock types. And then when you go all the way down to the fan toe, there's going to be changes in the relative proportions of each of them. So ultimately, the metasedimentary gravels were decreasing down the fan, and the felsic gravels were increasing down the fan. So we have these different relationships that are changing as things are being transported. And then finally, we can look at roundness and see that there are 2 different metrics that I used here, and they actually gave different results. When I look at the powers roundness, which was the visual comparison chart, all of the lithologies increased in their average roundness, versus when I used that circle tracing method, everything actually decreased in roundness, which is technically the opposite of what I would have expected. So there's two different kind of outputs from the two different methods. And then finally, when we compare the three different rock types, what you see is that the mafic and the felsic gravels, from the orange and the dark dots there, they have very similar trends to each other. And then the metasedimentary ones are ultimately rounder than them. So we have these two very similar ones that show similar behavior, and one that's different than them that shows different behavior from them. So to break down what I think I'm seeing here is ultimately that those metasedimentary gravels are softer and platier, and these internal properties that they have are probably increasing the ability for them to just abrade away completely. They're kind of falling apart. They're just changing a lot, and they're really influenced by that transport process. You can see an example of like a fresh chip of bedrock. It's very angular, and then directly downslope, the gravels there are a lot rounder. So there's a lot of abrasion happening in place from just the rock sitting there and other sediments passing on top of it as a little bit of water flows past it. And I think it's just that it's a much softer rock type. And then to very quickly tie it back to Mars, this is the same plot that I had for composition. I just put the felsic and the mafic end members on the left here, and I'm comparing it to the same data plotted on the right there for some end members of different gravel compositions on Mars. And you can see that there's a faint yellow triangle and a faint green triangle, and the two of those represent these end members for compositions of gravels, and there's pretty small differences between them, just like what I'm seeing in the mafic and felsic end members on the fan, which is to say that I don't think that there's going to be a lot of difference in roundness due to composition on some gravels that we're already observing on Mars from Curiosity rover data. So some quick takeaways here. The different lithologies, which is the metasedimentary ones, rounds a lot differently than the mafic and the felsic gravels, versus the mafic and the felsic kind of have the same behavior on the fan. And I observed these two relationships both in the field and by rover type instruments, even though they were a little different, but they were self-consistent. Quick shout outs to Sharissa, who joined me in the field, and my mom, who also joined me in the field and was instrumental for fieldwork. She's from California. And thank you to C-Star for funding this fieldwork. It was a lot of fun, and I think we'll be going back next week, or excuse me, next month. Thank you.
Thank you, Tatiana. As Penny said, moms rock. All right, so next up is Jordan McCaig, also from the EAS department. And Jordan's going to be talking about some of the genes in some deep sea salty situations.
Hi, everyone. Is this an okay microphone placement? Yeah? Okay, great. Yeah, so as stated, my name's Jordan, and today I'm going to be talking about microbes in the deep sea and how they can modify their genomes to deal with these environmental conditions. So the deep sea environment I'm talking about today is a deep sea hypersaline anoxic basin, or a DHAB for short. Just to break down what that is, it's deep, so they're at least 2 kilometers deep, and this means that there's a lot of water pressure, so a very high pressure environment just from being that deep in the ocean. They're very salty. So this salt normally comes from subsurface salt deposits that can get exposed, and then the salt dissolves into the water. And this creates something that's super salty. The transition zone can be extremely stark, going from normal salinities all the way into something that could be 7 to 10 times saltier than seawater. They're anoxic, so they have no oxygen. And these basins can be meters to several kilometers across and tens to hundreds of meters deep. So these are some pretty interesting, pretty large features that we can see in oceans all over the world. They're also very dark and cold, although those didn't make it into the name. And they're pretty inhospitable to most life forms. So if a fish were to swim into a DHAB, it would probably be instantly pickled. So not great a place for a fish, but it can be an okay place for some microbes. And since this is such an interesting suite of environmental situations, you can see some really interesting metabolisms happening and some really interesting microbial metabolites and products. They're also a potential analog for places in the outer solar system like Europa and Enceladus. So since these icy moons can have environments that are really salty, cold, high pressure, anoxic, it's possible that by understanding what sort of life we see in these environments on Earth, we can have a better idea of what we're looking for on other planets and moons and how we might be able to find them. So the DHAB in question is Orca Basin. It's in the Gulf of Mexico, just south of Louisiana. Its core brine layer is about 2.5 kilometers deep and is 7 times saltier than seawater. And like most DHABs, or like all DHABs, the conditions do get more hostile with depth. So it's saline, it's anoxic, there's not a lot of nutrients, and there are toxic metals. In the summer of 2023, the Oceans Across Space and Time, which is a research group made of lots of researchers from Georgia Tech and other universities, Went to Orca Basin and we sailed around for 2 weeks to all these different, you see the maps, awesome, all these different sites throughout the basin. And we were really hoping to understand more about Orca Basin and its astrobiological potential and the microbial ecology of what's going on down there. What I'm specifically interested at Orca Basin is how microbes can modify their DNA across the depth. So if you're a microbe and you're in a stressful environmental condition, you need to do something about your DNA, you have a couple of options. You could try to have a mutation, so change the genetic code. Like DNA is made of all the different DNA bases, so abbreviated as A, T, C, and G. You can change this code, and then this will change your genomic potential and what sort of things you can do. You can also do what's called an epigenetic modification, which means you're adding a chemical tag or some other structural change to the DNA without changing the sequence itself. So what I'm looking at is genomic methylation, which is a methyl group that you can add onto your DNA base, normally the A's or the C's, and this can change how proteins interact with the DNA. And by doing this, it can be pretty rapid and reversible, and it's been seen that a lot of microbes in different environmental conditions will actually change their methylation with the different conditions. So older sediments can have different methylation patterns, different areas of the water column have been seen to have this, and then also even in space. So it's been shown that spaceflight flown microbes can have different methylation patterns from the ground control. So to study genomic methylation, there's a few different strategies. What I'm doing is biological nanopore sequencing. The most common technology of this type is mid-ion sequencing. This is a type of long-read sequencing. So normally when you're doing DNA sequencing, what is pretty standard is to take your DNA, chop it up into a bunch of pieces, make copies, and then sequence those. This works pretty well and is really like the standard in biology. However, this isn't going to preserve things like these methylation modifications. By doing long-read DNA sequencing like this, you can sequence the native DNA itself and then capture these things. And just a quick overview of how this technology works. You have a biological protein nanopore, and the DNA is passed through this. A membrane, the synthetic membrane is here with the nanopores embedded in it, and a current is ran over the membrane. As the different DNA bases go through, they're going to change that current, and the magnitude of the change in current corresponds to the base that it is. And these things are pretty small, pretty low profile. You can use them in the field, you can use them in space. I brought one out to sea and was able to get my samples and be sequencing them in the span of a couple of hours. And as I mentioned, these things can help you look at genomic modifications. So in this picture here, if this red circle is your methylation, you can see how as it goes through the nanopore, it's going to change the current in a different magnitude from an unmodified base. So by using this mid-ion nanopore sequencing, you're able to study the methylation. So to do biological nanopore sequencing, you do need a pretty big biomass, which meant I had to do a lot of sample processing to get enough DNA to work with. So we'd collect our samples in these Niskin bottles, and then I would do 2 sets of concentration to take my samples from 4 liters down to about 200 microliters. So did the concentration on board, drove everything back to Georgia, and then started doing some lab processing. I extracted my DNA samples and then prepped them for sequencing, which this meant I just added some chemical tags onto the DNA that made it compatible with the nanopore, and then also made it so that I could see which sample I was using so I could sequence everything at once. We did our nanopore sequencing, and this gave me raw current readings. So to convert the current readings into your DNA sequences, you do a process called base calling. So we use the Dorado method from Oxford Nanopore, and what this does is takes your current readings and converts it into your A's, T's, C's, and G's, along with the quality of the reads itself. But when you have this, you just have a bunch of DNA strands. You don't know who they came from or where in the genomes they fit. So you can do a process called metagenome assembly. Metagenome assembly is essentially taking all those reads and putting them together into your microbial genomes. You can do this with just short reads, but you might have some gaps. You may not know the overall structure that well. You could do it with long reads, which will allow you to get better structural resolution, or you can combine both short reads and long reads, and this allows you to get the most accurate, the most complete genomes. So we did that, and we got metagenome assembled genomes, or MAGs for short, and then aligned our those reads back to the MAGs, and then got the methylation information, which is what I'm working on right now. Yeah, so we did all of that. We got a lot of long-read sequence data from 7 depths at P5, which is up here in the northern lobe. Obviously, there are a whole bunch of other places that we also went to, but since it takes kind of a lot of work to get these samples ready for nanopore sequencing, I just chose to do my full workflow on one sample. But other people in the Oceans Across Space and Time team did do this long read sequencing, so I was able to perform they did short read sequencing, so I was able to perform hybrid assembly. From this, I was able to get 105 metagenome assembled genomes with a complete list greater than 50%, and of these, 31 of them are more than 90% complete. So this is giving me a lot to work with. And that's what I'm doing currently. I just pulled the methylation results from one of my taxa to give an example of what this looks like. These are from desulfobacula, which is an anaerobic sulfate reducer that I saw a lot of in my samples. And my methylation things will kind of look like this. I can have overall this knowledge of where in the genome the methylation is, what percent methylation we're seeing, and have its location within the genome itself. And then we can also see methylation motifs. So there are specific sequences of DNA that are more often methylated than others. And these things can have certain functional associations and tell us different things about what the cells are doing. So I'm currently going through all of those and trying to understand more about the overall emerging methylation patterns. And with this, I'm hoping to learn more about how microbes can specifically modify their genomes to deal with life in some of these really stressful environments. And with this, hopefully we will understand greater how things can live in these environments and understand how to look for them in other places. And with that, just wanted to thank people who are involved in this work, including the Oceans Across Space and Time team, the POINT-SIR crew and research group, my group here, the Planetary Exploration Lab, and our funding sources. Thanks.
The next speaker we have is an online speaker from the University of Florida. So give us just a second while we make sure that the connection is working and that the volume will come through the speakers and everything. Maximos, can you hear us?
Yes, can you hear me?
Yes, perfect.
All right.
Oh, all right. So we'll pull up the slides and I think that you'll have to tell Olivia when to click through to the next one, if that's okay with you.
Sounds good.
Okay. Okay, so I'll introduce you real fast. This is Maximos Gumos from the Department of Aerospace, Physics, and Space Sciences at the Florida Institute of Technology. This is our only talk today from a student who isn't at Georgia Tech, but we're hoping to have more Southeast presentations in the future from outside the tech community. So if you know someone, next year, send them here. All right, Maximos, it's all you.
Awesome. Thank you very much. So, hi, my name is Max Gumas. I work with Dr. Manasvi Lingam and more recently started working with Peter Higgins in the bioenergetic modeling of methanogens in Europa's subsurface ocean environment, which is all theoretical work. There's no actual field work in this. So I'm going to start off with some overview and motivation, a little background about the project. So next slide, please. And next one. So our central objective is essentially to study the subsurface environment of Europa with the goal of predicting possible amounts of biomass and potential biosignatures. This is the pretty much end goal, but the results that I'm going to be presenting here are more in line with the third bullet point there about simulating these methanogens with each other and the environment to determine the habitability and survivability of the environments from a bioenergetic standpoint. So next slide. So a little bit about why we chose methanogens. There are multiple lines of evidence that point to their probable survival in non-Earth environments. There's many laboratory tests that show that they're super resilient. They can handle a wide range of environmental conditions and don't necessarily need sunlight. And they can handle high pressure, low water, high water, a variety of different temperatures, by different pH values. Also, the necessary reactants for methanogenesis are either thought to or known to exist on Europa, these being CO2 and H2 gas. And it's also thought that Europa may have hydrothermal vents on the ocean floor, and we know that methanogens exist around hydrothermal vents on Earth. Next slide, please. So, why we choose Europa? Well, it may not come as a surprise to most of you in the room, but as it being one of the icy moons of Jupiter, has a large subsurface ocean, and we know that water is required for life, as we know it. Like I said before, it may have these hydrothermal vents on the ocean floor that we know host a variety of different organisms on Earth. And the presence of the energy and heat combined with the liquid water and a protection from an icy outer shell kind of forms this perfect environment for life to exist underneath that icy shell. And next slide, please. And we do know that there are some missions coming up, including Europa Clipper, that will provide more evidence of the composition, the structure of these icy moons, and specifically of Europa. So now I'm going to be going through the code that I use on the next slide. I use a code called Nutmeg, which is written by Peter Higgins and Charles Cockle. and this stands for nutrients, maintenance, energy, and growth. And essentially, the authors describe it as an astrobiological model for assessing the energetic and nutrient availability of environments to predict their potential biological productivity. And it can be used to estimate how much biomass an environment could host and how that life might affect the local chemistry. So on these flowcharts we have here, this is essentially the structure of nutmeg. On the left side, you start with an energy source and a nutrient source, and you put in the required processes that go along with each one, along with their associated efficiencies represented by those epsilon sub m and epsilon sub UTs. And then any extra energy or nutrients go into the growth of the organism or the population. On the right side there, just really quickly, this is how the code is really structured. You start with your base organism that you define, that the user defines, and the environment, which holds the environmental properties, physical parameters like temperature and pressure. And then you define the reagents, reactions in that environment, combine the environment, the reactions, reagents with the base organism, all into a big ecosystem and simulate that over your set amount of time. And it could produce a variety of outputs. And the ones we're going to be focusing on today are going to be the power supply outputs. Next slide, please. I also use the GeoChemist Workbench software, which is used for geochemical modeling, as the name suggests. And this is essentially used to set the initial composition of Europa's ocean based on a literature review. And it's also used to see how the bulk ocean pH changes when the ocean was warmed from 0 to 200 degrees Celsius. So next slide. This table shows the starting composition along from a literature search of the simplified ocean composition and chemistry with the nominal case, a higher salt case, and a lower salt case. This is also goes along with like a theoretically unlimited supply of water. It's not actually, but in this case, we treat it like there's enough water for everything to happen. And we also use the H+ concentration, which is not listed here, to set the initial pH of the ocean as well for our different trials, I would say. So next slide. So now we're going to be moving on to the results. And the first one we have, actually first a little bit of background on the results in the next slide, is the parameters for Europa were used in place for those for Enceladus. The original nutmeg code comes with an example that was written for Enceladus. And so we changed the code to now focus on Europa with our Europa composition, temperature and pH ranges, and all the other associated changes. We also are using what's called a typical optimal methanogen, which is a theoretical artificial methanogen designed to behave as if any given temperature were its optimum by mimicking the growth behavior of a real methanogen that is well adapted to that said temperature. But this is also based off of real methanogen data, but it's kind of like the average of these methanogens to create a optimal methanogen. So on the next slide, we have the first result, which shows the available power supply for combinations of temperature and pH for these hydrogenotrophic methanogens. And you can see here that the higher the power supply, you kind of favor that higher temperature, lower pH range. And these dotted lines here also represent the evolution of that pH as you warm it from 0 to 200 degrees Celsius, like I mentioned before. On the next slide, we have the high and low salt cases as well. That previous one is for the nominal case. And you can see on the left side, that was the low salt case, and the right is a higher salt case. And you can see how the power supply will change accordingly with that, with the lower kind of favoring a lower pH, the higher salt favoring the slightly higher pH as well. On the next slide, we have these line plots that show the power supply available with these specific combinations of temperature and pH, with either having the temperature set constant or the pH set constant. And this plot has been split in half. So the top of the plot is on the left side, the bottom of the plot is on the right side. And again, you can see that the higher temperature, lower pH is more favorable in most conditions. And it shows these shaded regions that essentially show like the maintenance power for optimum conditions, maintenance power for anaerobes, to show how the power supply relates to those as well. On the next slide, we have the different criteria for habitability, which relate to the previous plot as well. And again, these shaded regions and the color of them correspond to whether or not you have enough power available in a low, high, or nominal salt case to meet certain habitability criteria, which again, of course, kind of relate to the shaded regions on the previous plot. Again, on most of these cases, you can see that lower pH, higher temperature favorability to have enough power available for these habitability criteria. I should say that the 4 panels going also on the left side, the leftmost panel corresponds to exponential growth of methanogens. The one to the right of that is the exponential growth of anaerobes. On the right side, the left plot on the right part of the picture is to exceed the minimal maintenance power. And on the very rightmost is the minimal power consumption associated with methanogens in modern Earth deep marine subsurface. And on the next slide, just a little bit of summary and future work. Like I said, the central theme of this project was to constrain the habitability and ecosystem properties of Europa and eventually other worlds. And this can help design future observations, compare with the data being collected from these future space missions, open laboratory missions, etc. And then lastly, on the last slide, some of my future work that I'm going to be going through is finishing up this analysis, delving deeper into why it's doing what it's doing, and writing this up in, we're currently writing this up in a paper as well that should be out later this year. We also have plans to expand this to other worlds or moons, specifically Hycean worlds, and potentially the Hadean Archean Earth as well, and potentially combine this with other models for deeper, broader analysis, and also show potentially the biomass evolution and the amount of methane being produced that could then be used in conjunction with other models to see how much of that methane could be seen from the atmosphere, for example. And then the last slide, I'd like to thank you for your time. If you have any questions that don't have time to ask here, feel free to email me at the email listed there. And yep, thank you very much.
Thank you so much, Maximus. There was vigorous applause in the audience. I'm not sure if you could hear that. All right, our next speaker is Sharissa Thompson, who's going to be talking about something very similar to what Tatiana spoke about, but from a different perspective. And then Maximus, if you can still hear me, stay online for the panel at the end of the session after this next talk, please.
Testing, testing. Is that good for everyone? Okay, amazing. Hello, everyone. As it was previously mentioned, I'm Sharissa Thompson, and today I'll be discussing constraining effects of spatial resolution on fan grain size estimates from thermal inertia, insights from the Milner Creek fan in California, which we've seen before now. So the motivation for this work is that we've seen evidence of liquid water persisting on the surface of Mars's surface in the past, and evidence are imaged here on the left, alluvial fans. So this is a CTX image. I believe it is the same one that was in the previous presentation. And so an alluvial fan is a depositional environment in which sediment is transported across a shallow slope by water. And the range of grain sizes that we get on this surface can lead us to understand how much water availability there was in the past, because we expect larger grains to deposit much quicker. But if we see larger grains depositing further down slope, then that means that there was more water available to deposit those grains. And so for our study area, we looked at Milner Creek Fan in California, which was a 30-minute drive north of Bishop. And so this is a Landsat 8 image here, and this is one of the data sets that I was using. And so how do we understand these surfaces? Previous work has looked at thermal inertia data to understand the surface properties of alluvial fans on Mars's surface. And so they're characterizing how these grain sizes change along the slope. And so what is thermal inertia? Thermal inertia is the ability of a material to resist change in heat energy. And so what this means is that materials that have high thermal inertia are equitable to what we would consider coarser grain material. And this means that it takes a lot more time for that material to either heat up or cool down, so it's more resistant to change. Whereas lower thermal inertia, we equate to finer grain material in which it heats up and cools down really rapidly, or it's able to change rapidly, and it's not able to resist as much. And so from this, I've come up with the following questions of how do changes in spatial resolution and areas covered per pixel impact relationships between thermal inertia and grain size distribution? So how does thermal inertia and grain size relate to each other? And then the second question, is there a correlation between grain size sorting and the apparent thermal inertia values? So new term, what is apparent thermal inertia? So due to the inconvenience of our atmosphere, boo, not really, we're unable to derive thermal inertia like they are on Mars from satellite imagery. So we have to use apparent thermal inertia, which is 1 minus the albedo or reflectivity of a surface over the difference in temperature. And so here on the left or right, mirrored, is 3 sublocations that we visited, and going down from top to bottom is going from the apex of the fan to the toe of the fan. And so these were taken with a Mavic 3T thermal drone that has about 3 centimeters per pixel resolution. And then over here on the other side, we have a Landsat 8 image showing the entire fan with these locations highlighted on it, showing the apex and the toe. And this blue line with the outlines also highlight the incised channel from which we collected most of the data. So we chose this incised channel to make sure that we were collecting grains from a similar transport process. So this incised channel is all from a channelized water movement down the fan instead of from either debris flow or more sheet flows. So we're able to just investigate how this one process is changing the sorting of the grains as you go down fan. And so we look at the thermal inertia, but how do we compare it to grain size, and how do we understand that and correlate it? So this is what we consider boots on the ground and hands in the sand, kind of just, we went in at each of those transects highlighted in the previous slide, and these blue lines going across are the transects that we went through to collect by hand the grain size distribution using a gravelometer imaged here. And so we would walk unbiasedly backwards or forwards with like our eyes kind of closed to pick up each grain and put them into the gravelometer to measure their size and record it to get that distribution. And so the results from that is that as you go, this is the x-axis has distance down fan, so the apex is towards the left and the toe of the fan is towards the right. And so we see that there is a decrease in apparent thermal inertia going down fan. And this is looking from the Landsat, which is that 100 meter per pixel resolution, to the drone imagery. So that's why it's kind of separated for the drones, because we only have it at those 3 locations going down the fan. And we do see a trend between the 2 of them. So from that, we can interpret that with decrease in apparent thermal inertia, it correlates with that decrease in grain size down fan, which we had hoped to see with the data. And so this image is just showing apparent thermal inertia plotted against median grain sizes, so about the middle range of grain size that was collected from that gravelometer data, as well as the plot on the left side showing you just that distance down fan against the apparent thermal inertia as well. And so the second result that we found was that the drone has higher apparent thermal inertia versus distance down trend down fan. And so this means that what we can interpret from that is that with the Landsat, the lower spatial resolution, it's harder to reconcile the actual distribution of grain sizes. As you can see from these images here, the Landsat image is covering a wider swath of an area. So the actual ability for us to detect the grains that are distributing in certain areas is lower than the higher resolution drone imagery as on the bottom side here, where you see that 1 by 1 pixel is inside of that larger Landsat pixel, and we're able to actually define the surface properties more, as well as the patterns on the surface from those grain size distributions. Okay, and so our third result was that moving down fan with apparent thermal inertia, the trends are more sensitive to grain sorting than other effects. And so this is a fancy equation that helps us understand how well the grains are sorted per each location. And we see that the correlation going down fan relates to this. And so we can tell that sorting impacts our results for apparent thermal inertia. And so if we have a lot of larger grains in the pixel, those will, compared to smaller grained items in the different ranges, we can say that that is impacting the apparent thermal inertia more than just individual grains compared to each other. And so for future work, going into the field and walking blindly along a transect layout is good and all, but it doesn't cover a wider swath of an area. So hopefully in the future, we will use these modeled images to get at grain size over an averaged area to better understand using these outlines here in number 2, and then measuring their sizes from the model in 3. And so it'd be by percent of boulders versus percent of pebble to cobble and percent of fines like granules that are smaller or harder to detect in the images. And so the take-home points of the study is that higher spatial resolution helps to reduce scatter, which improves insights on trends in the data, and that more data will need to be plotted to confirm the apparent correlation between apparent thermal inertia and grain size sorting. And so these are just the results labeled out here, and that is it. Thank you.
Thank you, Shrisha. Don't go too far because we do have a panel. Okay. That was an awesome talk. Thank you so much for giving such a different perspective on the same sort of a field site that Tatiana was talking about. That was really cool to hear. Okay, can I have the other speakers from this session come up? And Maximus, if you're still online, stay alert in case we have a question for you.
Sounds good.
Thank you. All right, I will open up the floor to questions. Okay, I'll start. Christina, I had a question about the different OH stretches that you were looking at. When the water is interacting with the mineral, would you expect the OH stretch to be shifted, not just like depending on the amount of mineral, but like a different mineral that might have more hydrogen bonding capacity or something like that?
Yeah, so that's something that we're still trying to figure out is like what's causing this differences. There's certainly the possibility that like a mineral with a surface that promotes crystallinity could have more hydrogen bonding, and hydrogen bonding could be part of like the mechanism through which we get more order. I still don't know exactly what's causing this. I would expect like part of the shift in energy to be due to that. But what's interesting is from what I've seen, we don't get just a shift in position without a change in shape at that 3 micron band. So that's suggesting that like it's not necessarily that we're in the same geometry, but everything's more stable. It's like it's changing geometry as well as the energetics. I don't know why. If anybody has ideas, please let me know, but I don't know. Yeah, thanks.
Very cool, thank you. Audience?
Thank you. My question's for Sharissa. There was a plot with, I believe it was a distribution of grain sizes, and there seemed to be a peak like midway down the fan. Do you know what the cause of that specific peak was?
So sometimes it's parts of the inside channel, and that would cause. Oh, so sorry. Wait, should I start from the beginning? Okay. Yes. So the instance channel that we were doing our data within was emplaced within debris flow deposits. And so some of those debris flow deposits would onlap into the insides channel, and that would kind of get in the way of the, especially for the Landsat data, would get in the way of the grain size sorting going down fan because we would see debris flow deposits instead of the actual insides channel deposits that we were trying to focus on.
Okay, yeah.
Yeah, so the question is, for my work, I saw some inconsistencies in the results for different methods for roundness. And the question was if maybe the debris flow deposits were influencing my roundness in any way. And I think something to add to Sharissa's point was that in some places, I think we had a little bit of bias and we were intentionally selecting places along the channel that almost looked similar to each other in the different sites. So we would, just basically walk into a dry river channel and see somewhere that had a lot of pebbles that look like the same size versus like what's called a boulder bar, where you see a pile of boulders that are representing a different kind of deposit, but also still fluvial. In my work, I was not sampling the really fine stuff, which is what the debris flow deposits would be, there would be a lot more mud in them, at least in the ones that Sharissa was talking about with the finer grains. So I don't think that's necessarily what was contributing to a difference in my data. My results are still very preliminary and I want to spend a lot of time thinking about the differences there. So no super satisfying answer, but I know that it's not the influence of the debris flow deposits.
Let me give you the mic.
Hello. First of all, hello from a former Florida Tech alumni. And hello to Dr. Manafsi, as he was my former academic advisor. But specifically, I wanted to ask on your prediction model that it focuses mainly on hydrogen-trophic methane or methanogens for an Archean evolutionary stage of a planet. It's been hot debated whether even hydrogen-trophic methanogens were either the oldest evolutionary type of methanogens versus a methyllotrophic. So I was wondering if in the future were you going to be considering any methyllotrophic or other types of methanogens in the future, and if so, how would you implement that, since some of the other methanogens have a very complex metabolic pathways?
Yeah, so for right now, we're only focusing on the hydrogen-trophic methanogens, and we don't have plans to look at other types of methanogens right now. But if you wanted to include those, the code nutmeg is extremely customizable, and so you can put in whatever organisms you want, a combination of different organisms. You can simulate the competition between them, and you can put in whatever chemical reactions you want, whatever reactants you want, and it'll simulate all of those. But as of right now, we're only focusing on these hydrogen-trophic methanogens.
Thank you, Maximus. More questions from the audience? I have one for Jordan. So as you're doing these metagenomic assemblies and whatnot, you talked about methylation being something that occurs under stress. Is that something that you expect to see more of with more depth and more salinity, or are there other patterns that you think will be expressed, like more methylation on saline managing genes or something? I don't know.
Yeah, so I think there could be some sort of either increase or decrease broadly over depth. And that's something that I am looking into, but I also think I'll probably see like certain types of maybe classes of genes being more or less methylated. I also think like I did kind of paint with a broad brush, like the overall, as it gets deeper, it gets more stressful. But as you go through the water column, there are a lot of different like layers that have interesting nutrients and things. So I think there'll be probably some interesting patterns really around that like seawater brine interface. But yeah, so those are my thoughts right now.
It triggered me to remember the question I was going to ask you, Jordan. And how fragile is the methylation? You know, I mean, it's reversible. What does that mean? Does it take a really big hit, or, you know, can it be a minor change? And is there any regularity to that, or is it stochastic?
Yeah, so I know that the methylation, it is something that also, like, besides the epigenetic modifications for like environmental stressors, it's also something that's used for different microbial strains to like distinguish self from non-self. So things like that I would expect to be a lot more like not really encoded, but more robust. I'm not totally sure, like in terms of these things that are getting more quickly switched on and off, like how robust they might be. But I would imagine that's something that as we kind of go through the water column, we might start to see some patterns about that.
Other questions from the audience?
Yeah, sure.
Yeah, so the question was for my experiments, were there differences in the 5 and 10 weight percent? You didn't miss anything because I didn't show that because I didn't have time. And I don't have a clear picture. So it seems like it really varies depending on the mineral. Some minerals seem to have a lot more tetrahedral regular crystal structure at 5 weight percent, others have more at 10%. And I don't really know why. It seems like with at least 2 of the minerals that I tested, you can get something that looks that has very little crystal tetrahedral structure and a lot more amorphous structure than water injected at the same temperatures, but the amount of that is different. So I think that's like 5 weight percent LHS1D, but like 10% olivine. I'm not sure why. This gets back to the larger question of like, I don't really know exactly what's driving these differences, but they're present. And even going from 5 to 10 weight percent, that will change evidently a lot of things in solution. Something that I didn't mention was that all of the mineral grains here have sizes of less than 40 microns. So I'm sure that there's going to be a large grain shape and size change as well. I don't think it's that the differences between the types of minerals is due to the shape, because from particle sizing that I did with Sharissa, actually, it seems like they're all pretty much following the same particle size distribution. But yeah, there's lots of parameters, I guess, that we're still trying to nail down. Yeah, thank you.
I have a question for the panel. So especially Tatiana and Shrissa, since you went into the field together and you work closely together, but all of y'all have been closely involved with the astrobiology community on campus. And like you just mentioned, you and Shrissa have worked together, even though your projects are kind of distinct. And what I wanted to ask is, how much do you feel like the community that you are part of and the people in your lab that you get to work with and the people in other labs that you get to work with, how much do you think that that supports and extends the progress that you can make as graduate students?
As someone who uses instruments in many different labs, I feel like it's very supportive to be able to expand and like answer more questions, because we're able to do more analysis with different instruments that might not technically be in our department. So it's very helpful, and it's really building up, I feel like, more of the community.
Yeah, very similar to Sharissa. So I'm not in the EAS department. I come from chemistry. I know a lot about weird things that things do under the chemical and physics stuff. I know nothing about rocks. Rocks are very intimidating and scary to me. So that means it's really nice to be able to go, oh, okay, I know, like, I could talk to Olivia about reflectance absorption in the IR. I can talk to Sharissa about particle sizing. I can talk to other grad students and other professors about their work and how that could help with mine as well. And honestly, a major part of why I picked coming to Georgia Tech was because people do really interesting work here, but also they want to talk about it and they want to talk to each other about it. And I guess that's rarer than you'd expect.
The collaboration I've gotten to do with other people just feels so real, especially in our lab group. Sharissa and I got to do that field work on our own, and it was really nice to feel like we had the ability to just plan things around what each of us needed, and I really appreciated that. I've also gotten to do field work with Jaleese and Olivia in my group, and just coordinating all our goals together feels really good to be contributing one aspect to a larger project, and having data sets that complement each other has been really exciting to see, like, and compare the data that we have from a bunch of different field instruments. And it's one of my favorite parts of Georgia Tech astrobiology.
Yeah, big fan of Georgia Tech astrobiology. But like, yeah, this organization has been so useful for like getting those networking skills and also just like helping to grow this community and being able to zoom out and think about these big picture things, which is so emblematic of like what astrobiology is too. Like, I can think about my microbes all day, but like I'm gonna have to talk to someone about a rock at some point. And this is a great place for that.
Yeah, and everyone up here has been an astrobiology fellow, like I am right now, and Olivia and Jaleese and Chloe. And that's about time for the panel, so y'all are welcome to sit down. We do have a couple more things on the agenda, but let's give them all a round of applause before we do that. Okay, so Dr. Glass is going to come up here and hand off the astrobiology graduate certificate recipients. As we're getting set up, and Chris and Francis, I just want to build off of what the panel just said about the astrobiology community at Georgia Tech. I am so thrilled. I will start crying if I talk too long, but I am so thrilled to be part of this community and to have gotten the opportunity to help plan this event. It's been incredible, and it wouldn't have been without all y'all. And I'm especially grateful for the other fellows who worked so incredibly hard to make this event so awesome. So thank you all.
And a round of applause to all the organizers, the Astrobiology Fellows. Yes, so the fellows, again this year, Abby, Jalise, Olivia, and Chloe, who's at the top. Thank you so much for organizing this event, picking the invited speakers, organizing the food, reserving the room, not only for this event, but also the event that we had in the fall. So we really appreciate all the work that you've been doing.
It's been fantastic working with them.
Yeah, so let's give them a round of applause for all the hard work. And we will, at some point, have applications for the next round of AstroBio Fellows. And so keep an eye out on that. And if you want to learn more about that, we'll eventually send out an application, and you can talk to past fellows. Again, I saw Sharissa, Buffo, Tatiana, Jordan, Emmy's not here. Jose Luis, Sarah. Yes, I think all of you are. Vahab was here earlier. There are a lot of past fellows that you can ask as well. So we really appreciate. So right now we're going to be doing the AstroBio certificate ceremony. And who would like to do the announcing? Sure, maybe Chris and I can split it. And then, oh, perfect. Okay, so we're going to start, and actually we're going to go through slides. We have slides for each student, so if you don't mind just flipping through. Thank you, Olivia. Yay, okay, our first recipient is Leah Adepujo. Thank you. And then we're going to start like a lineup.
Sure, we can do, well, we can trade. I think that's, yes. Next up, we have Crispin Gamble. Is Crispin here? Ah, perfect. Next up is a student in my group, Tatiana Gibson. Yes. All right. Bia Hale. Is Bia here? Hey, Bia. Here. All right. Next up, Julia Lynn. Julia. Yay. Awesome. Brianna Lindgren. No, I don't see him. Next up is Samuel Long. Yeah. He's awesome. He was in one of my classes. Yes. Samuel. Alex Rodriguez. Yep. Charlotte Thomas Wilkinson. Come on down. We got a big group this year. This is awesome. Yeah. Sharissa Thompson, also from my group. And then Yasin Watson. Is Yasin here? They might have been here earlier. Yeah. So just as a reminder, these are everybody who did the AstroBio grad certificate. And so we really appreciate everybody. All right, let me. Okay, yeah, it just takes a second.
I also wanted to thank Leah, who's not currently a fellow, but that she did help with setting up the lunches last semester with the speakers, and that we also had a couple people help, like Jordan and Buffo also help with that. Thank you so much. Jose Luis has been doing the ads as well, even though he's currently not a fellow, and so I really appreciate all you do to the community. The students really are the heart of the AstroBio program here at Georgia Tech, and so thank you so much, and I can't wait for next year. Thank you.
Okay, so this room is reserved immediately after us, so please vacate, but there is plenty of space in the hallway to hang out and chitter chatter some more. Please take any trash that you see. There's more food up there. If you see a sandwich that you want to take it with you. And there's no pizzazz next week, so don't. Yeah. But please do pick up any trash that you see. We are guests in this room, so let's try to keep it clean. Thanks, y'all. Come back next year.